Hey guys, we have received multiple grievances about the sound quality of many of our previous videos from multiple viewers over a long period of time. We paid serious attention and as a solution, we are republishing all our episodes from the Verilog series all together in this marathon episode by digitally remastering the audio. In this marathon episode, you will learn Verilog basics such as structural gate level modeling, data flow modeling, and behavioral modeling. You will learn how to create test bench using Verilog and test your design using live examples. Before anything, you will learn to install popular Verilog simulator such as Vivado, Icarus Verilog with GTK-Wave. You will also be introduced to Geany, the lightmost IDE for Verilog coding. Next, you will be introduced to the basic concepts such as if-else conditions, case, CaseX, CaseZ, for, while, repeat, and forever loops. You will be introduced to a special loop called generate loop. Next, we will enter into the comparative study of continuous versus procedural assignments, blocking versus non-blocking assignments, where versus reg statements, task versus functions, and synthesizable versus non-synthesizable Verilog codes. Finally, we will cover advanced topics such as usage of timescale, SDF Back-Annotation, VCD file tasks, compiler directives, PLI routines, and printing constructs. This is a must-have marathon for all VLSI aspirants. So stay tuned, stay focused. Hey folks, welcome back. In today's episode, we will be discussing the below points. Introduction to Verilog HDL, V-curve of Verilog design. We'll explain the components of the V-curve as well as why this is a V-curve, means the shape of V. We'll explain that also. HDL compiler versus synthesis compiler. So in VLSI, there are two types of compiler, very closely spaced. We'll talk about them. C language versus Verilog. You will find a lot of similarity with the C language. Hence, we would differentiate the C language versus Verilog so that your concept is very much clear about the Verilog with respect to the C language, which you might have learned already. Next, we will point out the comments in Verilog, which are very important of any language. Next, we will go through our typical Verilog module and we will also go through corresponding test bench to test that Verilog module, and both are examples, that means explicit Verilog code. Next, we will talk about the bird's eye view of any typical Verilog module. This helps you to create a snapshot what are the components that should be there inside a Verilog code. Next, we will summarize our entire discussion. So that's the menu for today. Without any further delay, let's begin. Introduction to Verilog HDL. Verilog and VHDL are the two most common hardware description language, that is HDL, used by beginners in integrated circuit design. There is a typo, it should be integrated circuit design. HDL syntax and semantics allow the design or sub-design or components to be simulated and corrected during the circuit realization and simulation. Designs described through Verilog or VHDL are technology independent, easy to code and debug. However, in actual practice in the Verilog, we transform this code for a technology dependent synthesizable netlist, and that we will talk later. As HDL, Verilog can be used to describe designs at 4 levels of abstraction. So these are very important. Please pay attention to these 4 points. First, algorithmic level, much like the C code with if, case, loop, etc. Next, the register transfer level, often abbreviated as RTL, uses registers connected by Boolean equations. Gate level, interconnected format of AND, NOR, etc. The basic logic gates. Switch level. The switches are most transistor inside the gate. The language also contain constructs. Those are used to control the input and output of a simulation. So from here you can summarize that Verilog is a very well equipped hardware description language that not only describes a digital circuit used for ASIC design, but also it has the necessary components to simulate the behavior of a digital circuit written in the Verilog. We need a simulator, however, to process these codes. We'll later discuss about the paid and free Verilog emulators. So that's all with this particular slide. Let's move on to the next slide. V-curve of VLSI design. Now this is a very important slide. Please pay very good attention. I don't expect that at the very first go you will understand this. However, this is the architecture that is used in most of the VLSI designs. How a design is realized from the thought level up to the actual silicon. So this curve is a theoretical curve. However, this curve is followed in the practical ASIC design. So let us start with the first step. First, we'll list out the system requirement. That means whatever chip we are designing, what are the requirements, what should be their input, output, and whatever like the truth table and all. Next, we design the system. At this stage, our design begins. Now, if we dive further down, we see the design subsystem. That means our entire system, a chip, is further divided into smaller blocks of individual design, which are very much independent in performance and functionality. Next, we design components. So for any subsystem to get realized, if we break it further down, we have to design individual circuit components like maybe gate, AND gate, OR gate, etc. Now we might say that the logic is there already, what we have to do. However, the logic is there, but in terms of the Verilog code or synthesizable netlist or the physical layout, you have to design them. So this is the design components. So you can understand this is a very much broader perspective of the chip design. It is not very much specific to the Verilog only, but rather it expands for the entire VLSI design. This slide has its importance. That's why I have kept at the very beginning episode of Verilog, so that you have the impression of this slide and you carry out this slide throughout your entire VLSI journey. At the next stage, a designer realizes the components using simulator, codes, etc. etc. Next, build and check components. So at left you can see that the design components is here. Once the components are realized, it is build and check for it functionality, connectivity, errors, everything. Next, once the components are done, we move level up to the subsystem level. We design the subsystem with the help of the components. Next, we finalize the subsystem at this stage. At the next stage, when we do a level up, we build and check the system using different subsystem blocks. So this is a very bigger block of design. We are approaching towards the finalization of a ASIC design or a chip design. Finally, once all checking etc. are done, we get a working system and the chip is ready for tape out. That means all these steps. Now, you can imagine that these steps are there. Okay, once we go past one stage, it is done. No, you may have to iterate in between two stages until the two stages are in sync and properly designed. So maybe from design system to design subsystem, you might have a couple of iterations. From design subsystem to design components, you might have a couple of iterations. From design components to the realized components, you might have couple of iterations. In the similar way, any two stages can have different level of iterations based on the fine tuning, based on the target design, based on the target functionality, based on the put out of any error that is coming. So all these things will be there. It is very much practical to have multiple iteration. That means you are not perfect at the first go of any stage. That might happen in some one exceptional cases, but in real cases, you will iterate through two different adjacent or neighboring stages multiple times. So this is the V curve of the VLSI design, and the significance is that whenever we start to write a VLSI code, you might think, where are we? This is the entire big curve. Where we are? So let me bring my mouse. So if you are inside a VLSI company who makes chips, right, you might find yourself at the first go. If you are a beginner, right, you might design components first, and the senior folks who are much more senior to you might design a subsystem, and people senior to them might design a system system. So these are very parallel. So whoever designing are also checking. So that means you are designing components and you are checking components. As a beginner, you might start with these three parts, and as you grow older in the VLSI company and you get more experience, so you do a level up. The things level up, you level up. So this is the kind of method that is followed in a typical VLSI company. So we are done with this particular slide, and I have shared whatever needed to be shared in this particular slide. Let's move on to the next slide. HDL compiler versus synthesis compiler. Why I kept this thing? Because once you enter into the VLSI industry, you might hear two names. One is the design compiler, it is from Synopsys. Another one is the RC, I think it's from Cadence, so RTL compiler. So these things are somewhere used in the synthesis part. So whatever you are learning with the free tool, maybe as a student right now, you might get confused that, okay, what is the difference? To make you understand the difference and you don't get a jerk once you enter the VLSI arena, I have kept this very simple, short and sweet difference of these two compilers. One is the HDL compiler that you can start using right now with the free versions or the free and open source versions. And once you enter into the VLSI arena in a company, right, there you will get the paid versions, that is synthesis compiler. So these are different things and they are for different purposes. Here, let me demonstrate. So here is your Verilog description, that is a .v file, and it passes through a HDL compiler that you can readily avail as from the archives of the free and open source tools. And this is a translated design. Now we have the translated design. At the next stage, this can be passed through the synthesis compiler. Here I named the DC from Synopsys and RC from Cadence, right? So these can be used at this stage to produce with the help of the ASIC PDK or DK library and the standard cell library, whatever they are. Generally these comes both together, the PDK and the DK. I have a episode in my channel in the VLSI FAQ about the PDK and DK. Please go ahead, deep dive inside that episode. You can find in the VLSI FAQ playlist this particular episode. There I have explained what is PDK and DK in detail. So please watch that episode. Now let me come back to the point. Once this is integrated with the synthesis compiler, the translated design can be further translated in technology-specific synthesized netlist. So this is the difference. The output of the HDL compiler that you can readily do with a free and open source version is not technology dependent. That means it is not from maybe TSMC 90 nanometer technology. It is not from that. So it is technology independent. So that can be used with TSMC 90 nanometer or UMC 90 nanometer. So like that, whatever the foundry, it is independent. Now at the next stage, once you add the PDK and DK in the synthesis compiler, right? So there you add the technology data, and the next level of realization is the technology specific synthesized netlist. So this is the difference between the HDL compiler and the synthesis compiler. So here the short and sweet difference is explained to you. Hope you have grasped the meaning. And with that note, let's move on to the next slide. C language versus Verilog. Generally in colleges, you learn your first programming language as a C language. Now, once you are exposed to the Verilog, you will find a lot of similarity in between the two. And the immediate pitfall for you, you start to correlate both of them. Stop doing that because these two are not same. The reasons are, because Verilog is a HDL, so it is for to defining a hardware. Verilog code intended to be synthesized into actual hardware, actual chip, that is actual IC. As a programming language, C is everything to be converted into executable hex file, which is to be loaded in your RAM while executing the program. So there's a fundamental difference of the Verilog code and the C code. Now let me explain it to further. If you have written A plus B equal to 1 and C plus D equal to 1 back to back in Verilog, then during the simulation, both equation will work simultaneously. That means it's a concurrent system. That means everything is simulated with respect to the time. At time t equal to t1, both the equation will get simulated. But in C, everything is sequential and there is no time here. We cannot enter time inside the C language. There are some provisions you can capture the CPU time, or with respect to you can add some delay, but that is not the real transient simulation. So this is not, C cannot do a transient simulation. Whereas in Verilog you can have a transient simulation. That means the simulation where the simulation and the values is changing with respect to time, and time is in x-axis the changes and the values are in y-axis. In C there is no chance of having a time in the x-axis. This is a fundamental difference of the C language and the Verilog. We are done with the basic difference of C language versus Verilog presented in this slide. So let us move on to the next slide. Comments in Verilog. In any language, the comment is a very important thing. Why? Because whatever you are writing the code, the purpose of the code or the section, whatever means, if other than you, anybody has to read it, they will get help from the comment. Even the code becomes bigger, maybe 10,000 lines of a code in a language, whether it is a hardware description language or it is a programming language. At that time, the comments help you to debug the code with your human eye. Obviously, you will need a debugger or a printf command to debug the actual or final problem. However, initial idea of the debugging, that is helped through the comments in any language. So that is why the comments are very important, and in any language you must first learn what are the comments. In Verilog, there are three forms of comments. This is a multi-line comment. Here you will also find similarity with the C or C++. The double slash is a single line comment. Anything after this double slash is a comment, and within the slash asterisk and whatever lines are there, and then we end up with the star then slash. This slash star and star slash, whatever contain, even we have a enter pressed or you have a inline character in between, that is a multi-line comment in Verilog, and double slash is a single line comment. Also we have a inline comment, that is not only by the double slash, but that can be placed once a statement has ended with the semicolon. So these are the three forms of a comment that can exist inside of Verilog code. So I have given you the first option. When you start coding, you can put your comments for your own understanding, or you are in a company, your comments will help your colleague to understand the code for a debug. With that note, let's move on to the next slide. Typical module example. Here in this slide, we will give a real-time example of a Verilog module for a digital circuit, and I will point out each and every section, whatever it is called. So this is a kind of visual tour. In next episode, we will simulate these codes in actual simulator. This is the comment. It is your first Verilog program. This is called the heading. Generally, any code has a heading, what the code is, who is the author, and what the section or the division of the VLSI company they are writing the code. All these things will go in the header. So here you can have a multi-line comment or multiple single line comments. Next comes the module, then Not-Gete, and we have two ports, that is in and out. So this is the fashion the module is written. Here the module is color in green because this is a Verilog reserved keyword. The Not-Gete is not_gate is written by us, and the in and out is written by us. This is the module declaration. Next, we have input, that is the nature of the input. Here the input, the keyword is in green and it is a reserved keyword for Verilog. Similarly, the nature of the output is output, and it is also a reserved keyword of the Verilog. Together, these two are port declaration. So next we go for assign statement. So this is assign is also reserved keyword and it is used for any assignment. That means here the output is the inverse of the input. So this is a assignment, and this block is called the functionality declaration. So here with the single here we have defined, and in other cases we have multiple such assignments for the functionality declaration. Next, we have the end module. Here I have used an inline comment of not_gate. This is a typical practice in VLSI because there will be multiple end module commands and you cannot have a method to know what module is ending. So this way, once you code, it is good practice that you keep a comment, inline comment at the end of the end module of whichever module is ending. So this way, even you have nested modules, then in that case, you might not get lost in a very long code. This is called the module closer. So here are the very short and simple Verilog code of a Not-Gete, and we learned here what is a heading, what is a module declaration, what is a port declaration, what is a functionality declaration, and what is a module closure. In next episode, we will simulate in actual Verilog simulator and we'll go through the output. test bench module example. Now, this code, whatever module we have written, we have to test it whether whatever the intended functionality, that means it's a Not-Gete, right? So that not operation is happening properly. For that, we also have to write a test bench. Now, test bench is nothing but another module written in Verilog. So this particular module will instantiate the Not-Gete and add some test vectors that will help to verify the functionality of the Not-Gete. Here in this particular slide only. In other cases, any test bench will help to verify the functionality of the instantiated module. Here, the first line is a comment, inline comment, test bench. Here it is simple. In actual case, this will be a couple of single line comments or a multi-line comment. Here we define the module with the module keyword, and this is test. Generally, this is a convention that we add a test word so that we can identify later. So this is a test bench module and not a digital gate module. Rather than it is a test module. So here goes our module declaration. Next, we have reg PLK and where out check. Now, these reg and where I will discuss about these types in later episode. Let us learn what are these. So these are data type declaration. That means in Verilog, we can have multiple type of warings and they could be registers, that is reg, or simple where, that is out check. I will come to the details later. Initial begin. This is a initial block. We are starting the block, and after this line, whatever we write comes under the initial block. So the begin keywords means we are beginning the initial block, and we write here $dump file abc1.vcd. VCD is value change dump. In the hands-on episode, I will show you how to open the VCD file in a viewer. Then $dump vars. That means in this file, this particular system command dump file opens a file with the name abc1 and the extension VCD, and in that file all the changing variables, that is with respect to time, including the time variable, get dumped by the next system command dump vars. Then we have a kind of printf statement, $display, checking output of a Not-Gete. So this is a simple printf kind of thing that execute only once. And next we have a recursive printf, that means monitor. Here we use the kind of %d, %b, %b. Then we mention the $times CLK and outcheck. So these are very similar to your C printf command. And the difference is here the $monitor keep on monitoring whenever any of these variable changes, it takes a dump. So this $monitor will give a printout in the screen, and the dump word will go to the dump file. So these are two ways of, one is on the go, you will see the output, and another one is the archiving. So the same data will be printed here in the screen and it will go to the VCD file as a permanent stored result. PLK is equal to 1. We are initiating CLK with 1, that is logic 1. And at time equal to 50, we finish our simulation. So here you can understand the hash 50 is nothing but 50 time unit, and the $finish keyword, which is a reserved keyword, finishes the simulation at this point. In many simulators, the finish can be defined by the simulator. However, in general Verilog code, we already have these directives to finish a simulation. All these $thing, these are reserved system commands which are for controlling a simulation, which are not for a description of a Verilog block, rather for a simulation control commands. All these contribute to the timing block. That means it controls the timing, behavior, output, whatever it is there. Next, we end the initial block with the end command. So this is how the block starts, the initial block starts and ends with the end command. So in this particular slide, we have learned the module declaration of our test bench with respect to our already written module, data type declaration, initial block, timing block. We have not finished yet. In the next slide, we will have the rest of this test module. So let's move on to the next slide. The test bench module example. Always begin. Here, both always and the begin are two reserved keywords. As you know already from the previous slide, the begin means we are beginning any block, and the first line is #5 CLK is equal to inverse of CLK. That means at each and every 5 time units, the clock value will get inverse. That means the clock will toggle. Here we have the end block. So this ends the always block. So the begin is started by the begin keyword and end is mentioned by the end keyword. So this is always block. So this different of the initial and always block is that the initial block is written there, the initiations are done there, and it executes for once only. However, for the $monitor, since it's a system command, it is designed in that way, we just only need to initiate it. The rest of the system, that means the simulator, will take care. For rest of the assignments which need to perform always, which are defined by us and that might be a part of the functionality, are put into the always block. So here you can see the initial and the always block are both are respect to the time. So you can see the stark difference between a C code and a Verilog code. That means here time is very important, and see the time was found nowhere. Next, here this comes the most important part of a test bench. Here we instantiate a Not-Gete. So first we write the name, and we write the instance name is MUT. Here MUT means module under test, and we put the two varings here, the CLK and the out check. In next episode when I simulate, I will tell you what is what and why we are keeping them. However, for now you can just understand that we connected the CLK and out check, which we have defined with range and wire. We connected those things with the actual module, so but as an instance, not as a library. So this is an instance. The MUT is an instance of the Not-Gete. You can name MUT as you like. You can name it instance of Not-Gete or like that, or I Not-Gete, anything like that. Here I have kept it as a generic name, MUT, that is module under test, because this is a test bench. Next, here this is the module instance, and here we use the end module. Here I have missed out the test bench name to be mentioned here, which is a good practice. So with that we end the modules. That means it is the module closure. So in the last two slides, means this slide and the previous slide, we have learned about a test bench module. What are the different parts and subparts, different parts and subparts of a test module. So we are done here. Let's move on to the next slide. Now, I have given the explicit example of both module declaration and test module declaration. Now, I will summarize the entire thing here in this particular slide, and this slide will act as a bird's eye view of any typical Verilog module, what you are expecting to write inside a Verilog module. So here goes our details, and in the right hand side we will have a figure. So first we have the module, then module name. It is mostly philosophically written. It is not the syntactically written. So don't think this is a Verilog code. This is a philosophical bird's eye view. That's why I have kept it. And here we have a pictorial representation of any Verilog module. So let me bring my mouse. Here the entire chip is the module, and here we have subparts or components like this one, this one, this one, this one. And we also have ports which we have declared and connected. And these connections will be either of wire or reg type. We will discuss in further later. We will have the power connection, VDD and ground. So here these functionalities or these blocks, these modules are defined by statements. So you have already seen, now you can correlate with the picture of already discussed module, and you can understand, right? This is the kind of representation of a IC, right? Whenever we put into a breadboard, we can add different voltages to test them out, so to the in and out. So this breadboard where we are putting this chip, this module, acts as a test bench in the Verilog. So we replace the breadboard testing facility with the test module in the Verilog. Here comes our declarations. These are expected to find. You have already come across the example, so you will be easily correlating the things. So these are, I am again emphasizing, these are philosophical presentation. This is not a Verilog code. So whatever comes in under declarations are port declaration, input, output, in out, etc. will be there. Data type declaration, range, where, param, etc. will be there. Task and function declaration. We will later in respective episodes we will talk about function and task, and we will also differentiate between task and function. Now the end got color green, but this is not a Verilog keyword, at least here, so don't get confused. Statements are initial block, always block, module instantiation, gate instantiation, UDP instantiation, UDP is user defined protocol, and etc. Continuous assignments, end module. So this is a bird's eye view what you can expect. So whenever you start writing any Verilog code, you can keep a note of this slide with you, that in sequence what you have to write, and you can go back and forth in your book or in this tutorial to go to the respective chapter of that particular command or the code, whatever you are writing. Command, I mean the system command, or code means I write the Verilog syntaxes. This you can keep a handy. This I think I have explained to you with the picture and the text. So let's move on to the next slide. Summary. Now let us summarize whatever we have found in today's episode and also add some more values. Verilog is a hardware description language HDL used to model electronic circuits. It is commonly used in the design and verification of digital circuit at the RTL of abstraction. So here in this slide, we are designed a module using Not-Gete and we have used a test module for verification. However, in VLSI, verification is a vast term and it is a different subject altogether. So I'll not talk about VLSI verification rather than a Verilog verification here. In 2009, the Verilog standard was merged into the System Verilog standard, and since then the Verilog is officially the subset of System Verilog language. Several simulators are there to simulate the circuits written in Verilog. Now, here is the catch. Here I am mentioning the paid and free simulators here. Although in this series I will be using a free or open source or a student version of a paid software. So here are the list of the paid simulators that are used in the actual industry in VLSI. First one is the Incisive Enterprise Simulator. It is from Cadence. Then the VCS. It is from Synopsys. Next we have Model Sim and Questa. It comes from the Mentor Siemens company. Next is the IAC simulator, it from Xilinx. Next we have Quartus 2, which is a Altera and Intel simulator. I think Altera is now the part of Intel, and X-Sim is a part of Vivado, which is from Xilinx. So these are all paid softwares used in the industry for industrial Verilog simulation. Now we have the couple of names of the free and open source Verilog simulator that you can start using right now, and in the playlist you will find the installation video of this and installation and usage. So one is the GPL Saver, another one, this is Icarus Verilog. Icarus is very popular because it simulates both Verilog and System Verilog. Next we have a TK-Gate. This is a GUI based HDL simulator, and we have Verilator. So these are couple of names of the paid and free open source Verilog simulator. In next week we will do the simulation of the already shown Verilog module and the test module. So let us keep it secret. Let's wait for the next episode. And I think we are done with the summary. Hey folks, during one of the live session, I got a request from a viewer to make an installation video of Xilinx Vivado. Today, we will download, install and obtain license to run Xilinx Vivado in Ubuntu Linux and Windows 10 environments. During the download and install, whatever challenges have been faced are kept intact in this video. This makes today's video an uncut version of the problems and solution faced during the download and install process. You can use the chapters in case you want to skip a section or jump across sections or go forward or backward as you want. The installation of Vivado in either Ubuntu Linux or Windows 10 took approximately 3 hours of clock time in each. Hence, we have edited the video in fast forward time-lapse manner for better viewing experience for the corresponding sections. So, without any further delay, let's begin today's episode. Welcome back guys. Right now, we will be installing the Xilinx Vivado. Before that, we have to download it from the Xilinx website. So, let us go to the Xilinx website. So, as I search in Google, you can see here that here the Xilinx website is opened, and we here go to the Xilinx website. So here you can see Vivado ML 2022.1 is available now. So here you can see the icons. So this is a login icon. So we have to go for login or register. I have already registered in the site using my Tech Simplified official email. So let me go there and log in with that. In your case, you have to create a login first, and then you have to use that login ID and password to enter into this particular Xilinx website for download. So here you can see there is been autofill option here, and here I am using the official email of Tech Simplified TV. So let me sign in. In case you have no ID created, you have to go to the create account option, and then you have to use your credentials to create a login, and then you have to come back again for the login process. Let me log in here. So here you can see I have used my name here while registering here. And you can see here there are different sections. Well, the section where we are looking for the download, let us move into that particular section. So here you can see the product support. If you look carefully, if you come down here, you will find the downloads. And also there is a documentation. So this will give the manuals. So first let us go to the downloads. So here in this download section, you can see there are several Xilinx softwares as well as packages are there which you can download. VT is here, Vivado is here, Beta Linux is here, and device models is here. So there are a lot of softwares. We will install the latest version of Vivado. So we have to use a proper download link, and obviously I will expect that it will catch up in our download manager. I am using here pre-download manager. If I go down here, you can see that the product Vivado ML 2022.1 is available for download. If I go down right, you can see that the first one is Windows self-extracting. The next one is the Linux self-extracting web installer. First, we will download both of them. Then we'll one by one install in the Linux as well as in the Windows. So let me grab the Windows self-extracting archive first. And let me open this in a new tab. Okay, so let me quickly fill my credentials here. Here I have picked other. For your case, you can pick student. It has now activated the download manager. So I will use this to in the download folder. Xilinx Unified Installer is downloading. So the download has started, as you can see here. The download has finished. Now let me go back here. This is Windows self-extracting. Now let me download the Linux self-extracting web installer. My download manager is ready. So this is here downloading. Download has started here. Close it and we are done. Let me go to the site again. Yeah, let me log in or rest. Okay, yeah, okay. So let me go to the download page. So here we have downloaded the Windows self-extracting web installer and we have downloaded the Linux self-extracting web installer. So we are done with this particular site for now. Let me close the page. So folks, we are back here in the downloads folder. And right now we are in the Linux partition. So we will have to use the Linux binary for installation. So let me open a terminal here. Let me do ls, and this is our binary, right? So I am making it executable. Open the terminal again. ls and run the binary as sudo. First I have given the sudo command and then I have used the binary, which the permission I have just changed. So you can see it, the color has changed and it has the right now the 777 permission, and let me execute it. So let us see what happens. I have given my password here and here the installation has started. The unified Xilinx installer has opened So here you can see Ubuntu Linux. Here is the supported operating systems for 2022.1. Here the list of Ubuntu's here, and I'm skipping up above all of this because I am not using this. I am using the Ubuntu Linux. Here I can see these are the versions. Okay, so I'm using LTS. I think this will go in a correct fashion. So here I have to enter my Xilinx ID and password. So I'm connected to the internet, as you know already, because we have downloaded from the internet, and once I move into the next step, the things will download automatically. Let me click on the next button. So here there are a lot of things you can install here through this installer. Today we are focusing on the Vivado. So we will select the Vivado here, and I will leave the rest of the things because we are not focusing on them. We are focusing only on Vivado here. And let me press next. So here are two versions, ML Standard and ML Enterprise. Let me read out. Vivado ML Standard Edition is the no-cost device-limited version of Vivado ML Enterprise. Users can add Vitis model compressor, which is a Xilinx toolbox for MATLAB and Simulink for AI engineers and programmer logic. If you have been using Xilinx system generator DSP, you can continue development using Vitis model compressor. Now, Vivado ML Enterprise included the full component of the VLSI Vivado Design Suite tool for design, including C-based design with Vitis HLS, implementation, verification, and device programming. Complete device support, cable drivers, and documentation navigator are also included. Users can add Vitis model compressor, which is a Xilinx toolbox for MATLAB and Simulink, designed for AI engineers and programmable logic. If you've been using the Xilinx system generator for DSP, you can continue using development using Vitis model compressor. So let me go for it is a no-cost edition, the standard one. What I infer from the two text here, that this is a no-cost version. So let me go for this one, and I'll suggest that you also go for the standard one. So here you can see what to install. You can pick up what to install and what not to. By default, everything is selected here. So here I think everything is selected only, and the download size will be 51 GB, and disk space required is this much, 51 GB. No, I think there will be a problem in the disk space here, since it is 155 GB physical disk space will be required for the installation. So if I go to the terminal right here, I can see pf-h is 97 GB free. So I have to free up some space, and then I have to come back again. So for now, let me pause here. Let me do some cleanup, and I will come back. Hey guys, I have cleaned up some space. Let me now check how much disk space is available. So folks, you can see here 183 GB is free. So let us proceed with the install process. For that, let me execute the binary. So this is the Linux binary. Let me run it. It is asking for the password. Let me give it. Okay, so the installation has started. So let me proceed here. Is asking for the ID and password which I have created in the Xilinx website. Let me put those data. So I have given the data here to download and install now. So this is a live installation process, and this is a different installation process where you can download the image from where you can install it afterwards. In case you are from any company, I think there you might use this, because the installer will download an image containing all devices and tool options for later installation. Use the option if you wish to install a full image on a network drive or allow different users maximum flexibility while installing. So here the full product image you can download. Here we will go for the live installation, since this is a single machine and it is not a network machine. And here we will proceed with the download and install now option. So here you can see different softwares are there which you can install, and this particular session we are installing Vivado. So I am selecting Vivado here. As I have already mentioned, the Vivado ML Enterprise is a paid version, and this is the no cost version. Okay, and go with it, and in case you are a student, you can go for this. We will proceed through the standard option. So here is the selection page, and you can see the download size will be 51.68 GB. So this is the installer package which will be automatically downloaded first, and later during the actual installation, the post download part, it will consume 155 GB. So this much hard disk space be there. For that we have done the cleanup here in this particular machine. Let me check if I uncheck these options, what happened. So you can see as I uncheck this, so this thing is going down. So the disk space, that is a post installation, will require less area. So here I think Vivado will install the Vivado, and uncheck, let me uncheck here. PTS model we are not installing here. It is the toolbox for MATLAB and Simulink. In case you have to install it, you can install by checking this option. So for me now, let me uncheck the devices. If I reduce, it goes to 134. So almost 10 GB it reduces. Let me uncheck it so that I save some space here during the installation, and let me install only the Vivado design suite. And this is for the FPGA devices. So let me uncheck all the option, and we are proceeding. It says at least one device must be selected. Okay, or install devices for SOM starter kit. Next. Okay. So here we come for the Xilinx INC end user license agreement for Vivado. Agree. For DocNav, agree. Third party software, agree. This is also agree. And let me proceed. So this gives install options tools/Xilinx. Here this will install, and install locations will be this, and tools Xilinx DocNav, and this will be the install area. So download size is this much, and space available is, final disk usage will be 77 GB, and disk is required is this much, and we have space available 200 GB. So let us proceed with that location. In case you have to change a location, you can go ahead here and pick a particular folder where you have to install. So maybe you have some other space where you keep your softwares in Linux. In that case, you will go to that. Otherwise, you can leave this unchanged. It says tools/Xilinx does not exist. You want to create it? Yes. So now we come to the installation summary. It says Vivado ML standard, it will be installed. Devices, it will install the VIA SOMs and starter kits. Design tool, so Vivado design suite will be installed. DocNav will be installed. This is the installation location. This is the download location where all the temporary download files will be downloaded. So this is a live installation. That's why it gives the location where it will be downloaded. And here it says the final disk usage is 77.76 GB. We will proceed here. The install option. Let me enlarge it. You can see here I am connected through the LAN here. So it's a wired connection. I have an optical fiber connection. So here you can see almost 5 Mbps speed is there, and it is moving forward with the installation. This is another point for you to remember, that for this live installation, right, you have to have a good bandwidth broadband so that you can download it. Here it is showing 2 hours and 50 minutes. Let me see how long it goes. So folks, you can see that the installation has completed successfully. Here you can see, and here is the final message. It is coming. Select a notification, see details in the description section, take appropriate action. So here it is the Xilinx Information Center, right? Here this thing you can use for the uninstallation process. Okay. So, and here Vivado ML manage licenses will be done using this particular button. So once we do this, we can enter the license details. So let me close it. And since we have done successfully the installation, Let me click here. Okay. You can see in Linux we have installed the Xilinx Vivado, and here is completed. That's all here. Okay, folks, we're in the Windows partition, and we are going to call the Windows installer binary, installer exe file. Here I am clicking the exe file, the right click or the right mouse button, and in the option run as administrator. Xilinx unified install started ported operating information in here. As I have said, right, that there could be option at one, download the image, and later it handle on the machine. So we will choose download and live right now. We will proceed further. Here you can see all the list is coming, whatever is unified install. Here we are Vivado. Next, as I have said that for Office multiple are working, here you can install the inter, and here see we are for print. Call it learning purpose. Here you will choose Vivado standard edition. Proceed here. I says 1. Here we passing on the Vivado suite board panel. At time after and all that time include all the parts here. 1. So folks, I have done some clearance on the files or disk. Let me start the process. I am running the installer exe as administrator. The Xilinx unified installer has been. Here you can see the mess for the win. Proceed. As I have mentioned, this option or where company multiple and here we will with the live installation for step for running the. Here there are a lot of softwares and Vivado. As I have mentioned earlier that Vivado is a student, a learner. At time Vivado no cost. All these are hey folks, are back in the installation, and we have some of the disks for the Vivado install. Start by right clicking the installer exe binary, and here we choose one as advisable for installing large heap softwares directly RJ45 in a directly router at Ethernet cable, more speed and you can faster. Otherwise interruption and break. So here we are back with the installer. Here you can per second. And let me. I have mentioned earlier the download option for the and for individual user or a learner, that person can call live link and install Vivado. For a learner or a student, you have to pick standard edition, first edition. Proceed. And you can install. Hey folks, we are done with the installation parts. Now in this section, we are going for the download of the license from the Xilinx website. Here we type So in Google, we have typed the Xilinx product licensing, and here you can see the first one. Let me open it. So in this page, I make sure that I am logged in. So I'm using my credential to log in. So let me go back and again open this one page. Okay. Now I am logged in. Since we are using a learning edition, so we have to go for the pre-evaluation product license. Where it says pre-evaluation product license. After completing the installation of Vivado ISE design suite, the Xilinx license configuration manager XCLM will start automatically and guide you through the licensing process. You may also go directly to the Xilinx product licensing site to obtain license for free or evaluation products. You decide to skip this step during the product installation. So during the product installation, we have not gone to the licensing part. So here we will go to the licensing site. So here my credentials have been entered again, and in your case you have to enter your credentials once again and proceed with the next button. So here it is asking to accept the cookies. So this is a basic policy for any website to acknowledge the end user to accept the cookies. So we are accepting all the cookies. So here you can see there is a list of licensings are mentioned here. So here you can see the Vivado Design Suite HL Webpack 2015 and earlier license and status current, and there is no end date. So we will go for this one. This will be the license that you need to download. So here we click on generate node lock license. So we will leave everything as is here and proceed with next. And here also we proceed with next. So here you can see that the license is here. So I checked my inbox here and I can see that the license has been delivered to my inbox. So here is a small instruction for node locked licenses, right? We have chosen this option. Save the attached license file to your desktop, then run Vivado License Manager. In Windows, run Manage Xilinx Licenses underneath your version. In Linux, type VLM in a command line window. Select the load license and then click on copy license button. Browse the downloaded license and click open. So let me save this one. So I had created a folder where I have kept the installations file. So in the same folder, I am saving the VIVADO-INSTALL license. So this is the instruction you can see, and we will follow these instructions. Right now I am in the Linux environment. I will launch the terminal, and here you can see it has said to launch the VLM. I type VLM and it says command not found. Let me run a find command. Okay, so here you can see I have searched for the VLM binary as it is mentioned here. You have to type VLM in a command line window. Now, since this is a different path than usual installation path, that is tools/Xilinx, where we have installed our Xilinx products. So there we have to go and we have to find where this VLM binary is there. So I have used the find command of the Linux, and here I have given the case insensitive search to find out the VLM binary. So let me launch this one. So you can see the Vivado license manager has opened here. So there is an option copy license. Okay. So here we will browse through, and here it says that click the copy license button, copy a certificate based license.lic file into the $home.xilinx directory. Xilinx application automatically detect the valid note lock license LIC reading in this directory. So let us copy the license. Just coming here, let me save a copy into the downloads folder also for easy access. And let me go to the downloads folder, and here you can see the xilinx.lic that we got as an attachment. Let me click and open. Now it says the license installation was successful. We click OK. Here I think we are done with the licensing part. Here there is some additional information about the licensing environment variable. In case it is needed, we can configure here. And here we can view the license status. So you can see that here we have the Webpack license, or the Vivado is there, and we can use this license, and it is version limit is up to 2023.05. The version limit is up to 2023.05. So here we are using 2022.1, and this license can be used up to this version, that is 2023.05. And view the license status. Here the license is installed, and let me close this license manager. So folks, we are in the Windows operating system, and let me navigate for the Xilinx menu. Here you can see the Xilinx design, and here you can see Xilinx subproducts are in the menu. So you will, for the license installation, open the PLM manage license out here. The license obtain license, code license. There are three license right where we have downloaded license already. Here we go for the license. Here I have saved the Xilinx SE file from Xilinx. Is the license first, and now we go back to the license status. Here you can license have to the versions, and are done here. Hey folks, when we are in the Linux operating system, here I open the terminal here, and let me search for the Vivado binary. So we know all the Xilinx tools and subtools are installed inside this path. So we will use the find command in Linux to find the exact location of the Vivado binary here. And we also give a wildcard in case there is something extension of the Vivado. is not a good choice. It is finding out multiple things. So let me clear the screen and type again only Vivado. So here I am using the command find and using the path inside which I will find the Vivado binary. So I think we have found it in the first go. So here you can see here is one Vivado and here is one Vivado. Okay, and this is object. So .o. I think this is not one. Okay, so let me launch this one first. It says start GUI. So you can see the splash screen has appeared in the desktop. And we have our dialings interface for Vivado launched inside the Linux operating system. So here we go to see the Vivado about, and here we can see we have Vivado 2022.1. Okay, so that's all, folks. Next, we have Windows launch Vivado now. So you can I double click Vivado splash screen has that. Hello. So done with this particular part. Hey guys, welcome back to the computer screen. Today we are installing two most used softwares for a VLSI beginner. So here I have opened the URL in browser. Today I will install these two. First one is Icarus Verilog. It is a Verilog simulator. It's a binary, and GTK-Wave is a GUI. So here you can see the GUI looks like this. Now these two are used hand in hand. Once your Verilog code is simulated, you can dump a waveform file, that is VCD file, and you can view it with the GTK-Wave. So this is a kind of splash screen that comes once you have launched the GTK-Wave. So here you can see the Icarus Verilog. It's a Verilog simulator. I will provide all these links in the video description. So from there you can pick it up. Just now, let me show you a few things. It is also available in the GitHub. From there you can download. Today I will install these two in my Ubuntu system, and those are basically command line. The instruction will be there in the video description. So instead of searching here and there, you can directly go to the video description and from there you can find it. And here you can see that this particular Verilog simulator is a part of the Geany IDE, that is GEDA, and Icarus Verilog is the part of it. And GTK-Wave, it is very essential once after you run the Verilog code. Another link I will also provide in the video description. This is the wiki page where GTK-Wave details are there, and this is for the Icarus Verilog. So here you can see the Icarus Verilog. There is an installation guide, user guide, developer guide, glossary, everything is here. So I'll also provide this for your easy use and can use it like a manual and so. And GTK-Wave, this also I'll provide you so that you can go there and dig up by your own. I am done showing in the browser, so let's now jump into the command line. I have captured the install instruction here in a text file. All this data will be available to you in the video description. Now, so let me now add this particular repository first. So I add this. I have to give the sudo password. I've given the sudo password. I have to enter. It started processing. One essential thing I'll tell you here, I have connected my machine to internet right now. To install like this, have to have the internet connection with you. So the first step is done. Let me now do the second step. The second step is also done. Now I will install two binaries. First, the Icarus Verilog, that is binary name is iVerilog. When you are installing and when you are using, you have to use this binary. So here you can see it started installing. I have given the instruction here. So I think this is done. Now I will give the instruction for the GTK-Wave. Now the GTK is getting installed. This is also done. So the installation of the Icarus Verilog, that is iVerilog binary, and GTK-Wave are done now. In the video description, I will also provide the install links or the URLs where you can get the Windows binaries. Into a ls here, I have kept a Verilog file here. Let me open it with the EVM. So here you can see there is a D flip-flop circuit here, and here is a small test module, and here you can see I have done dumping of the VCD file. I'll not go in the architecture and all of this example. I'll just use this case to demonstrate how the Icarus Verilog works and in and how the GTK-Wave is used. I am doing the ls. You can see there are only two files here right now. One is the instruction.txt, which we have the details of the install instruction, and the second one is the mydiff.v. I will run the Icarus Verilog. I type iVerilog, then I give the Verilog file name. Once I execute this, I have executed this and there is no syntax error like that, and you can see once I do the ls, here a a.out is created. The Verilog code is compiled by the Icarus Verilog, and by default it creates a a.out and it's an executable file. So we have to do the execution of it, and you can see I have given the name a.out. Once I execute, I have given a display statement here inside the paste module, and from there you can see it has been printed out. Now let me clear the screen, and again I do the ls. You can see one more file has been created. This is the VCD file. VCD means value change dump. Now how I open this file? I will use GTK-Wave. Then I give the ampersand sign. Is basically used just to disjoin the window from the terminal. Otherwise the terminal will be kept occupied. So once I type, you can see the splash screen has come. Now the GTK-Wave has been opened. Let me maximize it. And here at the left, you can see here once I click, this data structure is there. Now if I click here, you can see these are coming, which are basically the data from the Verilog file. Now if I click, you can see there is a clock signal. It is going periodically. Then we have the D pin, we have cube, we have the reset one. Here you can see that the entire timing diagram as per the test vectors is shown here. So this was the installation episode, and I have covered the basics. That means how to install and how to use the basic things. So that's all, folks. Hey guys, welcome back to the computer screen. Today we are installing one very useful and lightweight integrated development environment. As you can see here, we are on the URL geany.org. This is our IDE, integrated development environment. That means you can code here and at the same time you can run the code in the same window. So you don't have to switch in between a text editor and the command terminal to do the coding and running the code. The beauty of Geany is that it is free of cost. It is a free and open source software, and it is very much lightweight. That means it do not eats up your resources while running. Here you can see it is written Geany the lightweight IDE. And you can see it is compatible to multiple OSs like Linux, Windows and Mac OS. So in any of the OS you can download it. So here in the top row you can see that it is Geany, the base, then about, then download. If you click it, you will go to the download page. Alternatively, you can click here and go to the download page. So here you can see the source code is also here, the Windows binary is there, Mac OS is there, and in Linux, other than the Ubuntu or Debian, you can go ahead and use the source code to build it. For Ubuntu today, I will show you how you can install it from the command line. If you go here, you can see the manual, and here there is a wiki. So if I go to the manual, download the manual here in HTML format as well as in the text format. If you go to the wiki, you will get a lot of articles here. How to do things are here, and you can find out a lot of tips and tricks here about using the Geany. Now let me go back and go to the main page. So this is the general interface of Geany, and color can be switched. It can have multiple themes. So that's why these are there. And here, as you can see, it is very much fast and small, and it has a community support. That means you can have all the bugs and related info from there. And here you can see that multiple plugins are there, like here VCS plugin, and here if you go, you can find that different plugins. So here you can see different plugins are available. Let me go back again to the home page. You can see here it is supporting multiple type of programming language. That means once you install Geany, in the same window you can play with multiple codes. And if you want to go to this, let me go ahead and open in a tab. So there are a lot of available themes you can download, and you can switch to your desired look and feel for the Geany theme. Today I'll just showing you this thing. I will today only install the basic thing so that you can go ahead and start using the Geany. So without any further delay, let me go to the terminal. So here I will type sudo apt-get you must spell this correct. Geany is G-E-A-N-Y. So I have written the command here, sudo apt-get install Geany, and I'll hit enter. I am connected to the internet right now, and it is communicating with the repositories to fetch the required files. So here you can see that it has installed. So here I was logged in with the sudo password, so it did not ask, and it go ahead and install the package right away. Let me clear the screen. I'll invoke Geany. But now we have come to the interface. Here you can see file. From here you can save or save as the file. The most common operation, and you can find and replace operations. You can do it from here. Replace is here. You can change the view from here. You can multiple document related stuffs here. In case of language like C or programming language or C++, you can do the build here. This interface is very useful. First left here you will see the files, which files we are saving and writing. Here is the editor window. Here you will see the editing. If you go down, right, there are a lot of other things are here, like status. Here things will be messages, and here is the beauty. Once you are working in any text editor which gives you a syntax highlighting, the trouble with that is that you have to continuously switch between your text editor and the terminal. Here in Geany you don't have to do that. If you go down below here the terminal is available to you. So this is basically a shell. If I type echo $shell, you can see is the actual Linux shell, and it is not an emulated shell. It is actual Linux shell, similar to the terminal here. It's the same thing. Hey guys, in last episode we have discussed about the first program in Verilog. In this episode we are going to demonstrate the Verilog code simulation in two different simulators. One is Vivado, another one is iVerilog. Vivado installation and iVerilog installation I have shown already in the videos. You can find the links in the description. So here you can see in the screen there are two files. One is the hello.v. So let me open it. Here you can see the hello.v is you can think that is the first program, the hello world program here in your Verilog. So how to write? So we have a module main, here we write. Then we use the initial and begin to begin the initial block, and end is for the initial, right? And here we use the $display, which is very similar to the printf, and we write here hello world. Here, since we are simulating with respect to time, which is a very striking difference with the C language, we use the $finish to finish the timeline wise simulation, that is the transient simulation. So as soon as the hello world is displayed on the screen, we use the $finish the simulation, and here is the end to end the initial block, and end module to end the main module here. Okay, so this is the simple code for hello world program in Verilog. Let me close it and let me show you the another code. This code I have demonstrated in explicit detail in the last episode, that is the episode 1 of Verilog for beginners. So the module here is the Not-Gete, which we have written. There are two ports, so in and out. We define the direction input and the output here, and we have assigned that output is the toggled version of input. That is, this negation sign is there, and here we end module, and this is the inline comment for the Not-Gete, so that you can understand this Not-Gete is finishing here. And we have written the test bench here. You can see here the test bench, you can see that the test bench begins here. Okay, and we have the clock and the out check. Inside we have clock, and this is for checking the output, and here we have the initial block starting, and here the initial block ends, and in between we have dump file. So this will be needed when we'll be using the GTK-Wave, which will be used along with the iVerilog, not with the Vivado. Here the dump vars. This dumps all the variables in the dump file. So here we open the dump file, and with this command we dump all the data, all the simulation data into the VCD file, that is the value change dump file. And here in the screen we use the two printf kind of command. One, the display is the static one, which displays like a printf, it operates once only, and the $monitor is a continuous monitor. It keeps on monitoring if one of the values of these three values, if any one of them changes, right, those will be displayed on the screen. So here we have initiated the clock with 1, and at 50 time step we do the finish, and here is the end. And here you can see there is a always block. At every 5 time unit the clock is toggling here, and here we have instantiated the Not-Gete. So this module is instantiated here in the test bench. Now there is a very simplicity here in this entire file, that Verilog file, that I have kept the module here and the test bench here. So in the same file, it may happen that you can rename, or you can keep these two codes, the first code in a one file and another in the another file, and use them together. But since you are a beginner, I have, for simplicity, I have kept both inside a single file to avoid complexity, and you can easily grab them. So this code you can directly execute in any of the Verilog simulator. So I have explained again these two codes. Another thing I will say that these codes I will provide the link in the description so that you can directly download them. So there will be a GitHub download link which you can access in the description of this video. And you can see here that one more thing I would like to say here, the input is in, which is connected to the CLK in the test bench, and the output is out, which is connected with the out check. So in one simulator you may see the in and out, and in another simulator you may see the CLK and out check, but both means the same. So I'll show you. So two of the code is done. So let me close it. Now let me open a terminal here. First we will simulate with the iVerilog. Now we can simulate the iVerilog in two different manners. Okay, one is directly from the terminal, another one is through the IDE called Geany. So I'll show you both. So let me do a ls here. You know, we have opened the terminal from this particular directory itself. So there are two files, hello.v and the not with testbench.v. Now let me do a switch. So iVerilog is installed there, and it is from this path. So the Windows users, you will not get the iVerilog. This is in Linux only. So in Windows you can use the Vivado only. So here let me do the show you the man page and iVerilog. So here you can see that iVerilog, it comes with couple of switches. So mostly the things that we will handle is that with the output at the beginning, right? Generally, when we execute, it creates a a.out file, which is very similar. If you have done C programming in Linux with the GNU compiler, you might see there is also a a.out file. So here, once we execute it, right, so a.out file is created, and then we have to execute the a.out to get the output. So this is a two-step process. I'll show you. So let me close the manual. So here the hello.v. So I type iVerilog and then I type hello.v. Okay, and I give a -o. So instead of a.out, we will get hello, hello. Hello. This way you can actually identify multiple output files, which is the object dump of the simulator, right? Otherwise, every a.out will overwrite the previous a.out for different Verilog files. So I give a hello. So here, let me do a ls again. Now here you can see there is a hello. This is an object dump which is done by the iVerilog, this binary. And here you can see three files here. Let me execute the hello. You can see once I have executed on screen, the hello world is printed, and if I do the ls, you can see, okay, here we have not given any VCD file, so it has not came. So here you can see the hello object file. Once we execute it, then it prints the hello world. So this is the basic hello world with the iVerilog. So here I have no need of using the GTK-Wave because no VCD file is here. So let me move on to the next file for the not with test bench. So let me run iVerilog. Not with testbench.v, and then we give the output file -o as not test. So this will be the output dump created by the iVerilog binary. So once we execute it, let me do a ls. You can see here the not test, this object file is created. Let me execute this object dump created by Verilog, and here once I execute, you can see VCD info dump file abc1.vcd. You can see the VCD info dump file VCD is opened for output, and here the print commands have executed. This is from the monitor command. So let me show you by opening the testbench v.file. So here this particular line is printing this line. Okay, these two are creating this line and the dump file, and this series of printouts are coming from the $monitor command. So here the first is the time, because here in Verilog we have a time-wise simulation, that is a transient simulation, and the time variable we have to print, and this is a predefined and it's a system defined. So you can see it's $time. We have not defined it, it's already there inside the Verilog, and here is the clock and the out check which we have defined. So you can see here that first this is the time and this is the clock and this is the out check. So this is the in and the out. So you can see it is toggling, right? 1001 1001, and this way it is keeping on toggling, right? We have tested that our written Not-Gete module is operating as per the not logic with this one. Now let me do a ls again. Now here you can see that there is a VCD file. What we have to do with the VCD file? How we can open the VCD file? For that we have to use a binary called GTK-Wave. Let me clear the screen, do the ls, and let me find the GTK-Wave. So here you can see that the GTK here user bin GTK-Wave. We will launch this one. Let me use GTK-Wave and do the %, so that it do not block the terminal after it is launched. So here, as soon as I have given, this is GTK-Wave and this is the version GTK-Wave Analyzer. So this is also a free tool like Verilog, and it doesn't cost you a license. However, you have to use it in the Linux environment. So here you can see there are several menus: file, edit, search, time, markers, view. We are not going in very much detail of all this. Instead, we will go very simple manner. Let me file, then open new tab. Here, go to desktop, find and here we go to the test. So here you can see the abc1.vcd file. So here type of the files is star and VCD file it can open. So let me open it, and here we can see time, and here is a window but nothing. To get this, we have to click here, and you can see the MUT is here, right? MUT is the instantiated module of the Not-Gete. So here we have in and out. So here we click on in and out. As soon as we double click these two, right, they appear on the right hand side. Now here you can see that the toggling is shown here. And so you can see with time how the input is changing and the output is changing according to that. So you can see it is showing a perfect nature of a Not-Gete. So we have a pulse here and the reverse pulse here. It demonstrates the Not-Gete behavior. So we are done here with the GTK-Wave. Let me close it. You will find a similarity in the Vivado is upcoming. I'll show the comparison there that time. Let me close it. So here we are done. Now there is a difficulty here. Process these codes and the VCD file. What we have found that we have to continuously switch between the particular code, right? This code, and then we have to open and go back in the other terminal, right? So this is very cumbersome when you are designing a very big module and we have to switch, right? So for that we have a IDE. IDE is, and the IDE word, it comes as the integrated development environment. So that means we have everything integrated. So let me here launch the Geany. Before that, let me find the Geany. So the Geany spelling is Geany, and Geany is here. So let me launch the Geany. So here let me do the %. So here you can see this is the Geany IDE. Now here you can see that files will be opened and the file text will be here. For Verilog we will be needing the terminal only. Here I click the terminal here and the terminal appears here, right? So let me go here back and delete the hello and the not test downs. So I have removed. So very careful about using rm-rf. I have used it, but I will suggest you to use the \rm for only, because if you remove forcefully, right, it doesn't go to the recycle bin of Linux. It permanently gets deleted, like the shift delete in the window. Be very careful with this command. I'm a pro now and I use it for long years, so I can go ahead and use it. For your case, you will be very much careful using this command. So let me come back to Geany here. So here let me open the documents, then so here you can see that the hello.v is there. Let me open it. Okay, one more file, the VCD file is there. I removed it. So only the two Verilog files are there. Now the beauty here, the terminal is here, right? And the same terminal is here also. So both terminals are here as long as you are in the Linux environment. List of files in the left this pane. You have opened the Verilog file here and you can do the simulation right away here with iVerilog, then hello.v, and we give the output. So here you can see the file is here and I am simulating using the iVerilog binary here, and let me do a ls. You can see the hello dump is created, and let me execute the hello dump here, and you can see the hello world. So in the single window you can operate everything. This is the beauty of the Geany. So let me show you the Geany about. So this is Geany and this is the fast and lightweight IDE. So this is free. This is under GNU GPL. Even I think Geany has a Windows version too. Now let me open the not with test bench right here. So you can see you can have a tabbed version. So if you have multiple, in one file you have written the Not-Gete module, another one you have written the test bench, so you can open them side by side and compare. And if you want to do copy paste operations from one to another, you can do it easily. That's why the Geany is a very good candidate for the integrated development. So here you can see this file. We have demonstrated this already in the beginning. So let me execute it here. iVerilog, then not with, and then if the output name is not test. So you can see here we are using the iVerilog in the terminal. The terminal is here. We have our code viewing text editor here, and here we have the file access panel where we can see which files are there. So let me do a ls. You can see here the object dump is created. Let me execute the object dump. So you can see, let me pull it a bit up. Now you can see that this much is created. Let me pull it a bit down. You can see now we have the code and the output to compare side by side, up and down in the same view. Don't have to switch windows. So here you can see these two are giving this output. This particular display command is giving this output, and the $monitor command is giving this output. Okay, so you can compare side by side. This is the beauty of Geany. We do a ls here, and you can see the ABC1 VCD is created. From here inside the Geany, you can launch the GTK-Wave through the terminal. So let me launch GTK-Wave and then do the %. Another thing, let me show you how we can just load the file here. Then if you give the file name after GTK-Wave, right? So here what I have done, I have given the command GTK-Wave, then the next I have given the file name, which VCD file. So it readily opens the file. So this is another shortcut. Instead of going file and open and all those, you can directly. So here you can see that as we expand the module under test, the instance is here and in is here. Let me double click it. It comes here, and let me double click the out. So it comes here. So you can see this is there, and if we click this button, right, zoom fit, so it will fit in the entire opened window. So this feature we also have in Vivado and show you. So here the GTK-Wave is opened and you can compare the in and out, these two signals from the MUT. Now let me just shorten it, and you can see here in and out is here. So this is not taking the name PLK and out check, instead it is taking the original name in and out. Okay, and you can see it. So this way you can compare the waveform, the terminal output and the code side by side in case you have a Geany. Otherwise you have to switch multiple windows to compare them. Let me close it, and we are also done with the Geany here. So let me close it. Do the ls. Let me do the, okay, let me keep the VCD file here because I'll show you something later on. Let me remove the object file. So now we have the object files we have removed. And now here in the terminal, let me check where is Vivado. So the Vivado originally is saved in this location. I have created an alias to pick up the tool from this path. So in Windows, you can just go through the navigation and go up to the Vivado and launch the Vivado. That is very easy in Windows. In Linux, you have to use a command line. Okay, so here you can see that the tool is originally situated here and we have used the alias command to pick the Vivado. So let me launch the Vivado. And we give a %, so that the terminal is free. We can use the terminal at any time. So here the Vivado is launching and you can see it is starting the GUI and the splash screen has come. And here our Vivado is here. Once this screen has come, this is very similar in between Windows and Linux. You need not to worry, you will get the same window in the Windows operating system. Right now I am in Linux. Here we will go for a create project. Although there are file, flow, tools, all these menus are here. Right now you can just focus to the create project here. Go to the create project. You go to next and here you can see project 1 and we give it to the project test. We give a name project test. Okay, create project subdirectory, etc. Go to next. There are several projects you can create inside a Vivado because this is a environment of FPG design suite, right? So you can create multiple things. Right now we are focusing on the RTL simulation, that is a Verilog simulation, and hence we are picking up the RTL project. Okay, there would be post synthesis, IO planning, import, example, etc. We are not talking about this. We'll be focusing this one only. Okay, and I check here, do not specify the sources at the beginning. I check it here and we move to the next. So here we use a general purpose. If we go and pick any board here, right? And okay, so it is it's a website, so we have closed it. We do not need it right now for Verilog simulation. So we have picked it up and we move right, go to next. So here it says RTL project name, project test will be created. So we say finish. It is creating the project. So it has opened the entire GUI. Now here is a lot of things. Don't get confused here right now. There are file, edit, flow, tool, reports, window, layout. All these things are here. You can just focus on few things to start with. First, we have to add source file. So we have ready source file. So otherwise you have to write a source file, save it in text editor. Add sources, add or create constraint, add or create design sources. So here you can create also. We have a ready file, so we will pick the first. We will add files. We'll add hello here. You can see what type of files you can add. You even use a HDL also here. And let me click OK. And let me do the finish. So let me expand this one. You can see right here in the sources window, here you can see the main, that is hello.v, right, source file. And now we have to run the simulation. So here we do not use it right now. We go to the simulation directly. After doing the add sources, we go to the simulation. So run simulation, run behavioral simulation. Now it has run the simulation. Let me open and expand here. So you can see here the code is there, and here we are getting the output. Here you can see the hello world message, hello world message. So in this particular Verilog file, we have nothing to do anymore rather than just a hello world print. So here you can see the hello world is printed and our purpose is done. So let me close it and let me go back to add sources. So let me pick up Not-Gete with TestBench this time. So we are adding this particular to our project. So here it is, and we say finish. Sources here, and here you can see this Not-Gete is there, and this hello.v, and we don't want the hello.v right now, and we are removing it from the project. So here I have done the right click on the hello.v and click on remove file from the project. The file is not deleted, however it is removed from the project itself. The physical file is still there. If you go ahead and here and do the ls, right, the physical file is still there, it is not deleted. Let me come back to Vivado, and here what we have, here we have the module and the TestBench together inside it is the editor window. You can see here cut, copy, paste, everything is there. So you can write codes here, even modify this code. So here you can see the first the Not-Gete is here, and the next the following part the TestBench. So it is opened as is. Now let me go ahead and simulate this. We have to click a run simulation and run behavioral simulation. So here you can see that this checking of the output has come here, and this message has came here. We have seen this message through the Verilog simulation when we have executed the object dump. Now here you can see that this and this line is executed. Now let us go on to the graphics for the waveforms, and let me expand it. Here is a maximize button. I maximize it. Here there is a fit to screen also similar to the GTK-Wave. Now you can see here clock and out check here, and here you can see it has picked up the instance name. So clock and out check, clock is the input, out check is the output, and once we go here we can see that clock and out check is there. So here you can see the input waveform is toggling and the output waveform is exactly opposite. That means when this is 0, this is 1, when this is 1, this is 0. So the exact opposite kind of toggling is in the output. So it is showing the Not-Gete behavior properly through the TestBench. Now let me go back here and let me open the GTK-Wave and give the file name VCD. Okay, now let me show you here the difference that we get in between the, so I have displayed these two and fit to screen here. So you can see here in and out picked up as two terminals, whereas once we see in Vivado clock and out check. So with the GTK-Wave we are getting the actual modules in and out in the dump file here in and out, and with Vivado we are getting the clock and out checks here, clock and out check as the output. So Vivado, since it's a altogether integrated environment, here you can see the code, run the simulation and see the output. So you have everything inside one tool, whereas when you use the Verilog you have to use the Verilog and the GTK-Wave. Also, to use an integrated kind of environment you can use the Geany, which I have already shown. So you have seen the basic difference which is coming in the waveform here, as the in and out port is coming in GTK-Wave, and in Vivado it is showing clock and out check. However, the output waveform is very same here, and you can see it is very same here. So simulation is done in a same fashion and the output is coming in the same fashion. However, the names of the ports are different in GTK-Wave versus the Vivado graphics. I think we are done here. We have shown the three options today. One is the basic terminal simulation of Verilog, and then the simulation in Geany IDE, and then the simulation in Vivado. So we have covered the three things. You can pick up whichever you feel comfortable to you. Here I have shown you all the options so that you can try out at your end whichever options you like. Pick up the option that is very much easy for you, and hence I am not suggesting that use this or use that. Pick up any of the tool and the associated tools and run the simulation, see the out. That's all for today, folks. Hey guys, welcome back. In this episode, we are going to discuss the below points. First, we will talk about the various Verilog methods like structural and behavioral modeling and their subdivisions, what are their prerequisite needs. Next, we will talk about in detail for the structural or gate level modeling prerequisite, which is the gate primitives. Next, we will talk about the structural or gate level modeling of a 4:1 marks with test bench. So, we will design the 4:1 marks and also will write the test bench to verify its functionality. Next, we will do the structural or gate level modeling of another digital circuit, that is full adder, and we will also write a test bench for it to verify its functionality. Now here I would like to mention one thing. The test bench is a very important part because when you are writing a module, you may not be 100% correct. So the intention of writing a module is checked by the test bench. So the writing of a module in a Verilog is essential, and utmost essential is the test bench because that verifies your design whichever you have written. So with that note, let's move on to the next slide. Verilog modeling methods. The Verilog modeling type is broadly categorized into two major subdivisions. First one is the structural modeling, which has the basic necessities as gate primitives. We will cover this later in this presentation. The other major subdivision is behavioral modeling. It has two further subdivisions. First one is continuous assignments. The another one is procedural assignments. Now, these two are subdivisions, whereas this is a basic necessity which is needed to construct this. Similarly, this and these are the basic needs that you must learn to write the behavioral modeling. So the basic structure of the Verilog modeling is in front of you. Either you can take a structural modeling or a behavioral modeling. It depends upon how you are approaching towards the design. These are two different approaches and you should not confuse one with another. We are done with this particular slide. Let's move on to the next slide. In today's discussion, we will be focusing on the structural modeling and we will in detail talk about the gate primitives. We are done with this particular slide, so let's move on to the next slide. Structural modeling prerequisite. Structural modeling needs a few prerequisites which comes along with the Verilog language and with the simulator. So the simulator you are using, it has to support the prerequisites. What are the prerequisites? A set of pre-designed logic gates are provided in Verilog language inbuilt library. These are called gate primitives. So let me stress here, this is Verilog language inbuilt library. So this comes along with the language. You don't have to create it. You have to learn how to use it. And these are generically called the gate primitives. So in this kind of library, what you can expect? The basic gates like AND, OR, NOR, NAND, XOR and XNOR. So here are some figures just for your visualization. Generally, when we are writing the syntax, the first terminal is output followed by inputs, and inputs can be two or more. So here you can see there are two inputs, right? You know that this gate can have more than two inputs. So in this fashion, this is written that first one is output, rest of the things are inputs. The next point is we start our example here. This is a typical syntax. This is the primitive gate. You are writing your instance name. Here the first one is the output. So this is the OR gate. Here first you are writing the output and then the first input and the next input. So these two are here and here. So this way you write your syntax. You use them from the library. Next comes the NOR. As you can see, this one, right? This one is NOR. And here you can see this is green color because this is a reserved keyword. This is green, this is green. So these two are reserved keyword. You cannot use them for your own definition. So these are predefined. So these are coming as green. In different text editor or IDE, you will find this is coming in a different color, maybe in gray or something, or maybe brown. Okay, maybe in some other color, maybe blue. However, these are reserved keywords and you cannot use them for your own module name. Next comes the instance and then the output and the two inputs. Here is a typo. I has been printed twice. Ignore this, please. Next comes the AND. It is also two input AND. This is a two input AND. Next, the instance output first. This one is first and followed by the two inputs. Similarly, you can see that the NAND is also there. This one is NAND. So this one is NAND, right? And output comes first. Here is the output and the two inputs are followed by. So this way you can write the connectivity. So actually in case this in or out, all these things will be connected by either reg or where type of variables. So we will later discuss in some later episode about this type of variables. But first you have to grasp the basic structure of the Verilog modeling so that you can give a kickstart. Next one is a 3-input NAND. So here is the NAND gate, here is the output, and here we do not have the picture. However, you can see there are 3 inputs, in 1, in 2 and in 3. So the output is single, so this is constant. Here it is, you can follow after so many things that first terminal remains the output. So here is output, here is output, output and output, and rest of the things are input. Here 2 inputs, 2 inputs, 2 inputs, and here you can see 3 inputs. Next comes the XOR. It has the similar thing. And next comes the XNOR. XOR and XNOR. These are here. Similarly, these two are outputs and the following ports are input port. So this should be the syntax. You should use the first one is the reserved keyword or NOR and you are very much familiar with these names. So these are very easy things to remember. Next, you can name the instance as per your own nomenclature or as per your company's nomenclature or whatever you find suitable. So these things you will name them. And I will later show you in some upcoming episode what you should do or what you should not do about this nomenclature. So we are done with this particular slide. Let's move on to the next slide. We are continuing our prerequisites here in this slide. Transmission gates. This is buffer and Not-Gete. This is a structure of a buffer and this is a structure of a Not-Gete. You can see, you can identify the difference. Here you don't have a bubble and here you have a bubble. In Not-Gete, this is a Not-Gete and this is the buffer. So this is the basic structural difference in symbols between the two. This has one input and one output. However, there can be various different scenarios. One or more outputs first and then single input at the last. So one or more outputs will come first. So it can drive multiple things, right? Here you can have more outputs, right? So output will come first and input will be a single, right? This is the nature. So it is expected single input, single output. However, due to drivability, you can have multiple output ports here. Let us see the example. So this is reserved keyword buff and it is your instance name out then in. Similarly, this one is the reserved keyword. This was the instance and this is out and in. So this is very simple. Next, here we have a not instance which is having more than one output and one input. The input here is fixed. As compared to the previous slide, here input is one and output can be many. And this is because of the drivability, right? If this not has multiple drivability, right? Here 1, 2, 3, 4. So we have 2, 3 and 4. This kind of 4 outputs will be there to drive 4 different outputs. In different circuit configurations, you may need them and hence these are kept in the library and you can use in this fashion. So we are done with this particular slide. Let's move on to the next slide. We are continuing here the structural modeling prerequisites and here let me start. Special transmission gates, buff if 0, buff if 1, not if 0 and not if 1. How do they look? They have a different structure. Here it is a buff if 0, right? And here you can see apart from the in or out, we have another control input. So this is a very distinct feature. Next, for buff if 1, we have in and out and we have extra control. So you can see here, let me clear it. Here you can see this is if 0. So it's a 0 logic and we have a bubbled input for the control. And here it is 1. So we have a direct non-bubbled input. Now for the not 1, right? So you can see the not if 0 and not if 1. So this is common, this bubble is there because of the not, and here you can see because of if 0, here it is a bubbled input for the control input, and here the direct control input. So this is a structural difference with a basic buffer and the basic not-gate. These are tri-state buffer or inverters, output terminals first and then input and then control are inputs. Example, buff if 0, here this is a reserved keyword, and hence here in this particular slide I have kept the color green for the reserved keywords, and this is your instance name, and you can see here out this one, in this one, and control this one. So this way you have to instantiate the defined gate. Next is the buff if 1. Similar way you can see that reserved keyword, instance name, and out. So this one is out, in, and control. So here is in and here is control. This way you will define the if 1. Similarly you will define the not if 0 and not if 1. So here you can see out remains at the first one, then input, and then the control input. So the basic similarity you can see in the syntax is that for these 4 type of transmission gates, these are special transmission gates, you have the structure in common for the syntax to be used. We are done with this particular slide. Let's move on to the next slide. Now, here in this slide, we will do the structural modeling or the gate level modeling of 4 to 1 marks. Let us begin. Here we write the first line, that is the module definition. Here we give our custom module name, marks 4 to 1, and here we define the different input and outputs. Now we need a picture here. So here comes our picture. So you can see this is the out. So this is out, input 0, input 1, input 2, input 3. Here we define 0, 1, 2, 3. And we have select 1 and select 0. And here we have select 1 and select 0. This is the circuit, and we have defined the corresponding ports. These names you can do set by your own convention, and you have to maintain that convention because you have to remember things later on. In actual VLSI design, it's not that you are doing only a single module forever, because you have to keep on doing it and you have to maintain your convention so that whatever module you have defined 6 months ago, you should be able to intercept it even after 6 years. So your convention should be very much from today when you are learning the Verilog. And in case you are working in a company, there you have some conventions to follow, you have to follow that. That is my additional input for you. Next, we define the direction of out as out, and we define the direction input of all the rest of the ports, because these ports and these 2 ports are input and we have only single out. We type the keyword where here, followed by the different wherings we need apart from these ports. Now, where are these wheres? Till 1n. So here we are wearing this, right? This where that goes up to this, right? And here it goes up to this. So these 2 wheres are defined here, cell 1, n, cell 1, n. So this is n means the negated. That means cell 1, and once we put a not gate here, it gets negated. So it is n is coming here. Similarly, cell 0, n, right? Here this is cell 0, n, and it goes like this and goes here and goes here. You can see the different wherings. Now, there are 4 more here. From these output, the AND gates 1, 2, 3, 4. This will have outputs and which will be redirected to the final OR gate here, right? So these were, this were, this were, this were, and this were. We have to give them a name, and hence we define Y0, Y1, Y2, Y3. And here in this picture, clearly I have marked them, so you can clearly identify. For structural level modeling, as I have mentioned in the intro, that you have this circuit ready with you. Maybe with Carnot mapping or POS or SOP method, whatever you have done, you have this ready. So you put these names first, right? These port names. This one, this one, this one, this one, this one. And the wheres like this, you name them first in your diagram, and then you start writing this code. So this will be very helpful. It's not that you start writing the code and then you name. That you can do obviously, but it is a good practice. First you name them in your diagram and then you start writing the code. Next, here is the Not-Gete. So this is cell 1N and cell 1. So it is talking about this one right here. So here we have started our structural modeling. You can see that we are using a reserved keyword, but there is no instance here. This is another beauty of Verilog, that you can skip the instance name, right? You can directly use from the library and the language and the simulator will identify them. This is very easy to use because here you have to write only the gate name. Here you can see another not, which is this one, is Not-Gete. It has input cell 0 and cell 0n. So cell 0n and cell 0. At this stage you can see the primitive syntax that we have learned last 3 slides. Those are coming into use. Next, here we have the AND gate, and you can see this one is the first AND gate. So here we have Y0 and here it is Y0. So this is the first AND gate. And next we have the next AND gate, which is Y1, and it is here the second one. Third one here Y2, this one, and fourth one is here Y3. So this part, whatever we are doing it right now, this is called the structural modeling of all these AND gates, AND gates, AND gates, and NOT gates. These we have used from library. So these 4 gates, these 2 gates, and this gate we have used from library, that is from the gate primitives. And you can see here, as per our port definition from the diagram, we have connected them. So output is here, input, and then we have the rest of the input as per our circuit connection. Finally, we have the OR gate here. This one is a 4 input OR gate, and here first we have the out, and then we have 4 inputs. So Y0, Y1, Y2, Y3. So those are going as an input to this OR gate. So you can find the similarity when you have multiple ICs connected in the breadboard. This way you write your circuit and then you do the wiring. So in Verilog, it is very similar way. You are using the library gates here and you are doing the connectivity to this port nomenclature and wires that we have defined. We end our module here. Here we started our module and here we ending our module of marks 4 to 1. This is the multiplexer and we have 2 select inputs, 4 inputs and 1 output. So we are done with this particular module definition and design as per the structural modeling. Now the things are clear to you what is called a structural modeling. We are done with this particular slide. Let's move on to the next slide. Here in this slide, we will design the test bench of the 4 to 1 marks that we have designed. So first we write the module, then marks underscore TB. TB refers as the test bench. And here you can see we have not defined any input output ports because this is kind of like we have your module here design which you have done, right? And the test bench is around it. It's like the breadboard. So the breadboard don't have ports, right? Similarly, the test bench also do not have ports. However, the chip or the IC that you are putting in the breadboard will have ports. Your module will have ports. So this is a very similarity between the breadboard and the Verilog language. Here is our circuit which we have used in last slide also. I have kept it for your easy reference so that you can relate it. So first here we define reg here, that is register type of variable and where. So register type of variables are used who can store the values with time. So here remember these are for your test bench and that means these are part of your breadboard which you will connect to the circuit inputs, right? So remember this thing. Next we instantiate, that means we are putting a physical chip into the breadboard, right? This is a module name and this is the instance name, marks underscore inst. You can name it as per your own nomenclature or as per your company's nomenclature. So here we have used the port names as is out, input 0, input 1, input 2, 3, cell and 0. So one more thing here, in this slide I have kept the names exactly same. We can vary them in upcoming episodes. We will discuss about that. But for simplicity I have kept the names same right now for your understanding. We start our initial block. Here the initial and the begin means it is beginning the block. Then we have the system command dump file and we are writing the VCD file name. This you can give as per your own nomenclature. And here when we write the dump vars, that means it will dump all the variables, right? Here all these variables, this dump vars command will dump into this particular file. So this is the purpose of the dump vars. Next we have the display. It's similar to the printf command. Here I have made 4 tab separated column names for input 0, input 1, input 2 and input 3. These will come as a text output. Then at time 0, this is a delay symbol. I will discuss later in some other episode. This is a delay symbol, that means at 0 time we have the input defined. So if you put a curly bracket, right, and if you club multiple variables here, you can give a value in one go. Otherwise you have to use 4 different statements to define them. This is a kind of shorthand, and that is very easy for you to write a short and simple test bench. Now let me explain. Here are 4 inputs, and you can see because 4 we are putting number 4. 4 tick B. B means binary, and we are giving the binary values 0, 1, 1, 0. So these are going to 0 is going to this, 1 is going to this one going to 2, and this 0 goes to 3. So this way we are defining them. Next we have the display command. Here we are also using the tab separated value. However, here we use the column names. Here we are printing the column values of input 0, input 1, input 2, input 3. Next we have the next column names for cell 1, cell 0 and out. So these are also tab separated, you can see, for a better viewing experience. Next we have the $monitor. So this is a dynamic kind of printf operation which keeps on monitoring these values. If any one of them changes, it gives a printout as per this entire command. Next we have the value giving. So after time unit 1, we are giving the value cell 1 and cell 0 as 2 binary. 0 goes to this one and this 0 goes to this one. This 2 is because there are 2 variables here and B is binary and we are giving 2 values. After next one time unit, we are giving the value 0 to this one and 1 to this one. Next, after again another one time unit delay, so this is adding a more delay, that means after elapse of one time unit and again after elapse of time unit, that means 1, 2, 3. So 3 time unit has been elapsed and there we are giving 1 to cell 1 and 0 to cell 0. Next, after elapse of further one time unit, we are giving 1 to cell 1 and this 1 to cell 0, and then after 5 time units we are calling the system command finish to finish the simulation. As I have mentioned in previous episode and other previous episodes that the Verilog is a transient simulation. That means we have an independent time axis with respect to every other thing change, whether we change it or as per the circuit operation change. So the timing simulation has to have an end, and this end is defined by this finish command, and it is a system defined command and it's a reserved keyword, and hence I have kept it in green. You cannot use it for some other purpose. So all these things, right, this dump file, dump vars, display, monitor, these are already reserved keyword. So like that initial and begin, so you cannot use them for your own purpose. So they have a defined purpose and you have to use them for that only. And here we end our initial begin, right, initial block we are ending with end. Then we are ending our test bench module with here. So you can see in the test bench, we have defined or changed our values. In breadboard, what you do physically, you connect, you have a plus output and you have a ground connection, right? And you keep on changing either to this or to that and this to that. Like that, we are changing here. So this is a very similar to the breadboard operation. Now, here we have instantiated a mux. So we are operating on mux. Once our slide ends, we will do the simulation in both Vivado and Icarus Verilog. So we are done with this particular slide. Let's move on to the next slide. Structural or gate level modeling of a full adder. Here we will design a full adder using half adders. Also we will write a code for the half adder. In actual practice, you may get this half adder from a vendor and you can use it to make a full adder. So this is another type of structural modeling where you have a predefined block, which is here the half adder, and you are using it to make another design. So full adder circuit using 2 half adder. So this is the circuit and here is the circuit. Here you can see this is a half adder and this is a half adder. So in actual design, we are using 1 for this one, half adder 1, and here this is half adder 2. So let us start. You can see we have defined our basic inputs of the bigger block as A, B and C in, and we have defined the output as sum and C out. So here let us define the half adder module first. The module half adder, and we have A, B and sum and carry. So you can see A, B, sum and carry. This is very simple. We have putting inputs A and B, output word type sum and carry. And here we are using a assignment command here. I will explain in some later episode. which is not part of the structural modeling. It comes in the behavioral modeling. I will explain in those episodes. For now, as this particular half adder is coming from a vendor to you, you are not designing it. However, I am explaining the code. So here we are using an assign statement for the carry. Sum is A XOR B and carry is A and B. And here we end module of the half adder. So this half adder module you have received from your vendor, and using this you will be designing or you will be doing a structural modeling of a full adder. Here first statement is coming here as the module definition full adder, and here you can see we have defined the 3 inputs and 2 outputs, right? The A, B, C in and sum and carry out. Next, we define the type of the ports, input port as A, B, C in and output port as sum and C out. Next, we define the interconnection wire, that is S1, P1 and C2. So these are interconnection wires this will be using for this circuit. As I have mentioned, for structural modeling, you have already this diagram with you. So you have the diagram first, and as per that, you are writing your Verilog code here. So this must be very clear to you, because the structural modeling fundamentals are like that. You have the design first in your hand and then you are writing the Verilog code for this. So half adder 1, we have the instance. So we have the module definition here, and we are using an instance name HA1. So this is HA1, and you can see AB is here and S1, C1. So S1 and C1 is here. Next comes the half adder 2. We have P in and S1. So C in and S1 as inputs, and we have sum and C2 as output. So sum goes to this sum and carry is connected with C2, the wire, and it goes to the OR gate. Now we have to have the OR gate. So let us introduce the OR gate. So OR gate here has 2 input, 1 output here, C out. This is the C out, and we have P1 and C2. So C1 and C2 as inputs. So here you can see that using library gates, I have made a inline comment here for the good understanding. Now here we end our full adder module. So the definition of the full adder is done here in Verilog, and corresponding diagram is with you. So in structural modeling, the diagram should be ready before the writing the code, and this is here. So we are done with this particular slide. Let's move on to the next slide. Structural or gate level modeling, and here we are writing the test bench to verify the full adder that we have written in the previous slide. So here we start writing our code. Here we write our module and test bench. Since this is a test bench, this is like a breadboard on which you are putting your module as a chip. It do not have the ports, so there is no ports defined here. Here, right, here is our basic circuitry of the full adder, which we are instantiating inside this test bench. So here we type reg ABC in. Here ABC in, these are reg type, so this can actually over time remember the values, and where cannot remember the values over time. So here sum and carry, these are wheres. I will explain in some later episode about these variables, what are the deep meaning of them. Here we initial and begin, and here we use the dump file to name the full adder.vcd, and downwards will dump all the variables into this VCD file. Display, here we are using the display command for the column name, time, tab separated A, B, S, C in and C out. So A, B, S means sum, and then C out, C in and C out. Okay, all these things will be there. And here we write the monitor command to fill up the values time wise of for this particular column. So this belong to this column, this belong to this column, and this belong to this column. So values of the columns will be filled by the monitor command, which is printf kind of, but it is a more dynamic because it scans the input over time, and whenever there is a change, it prints the values. We are using the shorthand. At 0 time, we are giving the value 0 to A, 0 to B, and 0 to C in. So here we have clubbed 3 variables together. This is 3 means these are 3. B is binary because the following values will be binary. In the similar fashion, we continue the truth table here. Here I have taken a jump of 5 time unit each time. This completes the truth table. And at time unit 40, I will finish. So here you can see that here we have completed the truth table of 3 variables. We have 0, 0, 0, we have 0, 0, 1, 0, 1, 0, 0, 1, 1, and hence we reach up to 1, 1, 1. So the input truth table is captured here for this full adder. And we will get the outputs here in the simulation. Here we end our initial block, which has started with the begin keyword and ends with the end keyword. And here we instantiate our full adder from the previous slide here, and we give the names A, B, C in, sum and C out as the port names. And here for simplicity I have kept the same names. Later I will, in some other episodes, I will show you the different way you can deal with these ports. Here we end our test bench module with the end module command, right? This ends the test bench. So here we complete. So we are done here. Now let's move on to the simulators to try these Verilog codes and see how the output is coming. Hey guys, welcome back, and we are here in our directory where we have the two codes, that is for the full adder and the mux. Let me open them with Geany. Here I have kept open. So here in Geany we have mux.v. First we have the module definition, and at later part we have the test bench. So I have explained these to you, both of them, in the slides. Now let me run simulation for this. Here in Geany we will use the Verilogs. Let me do ls. Here you can see our mux.v is there, and since Geany is a tab browsing, I have also kept open the full adder.v in another tab. This is the beauty of the Geany. So you can keep multiple files open side by side. And here in terminal, let me run the Verilog. Then I give the module name mux.v, and then we give -o. The output file, the object dump here will be there. The output object dump which we have to execute to run the simulation. So I give it a name mux. So I run it. The run is complete, and let me do a ls. So you can see as per the run, the mux is created. The VCD file has not yet been created. Let me run mux. So you can see here in the test bench, we have defined the column names here and corresponding monitor commands to fill the columns. And we have defined vectors, that is the truth table for the cell 1 and cell 0 to be changing with time. And here we can see the output. So here you can see that inputs are checked first, whatever input we have given as port tick B0110, 0110, and then we change here, we change our output here in this column independent changing, and the corresponding here is independently changing. So at the beginning we have not set any value, so the first one we ignore here, and rest of the 4 values we will pick here, because here we have set it, but at the initial stage we have not defined any cell 1 and cell 0. We have defined here after time lag of 1 time unit, that means time delay of 1 time unit. So the first entry is X here. Let me clear. So we do not count this one because this is we have not defined, and the rest of the things we have defined, and as per our definition it is changing. The mux will pick up as for 0110. So here you can see it is picking 0110 as per the truth table operation, that is all combination of values we have put here 0001 1011. So accordingly the output is changing for the port to 1 mux. So here we are done with the mux related simulation in Verilog, that is the Icarus Verilog, and we are using the Geany IDE for our entire operation. Now let me clear the screen here and let us move on to the full adder, right? So here you can see that your half adder is defined as we have done in the slide, and here is our full adder module. The structure modeling is done here, and you can see here, right, the test bench is here. So you can see at first we with the display and all we have defined the column names and the column values, right? And then we have defined the changes to the input, and as per a truth table we have defined the change in the inputs, 3 inputs here for the full adder A, B and C in. We have done here, and according to that the output will be displayed on the screen here when we simulate as per these statements. So let me run the simulation. Verilog we will give the full adder, then -o. We give the dump object dump as FA. Here once we execute it, it has run the simulation, and the object dump is created as FA, and you can see we do not have a corresponding VCD file. This VCD is from the previous mux simulation. Let me execute the full adder. And here, once I execute, you can see right here the print statements have given the column names and checking the output of full adder. Don't worry, I'll provide the download links of this 2.v file in the description of this video, from where you can directly download them, use them, or alter them as per your need. So here you can see the time is independently changing here, and as we added delay, right, it keeps on adding. So this is added to the next, and this is added to the next, and this way at here it finishing, right? So you can see at 140 it is finishing, and whenever the values change as per our truth table change here, right, we have defined the truth table for these three inputs, right? So A, B, right, and C in, right, these are inputs, and this is our output, S, and C out is our output. So the change here you can clearly see as a truth table. So this way you can verify the functionality. Let me show you the graphical output also here. Let me clear it and let me show you the GTK-Wave. First we have done the mux, right? So here is the mux one, and the VCD is here. So let me launch it. So here you can see here it has come, right? All the inputs are here, and you can see the types which we have defined here, right? You can see the type definition in Verilog is also coming here, and we have the all signals and all wires and interconnection is coming here. So from here, if we want to select anything, that will come here and the corresponding waveform will be shown here. Let me show you. So here are 4 inputs. This is 1, 2, 3, 4, right? These are inputs, and we have 2 selection inputs. Since we have not given anything at the beginning, right? You remember the X from the terminal simulation, and here is our out. So let me expand it and fit it in the screen. So here, if all these inputs you want to check the value, right, you can click a cursor and take the cursor at some point, and there you will see the corresponding values. That is 1010 values will be displayed here. Let me move it to some other point here. So here, as I am changing, you can see the changes are automatically coming here. So as I change again, you can see change, right? It has changed here from the previous one. So this way also you can verify the operations in form of waveforms. So these are called waveforms, and these are digital waveforms, and this file is VCD file. So let me close it, and here let me clear it. Let me do alias of .vcd files. So we have another full adder, right? We have shown for the marks, right? We have the full adder, right? So let me launch the full adder. So here you can see the full adder is here, right? It has also a half adder and a half adder. So if you want to check for the half adder, you can go ahead and check for their values also. Half adder 1 and 2, right? You will see all these things. For half adder 2, you will also have the other values. So you can go and debug, right? Here is the full adder, right? You have the A, B, also the wires, and there is C in, right? Internal C1, C2 and S1 is also there. C out and sum, right? So all these are there, right? Select and delete all. So here, let me check the final output here. A, B, P in, and the sum and C out will be at the output. So let me expand it, and now if I put my cursor anywhere here, you can see the corresponding binary values are also displayed here. Since you have not given print of the internal variables, right? What you can do, if you want to check what is happening in the half adder, so you can put all the internal values right here, and then half adder 2, all the values here. This way you can investigate the values at any time of your circuit if you are facing any kind of anomaly in the expected output. So here, say if you see something difficult here, right, what you will do, you will put your cursor here, right, and then you will check the values here, what is happening, and you will check, okay, this is happening at 1 and this is happening at 2 of the internal circuitry, right, for the half adder 1 and half adder 2. So this way you will investigate the things inside your design. So here we are done with the simulation and the waveform verification for both the mux and full adder using the Geany. Now let me close the Geany and let me move on to the Vivado. So I have opened a terminal here and let me launch Vivado. So the Vivado splash screen has come, and here we are with the Vivado home screen. So here let me click on create project, next project, and here it will be saved in our Verilog 3 episode and Verilog codes. Next, RTL project, do not specify sources at this time. Next, category all boards 1, next, and we here finish. So here the Vivado interface is ready, right? Let me add sources. Next, add files, we add mux.v, finish. And here you can see our mux EB and our mux module is here loaded. Is opening in editor, right, mux.v. So here you can see our test bench is there and our module is here, the definition, and the test bench is at the later part. And let me run simulation. The simulation is done. You can see here that this too has the column names and this is also the column name, and here you can see the initial input values and here the table. So first one we are omitting because in the test bench we have not done, and here you can see that we have varied the cell 1 and cell 2 output, right, and we have got the output here in this column. So somehow here the alignment of the tab is different and here the output is coming, but however from the column sequence you can understand this is cell 1, this is cell 0 and this one is output. This way you can interpret. Now let me move on to the waveform. So here I have done the zoom fit. You can see here, let me change the panes because these panes are not yet. Let me do the zoom fit. Yes. So here you can see that at the beginning this cell 1, cell 0 is not fixed. So these are red, as here it is coming as X, as here it is coming as X, right, and here it is coming as red. These are same. So don't think about them. Rather, if you click here, right, you can see the different values here also coming. If you want to debug this, you can also debug it. And you can see the corresponding value changing as per you move the marker here. The corresponding values will change here for all these inputs. So this way graphically with the waveform you can debug your design or check the functionality. And as I have said, right, mux is there, right. So here you can see all these ports, etc. And we are done with the mux simulation using this Vivado. Let me go to add sources. Add files, full adder, sources, right. So mux, let me remove from this project. It has removed. So we have this one, right. Full adder, right. Opening in editor. Here you can see the full adder. First, you can see the half adder here. This code is provided in the video description from where you can download it and you can try it at your end. Here is the full adder, the structural modeling of the full adder using the half adders, which we assume that we have received from our vendor. And finally, we do have the test bench here, right? I have explained in detail already. And here, if you go, right, let me run the simulation. So let me control the panes here and let me do the zoom fit. Here you can see the inputs and the binary values are coming, right? And if you put the slider here, right, the corresponding binary values will change. And here you will get the change values of these binary variables. So this way you can debug your design anomaly. If something, say if at this point the anomaly is coming, you will put your cursor here, and at this point, once you put the cursor, the values will change here, and according to that, you can debug your design. Another thing, this is the graphical, and also we have at the bottom the, let me open the test bench side by side here. You can see, right? So all these display related command, the printf type of command is creating first set of column names and etc. And then the truth table creation by the value assignments right here. It is creating the truth table here. Here you can see that the time has gone and some has shifted here. However, this was not the case in the previous simulator. This is time A, B, S, C in and C out. So this way you should interpret them. So now you can see all these codes are simulated in both the text fashion here and as the waveform. Here you can take either this approach or this approach, or you can use both of them to understand whatever you want to debug or go deeper in the design. So we are done here with the Vivado simulators, and we have simulated both the marks and full adder here, and we are done here. Hey guys, welcome back. In today's episode, we are going to discuss the below points. We will give an overview of the Verilog modeling methods. Next, we will give our introduction towards data flow modeling in Verilog. Next, we will talk about the significance of continuous assignments in data flow modeling. Next, we will do the data flow modeling of a half adder in Verilog. Next, we will do the creation of the test bench of the half adder, which has been designed through the data flow modeling. Next, we'll do the code simulation with the combination of Geany IDE, Icarus Verilog and GTK-Wave. Next, we'll do the code simulation using Vivado 2022.1 ML edition. So this way you will have both the taste of Icarus Verilog as well as Vivado for the Verilog code testing. That's the menu for today. So without any further delay, let's begin. Verilog modeling methods. We can divide the different modeling methods in Verilog in two major types. The first one is the structural modeling, which is done using the gate primitives, and the behavioral modeling, which is done in two different ways. The first one is the continuous assignment. We use continuous assignments to do the data flow modeling, and the procedural assignments. This is another way where we use the if, else, etc. different things and all these blocks here in the procedural assignments. In today's episode, we will talk about the continuous assignments, how we do the data flow modeling using the continuous assignments. This is a brief overview of the Verilog methods. We are done with this particular slide. So without any further delay, let's move on to the next slide. Introduction. Small digital circuits can be easily described by structural or gate level modeling. In last episode, we have done the structural or gate level modeling. For large or complex circuits, it's easy to use the logic equation at coding or programming level to describe the nature of the flow of data in the circuit. Now, we are doing a level up here and we are moving towards a bit large and complex digital circuits in nature. There, the method that we will use is the logic equations at coding or programming level. This one. And also keep the point here, the flow of data. That means we have a circuit right here and we have some inputs here and outputs. And flow of data means obviously data will flow from this towards this direction. So this is the data flow. The word data flow means this kind of operation, which is shown by this diagram. Data flow modeling describes the architecture of a digital circuit without describing the explicit components, rather describing in terms of the flow of the data from input towards the output. You are very much aware that in last episode, for structural modeling, we have used the gate primitives and we have interconnected the different gates to construct the circuit, where our circuit was already ready by the Carnot mapping and POS or SOP form in hand. However, the data flow modeling, which is a bit different here, the data flow modeling is bit different. So we have to design the data flow. That means this is a circuit and we have inputs and outputs, and data will flow through the circuitry towards this point or towards this point. So there will be lot of circuitry here. All these equations which will help the data to propagate from the input port towards the output port is the technique called data flow modeling. And here we refrain from expressing the exact digital circuit with explicit components. Here we have used the explicit component, that is the gate primitives in structural modeling. Here we use equation, but we refrain from using the gate primitives. Rather, we have logical equations to build up the data flow. However, we will have a test bench to testify our own design, which in every episode I essentially include, because otherwise your design is untested and you don't know what can be the output. Data flow modeling uses continuous assignment to code the above mentioned equations. Now, we have done the structural modeling where we have used the equations to interconnect the gates, and in data flow modeling, what we are doing, we are using continuous assignments. In today's example, I'll be using the continuous assignment, which is nothing but a assign statement to code the above mentioned equations. So that means the data flow. So we have to create the data flow using logical equations. These are logical equations rather than explicit equation in terms of gates. These equations may contain one or more operators among the arithmetic, logical, conditional, relational, equality, bitwise, shift, reduction, and concatenation. So, clear it? So, the equations that we are going to form the data flow, we will construct the data flow from in to out, will include some of these mentioned type of operators. So there could be arithmetic operator and conditional operator, there could be relational operator, there could be only bitwise operator, there could be shift operator, there could be concatenation. We will use different combinations of all of these operators in data flow modeling. However, in today's episode, the example is very short and simple. Just to begin your data flow modeling, later episodes we may come up with a complex circuit where we are using different kind of operators. So we are done with this particular slide. So let's move on to the next slide. Continuous assignments to be used inside data flow modeling. How do we use the continuous assignments? Here are some glimpses for you. Data flow modeling is used to represent the code or combinational circuitry. A net is assigned using the continuous modeling with a assign statement. Let us begin the examples. These are not code examples. This is the example of the assign statements for data flow modeling. First, we can define where type net with 3 down to 0. We read it like 3 down to 0. This is a bus, and preset and clear. And we end the statement with a semicolon here. Next, we use these variables which we have defined here using the where statement to construct the assign. We have defined the variables here, and here to represent the data flow, we will use this equation. Here the statement name, this is a reserved keyword. Assign is a reserved keyword, and hence here it is shown in green. In a particular text editor, it may come up with a different color. However, this is a reserved keyword. You cannot use it for your own variable name or any other personal purpose. So it is assigned for a particular function, and here it has to be used. So here you can see the equation Z, this one is AND, logical AND of present and here. Here there is a typo here. So this is a preset, and there is a typo. It has become present. Please excuse me for that. So Z is nothing but the AND form of preset and clear, which we have defined here and here. So next one, expression on the RHS is evaluated whenever any operand changes its value in the RHS. So whenever the preset or the clear changes a value, assign statement keeps a track of this change in any of these variables, and whenever there is a change in either preset or clear, the entire equation is evaluated at that particular time point. So at maybe time t equal to 10, this is evaluated. Time t equal to 20, it has happened again, there is a change, so it will evaluate again, and hence it will go on. Next, we give another example. Here we define a net using where, that is C out and C in. These are two different wheres, that is nets. We define couple of more wheres here. 3 down to 0 sum is a bus, and A and B. Next, we use the assign statement here, assign, hence it is in green. And here you can see this curly brace, right? This is a concatenation operator, right? Here it concatenates these two. And here we use the logical expression of ORing, that is A or B or C in. So this is a logical ORing operation, and this is not a regular addition operation. This is a logical operation here of the ORing, and hence the assign statement, the entire assign statement creates a relation between the inputs and outputs. These are outputs and these are inputs. So this way the data flow is modeled by the assign statement. Here is also it is same, these are inputs and this is output. So you can see that the assign statement can be used to model the data flow from input towards the output. So arrow is going in the left hand side, and here is also from input towards the output, and here the arrow is in the left hand side. From right hand side it is evaluated and the value is assigned at the left hand side. So data flow here for a circuit here, right, when we draw like the in is here and out is in our RHS, right? This is in and this is out. So in and out is here, right? However, when we are drawing, right, we are drawing from left to right here. The flow is going. However, in equation, you can see it is going from right towards the left. From right towards the left. However, in the circuit, when we are imagining the circuit, the data flow is from the in to out, that is from left towards the right. So keep this thing in mind. In continuous assignment of data flow modeling, LHS, that is the target, is an expression, can be a single net, that is Z, bus, that is a bus which we have already encountered here, the sum one. Then the bit select, right, a single bit. Z is a 4-bit, right, 3 down to 0. And here Z we can assign one single bit also. Let me clear the drawings here. Z1 can be assigned. This one can be assigned individually, 1 bit, by any operation which we have discussed in last slide, be any type of operation, and with the assign statement we can assign this. Next, we can use the concatenation. I have already mentioned here. Here it is already the concatenation I have shown you. And this is a good summary. Here it could be a single net, it could be a bus, it could be a bus but bit select. And here it was a part select, that sum 2 down to 0. Part means not the whole. Here sum is 3 down to 0, and here we have used only 2 down to 0. So it's a part select, or it could be a bit select, a single bit. Or the entire bus could be used in assign statement. So this way we can have many combinations of the assign statements to describe the data flow as per our design, or the design and the design need. So here we are done with this particular slide. Let's move on to the next slide. Data flow modeling of a half adder. So here we'll do the Verilog coding of a half adder for the data flow modeling. Here goes our comment, half adder circuit, and we start our module definition. Module half adder, we name it, and we give the A, B, sum and carry, right? So these two are inputs and sum and carry are the outputs, right? So here you can see our circuit, and as I was saying, in the design of the circuit, generally we draw that our inputs are at the left while our outputs at the right. So A, B, sum and carry, and this is a block diagram. So here the A is in upper caps, B is in upper caps, sum is in upper caps, carry is in upper caps. And when we are using the nets, right, we are using them, or the sum or carry, right? These are ports here. So we define these two as inputs with this input command, and we define output and type is where, right, for the sum and carry. So this sum and carry we have defined as outputs. So these are inputs and these are outputs, right? So this way we define the in and out with these two statements. Next, we are using the assignment statements, that is the data flow modeling. We define sum is equal to the A XOR B. We know from the basic equation of the half adder, right, that A XOR B, this sum is nothing but A XOR B. So here the caret sign, that is this sign, is equivalent to the XOR sign here. We have to remember these mappings, right? Otherwise we don't have a exact XOR sign here. We used to use the caret for the XOR sign. Later I will give you the different operators which we will use in tabulated format in some other episodes. And the carry is A and B. So this AND is a logical AND. This is a logical AND. So this is nothing but the AND operation, logical AND operation, not the AND gate. So here you have to be very careful. This is a logical AND operation and this is a logical XOR operation. However, the symbol is different here, and in some later episodes we will cover all of them through the tables. And here we end our module of a half adder. Here you can see that we have used the data flow modeling of Verilog to construct the data flow from the input ports towards the output ports here to the assign statements. This is the data flow modeling in Verilog. So we are done with this particular slide. Let's move on to the test bench. So here we will design the test bench of the half adder, which we have done through the data flow modeling. Now here, let me tell you one thing. We are not using the data flow modeling for the test bench. The test bench is a common practice that you will become familiar with multiple examples throughout this series, and you will be very easy after a couple of episodes to write your own test bench. So here we name that test bench here test bench half adder, because you know, right, our test bench is nothing like the compared to the breadboard, which do not have any ports, and there we instantiate a module which is nothing but in actual breadboard is a chip which has ports. The module which I have defined in earlier slide had input and output ports. However, here since this is a test bench, nothing but similar to the breadboard, it do not have the ports. So we do not have the ports here, only a empty brace here. So here we give a picture of the module which we are going to instantiate for our ease. Now let's define the reg A and B. Reg is nothing but it has memory. This kind of nets has memory and they can remember the values over the time period. That means because our Verilog simulation is a transient simulation and we do the simulation with respect to the time. So these register variables have a nature of remembering the data values over time, because in Verilog the simulation happens in the independent axis. There is time. So time goes in the independent axis and the rest of the variables will change in the y-axis. So here we will have multiple things, but however the x-axis, it will be time. Over time, if we have to remember some values, we have to use the reg kind of nets. Then we use the where, sum and carry, and we start our initial block here. Then we write the first statement inside the initial block as dump file, and here we give the halfadder.vcd, this name. So this file will be dumped, which we can view in the GTK-Wave. Next we give the dump var. So this dump var does nothing but this dump var, what it does, it captures all the changes on all of these variable and time t and dumps them, all of them inside this file. These two has to be used back to back so that we get the filled up VCD file. So we use a printf statement just for the heading print here, checking the output of the half adder. Then we give the another heading. Here we have a tab separated. First one is the time because it's the independent variable, then A, then B, then S, then C. That is S is sum and C is carry. And here we give a monitor statement which is very different from the display. Display is a static print and it occurs only one time. Wherever the monitor is different, because it keeps on monitoring all of these variables. If any of them changes at a particular time, right, the monitor gives the print on the screen. So this monitor statement will fill up the column values of time, A, B, S and C. Here you will also see it is tab separated. And here we have explicitly given time, A, B, sum, and carry. So this way it is filling up the output columns. Now here we know this is a delay element, so at time 0 we give the value here. Let me tell you again one thing. This is a shorthand. If we use this thing, this curly brace, and we club the A and B, two variables together, that means the two inputs, right? We are clubbing here and we use 2. 2 means the width is 2 here, 2. B is binary. Tick we have to use, this is the convention, and we give 0 and 0. That means 0 to A and 0 to B. We assign these two values. We do not use assign statement here. We are just giving the values or changing the variable values using this particular statement. And here you can see, right, we have changed the value here 1, and this is after 5 time unit delay, and this is after 10 time unit delay. We have changed it to 0 and we changed it to 1, and here 1 and 1. You can see for A and B, for these two inputs, we have defined the truth table for the input change, and we will get the truth table output for sum and carry to the printf statement in the screen. Here at 20 time unit, we do the finish. This finish keyword finishes the simulation, and it finishes the time-wise simulation at after 20 of this. So when we add 0 plus 5 plus 10 plus 15 plus 20 equal to some time units. At that time unit, the finish will occur. We end our initial block here with this end, and then we instantiate our half adder module using the half adder, and we give the instance name as HA, and we give the ports names A, B, sum and carry. Already we have defined the types. It is reg and this is where, right? Here you can see that we have connected these ports in the instance. Another thing here, let me tell you, this reg will remember over time. So whenever we are moving from 0 to 5, these values will be retained up to the 5 time unit, and after that this will be changed. So reg is the purpose, because here A and B has to hold on to the value here. Outputs are where, so they will simply give the output. However, these inputs have to be memory type. That means they have to hold on to the values of 0 and 1, 0, and they has to change up to 1 when after 5 time units. And from this to this move after 10 time units, from 5 to 10, they will hold this value, and then it will changed by this statement. So this is the significance of the reg type of net. And here we end our module using the end module statement, and here we end our test bench. So that's the test bench. We are done with the test bench, and let's move on. Hey folks, we are in the folder where the Verilog code is kept. Let me open a terminal here, and let me open Geany. Folks, you can see here the module half adder, which we have just talked about, is written here with its inputs and outputs. And here in Geany, you can see the reserved keywords are highlighted in deep blue or navy blue, whatever you can see. And we have the test bench here. You can see the test bench is written here with the inputs and outputs for the instance here. And we have the truth table input combinations defined here, and the outputs will come to the print using this print commands. These are display and monitor, two types of print commands. Monitor is a dynamic print command, and the display is the static print command. So let me here do a ls half-adder.b. Let me run the code through the iVerilog, that is the Icarus Verilog. So we have typed the simulation command iVerilog half-adder.b-oha. So the output object dump will be named as AJ instead of the default a.out. The simulation, here you can see the object dump is created AJ, and let me run the object dump. And here you can see the comparison. Here we have defined the time A, B, S and C using this particular display command, and the values for all of these changes here, this change is depicted here using the monitor command. and the output for the sum and carry are depicted here. So you can see the truth table has been printed here, and here we also can see this time values, the time values which you have given with the hash statement. Here you can see that these time values are also printed for the time. So this is a time wise simulation, that's why. And by your basic common sense you can understand this is the truth table of a half adder. We have verified our design which we have done right in the Verilog modeling using the data flow assigned statements is correct, and the output is giving correct, which is verified by the truth table. Let me open GTK-Wave. Sorry folks, there is a typo, let me correct it. GTK-Wave, and let me launch it once again, and here it has launched. You can see here the test bench is there. Inside we have the half adder, right? Half adder instance named HA, and let me expand it, and this is the first two inputs, right? And then we have the sum and carry. Here with this button we are doing the fit screen, and if you do the values here, right? AB00 sum carry 00. So here change 0110, and here 1010, and here 1101. So this is the basic truth table. Also you can find from the graph. You have to just point the marker here by clicking directly on the graph on the right hand side. Here I think we are done with the graphical verification of the half adder that we have, and let me close it. So here we are also done at the Geany front, and here we will open up Vivado. Let me open the Vivado. So it is opening up. You can see the Vivado 2022.1, this version is opening up. So here it is starting the GUI. You can see the message, and here the splash screen has come up. Now our interface of the Vivado is here, and let me create a project. It has picked the directory name correctly here from where we have launched it, and we have checked the option create project subdirectory. So we have clicked it, and here we are selecting the RTL project and do not specify the sources at this time. So this we are picking up. Next, and here it should be all, everything is all right, and we go to the board and click on to a board, and then we click next. So it gives some message which, let me close this website. It has taken to the board definition and all. So it has given the new project summary here. Okay, our new RTL project will be created, and we have picked up the board. Although here we are not using the board, we are doing just the simulation, so it's okay with us. Let us click on finish. I will go for this add sources now, because we have written the Verilog file here with the module and the test bench inside the same file. From the directory we have launched the terminal, and through the terminal we have launched the Vivado. So we will go and click on the add sources. So we will pick up the add or create design sources, this option, and next we will go for add files. So in this particular folder we already have the halfadder.v which we are picking up, and here is the preview of the file. In case you have multiple files, you can check the preview here, and we click on OK. So here we click on finish. So here you can see the halfadder.v, it is opening in editor. So here you can see the module definition is getting displayed, and if we scroll down right, the test bench is also displayed. So we have opened the correct file here, and now let me go for the, we will go ahead and click the run simulation here at the left, and we will pick up the run behavioral simulation. So the simulation has finished. This is a graphical form, and let me open the text form here. So I have resized here. So here you can see the output here. So these print commands, the display and the monitor commands, help to print out the two top lines where the definition of the output and the column names have been described. And here you can see these time values which are simulated has come here with the print command here, the monitor command, and this change of the input values for A and B, these have been displayed here. However, there is a shift here. You can see for A this line is picked, for B this line is picked. Okay, now the output has been displayed here for the sum here and the carry. So there is a shift here due to the white space management of Vivado during the print commands. And you can see, however, here it has been, if this is the sum, right? So this is a XOR of these two only. It is 1 only when 0 1 and 1 0 combination, that is exclusively either A or B, any one of them is 1. The sum has been truly evaluated, and for the carry it is AND, that is A and B. So here you can see these three are 0 and only this is 1 when both are 1. The truth table has been correctly displayed here for our module under test. So here let me resize it and let me shift it a bit, and here we use the toolfit command similar to the GTK-Wave, and here you can see we are having the binary values here. Now let me click here at the beginning. You can see 4 are 0 right here, then here 0 1 1 0, and then here if I click 1 0 and sum and carry will be 1 0, and here 1 1 and it is 0 1. So this way, if you just try to probe by clicking here, here and here at 4 points, you will get the corresponding binary values from where you can construct the truth tables for the input and outputs, that is A, B and sum and carry. So the truth table is also correct here to the graphical form, and here we are done. Hey guys, welcome back. In today's episode, we are going to discuss these below points. Verilog modeling methods. Next, we will introduce the concept of behavioral modeling through procedural statements. Next, we will go for the theory and example of initial and always procedural blocks. Next, we will do the procedural modeling of 2 to 1 mux. Next, we will design its test bench to check its functionality. Next, we will do the code simulation by the combination of Geany, Icarus Verilog and GTK-Wave for waveform viewing. Next, we will do the code simulation with the help of Vivado 2022.1 ML edition. So we will side by side use two different simulators to simulate our mux and its test bench. So that's the menu for today. Without any further delay, let's begin. Verilog modeling methods. The Verilog modeling types are subdivided into two different parts. The first one is structural modeling, which we have already covered, and you know that it is done through the gate primitives. The next one is the behavioral modeling. One subpart of it is the continuous assignment, which we have done in the last episode, and in today's episode we are going to talk about the procedural assignments. So we are done with this particular slide. Let's move on to the next slide. Introduction. The behavioral modeling is majorly done by procedural coding. Now here, if you look, it has two parts, procedural and coding. The coding here is nothing but the Verilog A coding, and the procedural we will come in a short while. This kind of modeling has similarity in coding style with the Perl coding or C style coding. So in case you are either familiar with Perl or C language as a programming or a scripting language, you might be aware with the procedural method of coding, which is a very stark difference with C++, which is a object oriented, or Python. both of which are object oriented. This way, you can identify the coding style is a procedural one in case you have previous familiarity. However, the transient simulation is done here in contrast with the Perl or C language. So, this one is the difference between the programming language or scripting language and the Verilog language. This difference is the fundamental difference between the two types of procedural coding. That is, the first one is this and the second one is the Verilog. Conditional variation of output with respect to the input are captured with the help of if-else blocks. So the if-else is a very common construct in any programming language. This is, I think, the first conditional block that you encounter in any programming language, and in Verilog we do have it and we use it in the procedural coding. Definite set of input variation are captured through CaseX and CaseZ blocks. So generally in C language or Perl, you will have only case. So this you will find in Perl or C. However, in Verilog, you have two more, that is CaseX and CaseZ. We will come in detail in some later episode. Looping procedure technique are achieved with the while, for, repeat and forever block. So these two, while and for, you are very much familiar if you have done the C coding or the Perl coding. Now the repeat and forever, these two are new concepts in Verilog. In later episodes, we will get familiarized with these two type of loops. All the initialization of data are done through the initial block. In any of the circuit, the initialization, that is the boundary condition, the first boundary condition that we do is done in Verilog through the initial block. In a circuit, the boundary condition, that is whatever condition that the values what should be there before starting the operation, is very important. So these boundary conditions are set by the initial block. Dynamic initialization and change of variable values are captured by the always block. So initial is done at the beginning, so it is done, purpose is done. But while the transient simulation is going, in case you have to dynamically initialize or you have to change the already initialized variable, you have to take the help of the always block. We are done with this particular slide, so let's move on to the next slide. Initial and always procedural block. Initial block starts at t is equal to 0. Execute only once. Generally used in the test bench. Initial block is not synthesizable. Initial block. So remember this thing, this initial block start t equal to 0 and it execute only once. So this is the specialization or special thing of the initial block, and this block is non-synthesizable with respect to the Verilog synthesis. This is a very important point, and the greater use is found in the test bench. So in last couple of episodes, you might have come across the test bench, and there you have seen the initial block has been used multiple times in each of the different examples. There can be multiple initial block in the design. This is a very usefulness of an initial block. So initial block initializes the things. However, we can have multiple initial block. Everything will be starting at t equal to 0. Remember this thing. How many initial blocks are there? However, they will start at t equal to 0. Always block starts at t equal to 0, executes in a continuous loop. So this is the beauty of always block. Always means it's a always on block. It runs always. That means it happens in a continuous mode. Block execution is triggered based on user specified condition or sensitivity. So the always block for execution, it needs some condition or sensitivity. Generally, there is a @ symbol and then we have a bracket here, and inside that we will have the condition or sensitivity in always. Here is an example. So here is the always. So you can see it's written in green and it's a reserve keyword and pausage of clock. So here the off is not written here. However, when we are reading the code as a human being, we can read it at always at the pausage of clock. So at means at is a time related event. So whenever we have a clock transition like this, so this is a pausage, right? So this pausage and this pausage. At this pausage, the always block will be sensitized and whatever things are written here inside this block will be executed. Again, at the next pausage, this block will get executed. And remember, if anything changes negative edge, that means here inside this code, that will get implemented in the pause edge. That means this is the first, this is the second, and here something does change, so that will get reflected in the second pause edge. Hence, the always block is a very useful thing for the hardware description. The procedural blocks are automatically activated at time equal to 0. So this is a very important thing. Everything starts at time t equal to 0 because Verilog is a transient simulation and time always starts at 0. All the procedural blocks and their internal statements are executed concurrently. So this means we have statement 1, statement 2, statement 3. So this will start at time equal to 0. This is start at time equal to 0, and this will also start at time equal to 0. So this is the concurrent operation. Remember, this is a stark difference from the programming language where every statement is executed sequentially, one after another. So in sequence, this one will happen first, then the next, and then the next. However, in Verilog language, in the procedural blocks, the statements are executed concurrently. That means at time t equal to 0, this will start, and this will start. So everything will start at t equal to 0. Or you have a different like pausage of clock, and that time all the statements will execute. So at any of the sensitive points or the condition, whether if it is coming in the always or if it is by the initial block, then at time t equal to 0, it will be executing. Reg is the main data type that is manipulated within a procedural block. A procedural block has data manipulation, and reg is a very important kind of data type here. And why? It holds the value until replaced with the new value by a new assign statement. We have already come across the assign statement, and it's a very short and sweet way of assigning value to a variable. And the reg is the kind of data type that can hold the value until a new assignment comes into the variable. So we are done with the initial and always procedural blocks here for their introduction. Let's move on to the next slide. Initial block, we will see couple of examples here. Here, first we have the definition. Initial block, then a single statement, and then if we have a multiple statement, we will have the initial, then the begin, and multiple statements will come and it will closed by the end statement. In case there is only a single statement, we don't need the begin and end as here, and in case you have multiple statements, then begin and end will be there to encapsulate them inside one initial block. Here let us see some examples. We write some module name behavior. It's a rough name, so just you don't think of any hardware. It's just a name for understanding. We have reg 1 down to 0 for A and B, and we have initial begin here. We have A equal to 2 tick B 1 0. So that means here you can see A is 2-bit Y bus, and here the 2 bits of A are assigned by 2. 2 means we will have 2 values. B is binary, and 1 and 0 are the binary values that will go inside the A. And after the delay time 20, B is assigned with 1 1. And here we close the initial block. Here we have the opening, and here we have the closing. Again, we have another initial block here, and here after 10 time unit delay, we assign A with 1 1, and after 20 time unit delay, we will assign B with 1 0. Here we end our second initial block. So this is the opening and this is the closing, similar to this and this. Next we have initial, and we have a finish statement. So I think this will be a $finish, and here is a typo, so please excuse for that. Generally it will be a $finish, and because this is a system command, it will finish up the run of the simulator. There is a typo, please excuse me for that. And here we end module. So here you can see this is an inline initial statement. We don't have begin or end here because this is a single line inside this initial block. So here we have seen that hashtag time adds a time spacer and advances by the transient simulation by time unit. So here it advances by 20 time units, here it advances by 10, here by 20, and here by 50. So if you add them, so this plus this plus this plus this will be the total time for the simulation. So here if we have the time in the x-axis, if we add all the values, it will go to the final t, that is t dash. And here all are marked. And here we have seen the example of multiple initial blocks. This. So we have come across 3 different initial blocks. And also we have seen reg reassignment here and here. You can see initially it was assigned and later on you can see the reassignments are here, because here it is time t equal to 0 the assignment and it is reassigned here, and you can see here it is reassigned. So you can see that the assignments and the reassignments are happening through the initial block. So here we are done with the typical definition and example of the initial block. So let's move on to the next slide. Always block. Let us see through the example. Here we first have the definition. So here the syntax is always, then we have a @ sign, and within the first parenthesis we have the sensitivity list. So anything comes here, any number of sensitive inputs that will be here, that will come under the monitoring of the always block. And here goes the statement. So this is a single or inline always block. And in case we have multiple statements, we will have always, then @, then the sensitivity list. And remember, this is a list, so there can be 1 variable, 2 variable, 3 variable as per our design need in the sensitivity list. So it's a list. And here we have the begin to open up the always block. And here we put multiple statements and close it with the end keyword. So this way the multiple statements are encapsulated inside the always block. Here let us see some example. Non-synthesizable because of delay element. This you have to remember. So here it is a typo. It's a delay. DL is missing here. So delay statement. So here always we have #10 clock, and then we have clock inverse. So this is a inverse sign. This one is the inverse sign, which is equivalent to a Not-Gete. That means after each 10 time units the clock will toggle. Next we have the synthesizable format. Always @ posage of clock or negage of reset n. So here you can see or. So this is a conditional operator. So either this or this will sensitize the always block codes written here to execute. We open up the codes by begin keyword and we put if rstn and we have a bang in front of it. That means it's a negation. And then we have this is another kind of operator, we will come later. Q equal to 0. Else if D, then again we have another statement here. Else we have another separate statement. So this way we are going through the if else conditions and we end it here. And the next one is the end, which ends this particular always block. And in the next line we begin with the next always block example. Here we again have the keyword @ symbol, and we have A or B or C or D, 4 sensitive variable list here, and we begin the always block by the begin keyword and we put here by this particular statement, and then we end the block. So here there can be multiple lines within this particular always block. And here we have just came across the multiple always blocks. So this one is one example, the second example one is this, and the third example is this. So we have done 3 different examples of the always block. This is just for your knowledge. Right now you don't have to go into the logic and find the digital output. Just you get familiarized with how the always block is written. There are 3 typical examples are here. Those will help you to understand the always block. And here this is a non-blocking statement. So this is not equal to, so this is called a non-blocking statement. So in later episode we will also cover and we'll go for the typical details, and we also will cover the differences between the blocking and the non-blocking statement. So this one is a blocking statement, is equal to, and this kind of arrowhead and then equal to is called the non-blocking statement. So we are done with this particular slide. Let's move on to the next slide. Procedural modeling, 2 to 1 marks. So here this thing comes, and here circuit of 2 down to 1 marks. And here you can see the circuit. It's a typical symbol. Here we have input A, input B, the select switch S, and the output is Q. So this kind of structure is called the marks. Generally this kind of symbol is used for marks in a digital circuit drawing. Now let us write the code. First we write the module statement, and here we give a my name 2_1 marks. So here we have all the inputs A, B, S, Q. Here in picture we have written all the variables in upper caps, whereas in our coding we have used the small caps. So this is a difference between the picture and the code. Input A, B, S. So these 3, these 2 and this one are inputs. So we have written input keyword and we have placed A, B and S against it. and we have the output Q. So Q is the output, and we have defined the type range for this because this will help in procedural assignments or reassignments as per the change in the A, B or S. Then we have the always block. So always at the rate A or B or S. Now this always block monitors this one, and this one. For any change in either this or this will trigger the entire always block to get executed. Here we write the begin keyword. Here we have written it in the next line. We can do that instead of writing it here. If A is equal to 0, we have assigned Q with A. So S for 0, A will go to Q. So this one. Else if A is equal to 1, Q will be assigned with B. So this one will be output in the Q. This is a mux logic you have already came across in your digital electronics, and this way we are coding it inside the Verilog. And here we write end, and this is the end of always block. This end here ends the always here. So it is the beginning and this is the end. So here the code is encapsulated inside the always block. Next, we use the end module here to close the module. Here we have used the same name here as a inline comment because in real-time Verilog code in the industry there will be multiple Verilog modules. So if we do not put this tail comment as for a human reading, it will be difficult for us to identify which particular block is ending, which particular module is ending. So this is a good convention, you must follow it. So here we have done the coding. Let us move on to the next slide. Here we will do the test bench with the procedural modeling for the 2-to-1 marks. So here we start our code, a test bench. So we have a comment test bench, and then we write our module name as test my 2-to-1 marks. Next, we have the register type defined for the A, B and S. Now here if you understand that this reg type will have to hold the value until our next particular time event. So we are defining A, B and S with the type reg, which is a bit different from the previous code. That means the module definition. Here we write where as Q because as the regs are calculated, the exact calculation will go into the Q. And we here write the initial begin, and here we first write the system command down file, the VCD file, we given the name here, and down where. So this will dump all the variables, that means all of these variables here into this particular VCD file. Next, we write the display command. This is nothing but a printf command, and this will give the column names for all these variables. And here we write a monitor command. This is a more dynamic printf command. If any of these 4 or 5 variables, here 5 variables we have, time, A, B, S and Q. Anyone if changes, right? At that point, all the values will be printed here, and all the values are tab separated as per this particular display statements. So this will print a good truth table in the screen. Now, in the next part of this test bench code, we add our stimulus. So at time 0, we are using a concatenated version of the assignment here with the curly braces, and here 3 means we have 3 variables here. P is binary, and we give 0, 0 and 1 to this and this variable. So this way in one go we assign 3 values to the 3 different variables. Next we have assigned the 0, 0, 0, and this way we keep on adding and adding and adding, and we finish here at 90. So here you can see here it is correctly written $finish. So you can see here we have written all the combination for input variation, and this input variation of the truth table will trigger the monitor command to measure the outputs and construct a truth table with these 2 print commands. Here we end our initial block with the end command. Next we have the instantiation of the marks that we have done in previous slide. So here we have the name of the module, and we have the instance name here, and we have given connections to the ports, and we have kept the name same to make the port simple. Here we use the end module keyword to end our test bench module. In our actual code, these two codes are written in the same file so that we have lesser complexity of running the code. However, they can be written in separate files. So we are done with this particular slide. Let's move on to the next slide. So we are done with this particular slide and let us move towards the code simulation. Hey folks, we are in the directory. Here we have kept the Verilog code for the 221 marks, and let me open a terminal here and let me launch Geany. Here is our Linux terminal inside Geany, and here you can see the code. So here is the module of 221 marks which we have discussed in slides, and here is the test bench. You can see in the same file we have kept the module as well as the test bench. So we will use the Icarus Verilog to simulate this particular code. Let me do a ls here and let me type iVerilog. This is the binary for the Icarus Verilog, and we have our 221 marks.v here, and let me give a output object dump name as marks. The simulation has generated the executable .marks, and let me execute this object dump. Here you can see the marks input variation has been printed, and here the output is printed. So let me correlate them with the test bench. Here you can see the input variation is put here using our stimulus vectors, and this has been captured here, and the time variation which we have done using the hashtag statement has been printed under the time column. So, and you can see these two print commands have been helpful for printing the entire truth table, and here you can see that the output is created according to the marks operation. So let me pick up this one. Here you can see A is 1, B is 0, and S is 0. So A will be picked, and you can see the A has been picked here. Let me pick one opposite case. Here you can see here A is 0 and B is 1, and we have S equal to 1. So in this case B will be picked, and this one is going to the output. So in this way, with the investigation, you can understand the input output relation that has been tested using this particular test bench and has been dumped here using the simulation with the Icarus Verilog. Now let me do a ls. Here you can see a VCD file has been created. So let me launch the GTK-Wave. So here you can see our marks instantiation is there. Let me one by one put them in the window. Let me use the fit screen. So you can see the entire timing simulation has been captured for all these inputs, that is A, B, S and Q here. So if you take your marker here, 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 you will see a change here. Let me do it, and you can see in this way, if you progress like this, you will capture all the states from the waveform. So if I put the marker here, there is this value. If it is here, it has this value. If it is here, you can see I am moving it and the values are changing here. In this way, putting a marker like this will help you to investigate the values here. Also, we have graphically shown you the marks data checking from the VCD file, and we are done here with the GTK-Wave. Let me close it. So here we are done with both the Icarus Verilog simulation using the Geany IDE here, and then we have done the VCD file exploration, that is the graphics waveform output we have checked to the GTK-Wave. So we are done here. Now let us move on for the Vivado simulation. So let me launch the Vivado here. So here you can see that the Vivado has started to initialize for the launch. It is starting the GUI. Splash screen has hit the screen. And here you can see our Vivado interface is ready. So let me create a project. So here we click next. Here you can see the project name. So let me change it, and here you can see the path is correctly displayed. Here we have kept our Verilog code. Also we have chosen create project subdirectory. Next, here we select the RTL project and do not specify the sources at this time. These two options we have checked here. Next, let it keep here, all will be as default, and let me go to the board and select one particular board and hit OK, and we hit next. Here you can see new project summary has been given here. So the project name will be created and this board is used. Although we are not using any board at this moment for this Verilog simulation, however this interface for Vivado gives you the facility to use a Xilinx board. Let me finish here. So let me go for this option, add sources. We will pick the option add or create design sources. Since we already have the code written in the file, let me add it. Here you can see the code. Let me pick it, and here in the right hand side you can see the code preview. So this is the correct code. And here we click on. Here the next thing, let me see the source file here. In the right hand side editor, you can see that the code is written here. In the next stage, I will use the run simulation. We will check this option and we click on run behavioral simulation. So here you can see the test bench is here, the vectors for the input stimulus changes, and according to that the truth table has been printed. Here is the time and rest of the input A, B, S and Q. So you can see here is the shift in the white space for this couple of values, and then there is a shift here. So this is because of the character management of Vivado. So you can see and you can check by yourself, right? Let me pick this one. So here you can see A is 1, B is 0 and S is select. So select, if it is 0 it will pick A, and it has picked 1. So it has done the picking up correctly. And here in this one you can see, right, A is 0 and B is 1 and select is 1. So select will pick the B, right, and it has picked the correct one, that is B. So this way you can verify the truth table for the 2 to 1 marks. And here you can see that all of these input truth table combinations have been correctly executed by the Vivado simulator for this truth table. Now let me open the web form and let me hit the fit screen. So here you can see the input A, B, S and Q has been given, and if you put your marker here at different points you will get the change in the value here. If you go keep on doing this for all the points where you can see visually, you can actually get the truth table of this circuit. So let me show you here. You can see it's 0, 0, 1, 0, and here if we progress our monitoring point and values are actually changing here. This way you can check the values from the graph, that is the graphical font, and here using this kind of marker you can get the exact binary values of all these inputs at any particular time. So from that you can also create the truth table and you can verify the design's functionality. So folks, here we are done with the Vivado simulation. Hey guys, welcome back. In today's episode, we will be discussing the below points. Introduction to the assign statement. Multiple use of assign statement. We will talk about the rules we should follow while writing an assign statement. Next, we will do some variations which are acceptable in Verilog for the assignment statement through example. So that's the menu for today. Without any further delay, let's begin. Introduction to assign statement. Any assignment in Verilog is done using the reserved assign keyword. This one is a library reserved keyword. While we talk, we mention that assign, and in actual library we also have a reserved keyword assign for the same purpose. The LHS of any assign statement must be scalar or vector in nature. So generally any assign statement will have a equal to sign, and there will be a right hand part and a left hand part. So this one should be always a scalar or vector in nature. So this should be scalar or vector. In data flow modeling, this keyword is used for continuous assignment. In one of the last episode, you have encountered the data flow modeling in detail, and there we have used the continuous assignment, and there we have used the statement assign somehow like in this manner. Here you can see the example, and this is a forever declaration. That means once we declare it, it remains true for the entire stretch of time when the Verilog simulation is ongoing. As you know, the Verilog is a transient simulation in nature. As I mentioned, the continuous assignments are forever. That means we have a time axis t, and from t equal to 0 to t equal to t1, the entire stretch, this equation will be valid. So this will be valid for this entire time stretch. Assignment can be both explicit and implicit. So just focus on the word explicit and implicit. Explicit means we write it in detail, and implicit we do not write in detail. So let me give some example. So here first we define where a, and then we assign a with the logical equation on the right hand side. So here this is called a explicit because here we have used the where keyword, we have used the assign keyword, and explicitly we have mentioned everything. So now let me give the implicit example. Here the same thing can be written as where, then a, then equal to sign, and then the expression on the right hand side. So here you can see the assignment operator or the assign statement. Here this keyword is missing in this particular equation. Here even we are not mentioning the assign keyword here in this equation, although we are serving its purpose. So this is a implicit expression for assignment. We will continue in the next slide. So let me change the slide. Delays can be inserted using assign statement. So how? Here the assign, then we give the hashtag delay, the number, and this is 20 time units for which the delay is inserted, and then the expression here. This delay will occur on this expression. So this means these two will be delayed to be assigned to this by this 20 time units. In procedural modeling, assign statements update variables declared under reg, integer, real, or time data types. So this, and this are 4 type of data types. And here we are talking about the procedural modeling, that is the procedural behavioral modeling or behavioral procedural modeling. So here these 4 data types are assigned with the assign statement. The value contained in a variable is kept intact until it is reassigned by another assign statement. Here we have used the assign statement and we have given a value. It will be kept intact until the next occurrence of the reassignment. That means with some logic or some procedure or something, it will be kept intact. And this thing could be combination of explicit or implicit. So in the first one we have assigned it with the explicit, and the later inside the procedure we have used the implicit. That's okay. So there could be permutation and combination of these things. However, whatever value we have assigned, it will kept intact and it will change only at the next reassignment. LHS of an assignment statement can be a single, where, reg, integer, real, time. All this data type can be in the left hand side of the equation. So this is LHS and this is RHS. So here there could be this type of datas or data types. The variables could be this, and generally the LHS is called a target. It could be a bit select of a bus. So here we have defined a bus, or part select of a bus. That means here our part select, the bus is greater than 2 down to 0. The bus may be 4 down to 0, and from which we are picking up the 2 down to 0. So it's called a part select. So it's a part of it. So this could be on the LHS. And concatenation of the both. So these things, whatever we have discussed, they could be concatenated using the parenthesis. So this is a concatenation operator. Here I have generically used 4x and 4y. This could be anything as mentioned above, and the concatenation operator can stay in the left hand side where the right hand side can contain something else. This kind of expression you are expected to handle in Verilog. So we are done with this particular slide. Let's move on to the next slide. Multiple use of assign statement. Here, first, let me give the structure of assign statement. As per the Verilog LRM, this expression is written as assign first the keyword, then the target expression, which is at the left hand side, and the right hand side, there will be drive strength, how many pins it can drive, the delay, the hashtag time delay we have already discussed, and finally the logical expression of signals or constant values. So there could be variable or constant, and they are combined in terms of an equation. These three things, 1, 2 and 3, this can be on the right hand side. So at the left hand side only there will be a expression, continuous assignment and procedural assignment. These two are the main division of application or implementation of the assign statement. We have seen in last episode. I will bring up those examples here again just to pinpoint things in your mind. So this is our continuous assignment example. Half adder circuit. So we have here the module definition, half adder, and we have the A, B, sum and carry. Then we have defined as input A and B, output the term is where, data type is where, then sum and carry. And we have used the assign statements here to define the half adder functionality. And here we close. You can see these two expressions will be, so this is a time axis T, and whatever could be here, the responses, we can add plots here as you have seen in the plotting tools we have used in last couple of episodes. These two will be valid till the time t dash. So t dash is the finish time. These two expressions will be valid, and this is a continuous assignment. So here we are using the assign statement. However, we are doing the purpose, that is a continuous assignment. Once you take these pictures into your mind, you will be able to decipher any already written Verilog code once you are working inside an industry. So whether it is a continuous assignment or a procedural assignment. When you are working as an individual and you have not entered into the company, these things is a learning purpose, but once you enter an industry, there you might have to go see through already written codes, and there you will be able to differentiate between the two types, that is the continuous type and the procedural type, using this example shown in this particular slide. Let's now move on to the procedural assignment here. Here circuit of a 2 to 1 mux we have already discussed in last couple of episodes. Next we have the module definition, that my 2 to 1 mux, and we have A, B, S and Q. Then we have defined the inputs and outputs A, B, S, and we have used the reg type data for Q, and we start our always block here at the rate, and here we sensitized A, B or S. Any of this becomes sensitively changed, then the inside operation of always, whatever we are writing here, will be executed. We start with the begin and we write if S equal to 0. Then we assign A to Q. This is a non-blocking assignment, which we will talk in the next episode. Else if S equal to 1, then we go for Q assigned with B, and then we put end, that is the end of always. So here is the begin, here is the end for this always block. Here you can see this is a procedural assignment and this is a procedural assignment. So here, while this is a procedural assignment, it is kept under the procedure. So this is the procedure, if else procedure we have kept inside this, and hence it is becoming a procedural assignment. And here these are pre placed assignment, and hence these are not procedural, these are continuous. So they don't come under any procedure like this, they become independent and hence become continuous in nature over time. And here we end our module with the end module. So by looking here, you can see this one is a continuous assignment and here this one is a procedural assignment. So side by side you can see the difference in between these two. And now when you are visiting any code already written in the company what you have joined, so there you will be able to differentiate between those, whether this is a procedural assignment or this is a continuous assignment. We're done with this particular slide, so let's move on to the next slide. Assign statement, rules to follow. The LHS of any assign statement must be a scalar or vector in nature. Scalar means we have a single bit and vector means we have a bus that you can easily relate as you are a student from electronics. Scalar means it's a wire and vector means it's a bus, that is a collection of wires. A reg can be assigned only in initial or always block. So a reg is a particular data type which is only attached to initial or with the always block. RHS can contain scalar or vector registers and function calls. So the RHS, that is the right hand side, generally we have an equation. So left hand side is a target and right hand side is our expression. Whatever expression we have, build the logical expression or constant or variables, whatever. So the RHS here will contain scalar or vector registers and function calls. Function we will cover in some later episode, and there will be task also which are side by side as a special thing which you cannot find in C, but you can find in Verilog, a stark difference between a function and a task, and we'll talk about their similarity and dissimilarity in some later episode. Whenever any operand on the RHS changes the value, LHS will be updated with the new value. So here we talk about the equal sign. Right hand side, anything changes, it will be stored in the left hand side value immediately. That means immediately with time, whatever time t dash the things is changing on the right hand side, it will be assigned to the left hand side value. This value goes and stored into the left hand side variable, whether this is a scalar or a vector. Assign statements which are always active are called continuous assignments. So we have exemplified in last slide, and the continuous means they are always active. So if they are not inside some procedure blocks, procedures are sub blocks inside the code, and only once we reach or enter inside that block, the procedural code or assignment statement will execute, else it will not touch the code. So the assignments which are outside of this kind of blocks are called the continuous assignments. And generally we have two types of modeling here, and we have discussed this in last couple of episodes, so these things are very clear. Here we are just rephrasing the things about the assign statement so that you have a clarity and you don't get confused over the different usage of assign statement. We're done with this particular slide, so let's move on to the next slide. Assign statement variation. We will go through couple of examples, and here we will talk about a module, and here we did not try to write any particular expected kind of digital functionality. Rather, this is an example, take it as this. So here we will give some variations, and you must focus on the variations and not as a module. Hence we have written the module XYZ and we have given the input XYZ. Input X is a bus, it is 3 down to 0, it's a 4-bit vector, and Y is a scalar, 1-bit scalar, and output is a bus, that is 4 down to 0. Z is a 5-bit vector net. So if you can see, 4 plus 1 is 5. So this way this is written. We write where 1 down to 0 A and where B. And here we use a assign statement. Here we can write Z. Z means this is 5-bit vector. So we have concatenated X and Y directly into the assign statement. Next, we have used this bus 3 down to 1, which is a part select, and we have concatenated X and Y and pushed this thing, concatenated thing inside this part of the Z. Next, we have the same repetition here. It's a typo. Sorry, folks. Next, we have the Z4. We define with 1. So we are defining only a bit with a constant. Here you can see Z3 down to 1, XY. I think this is same again with this one. It's a typo. And here we write Z3 equal to 0. So we are doing a bit assignment, that is this particular bit of the bus is assigned with 0. Let's move on to the further assignments. Next, here we write assign Z3 down to 1 as XY, assign Z3 equal to 1, assign Z with X down 1 down to 0 and Y. This way also we can write. Okay, this way we also can write that 1 down to 0 and this is Y. As I have mentioned, this is a kind of variation example. This is not a real module, so don't focus on the output. Just think on how we can do the assign variations or the acceptable assign variations here. So here we have written assign Z2 down to 0, then X1 down to 0 and Y1. So these two has been concatenated and pushed into the Z. Here we have written assign Z with the Y. Next we have assigned A and B together with X and Y. So here you can see A and B. Here on the right hand side we have X and Y. So X and Y, these two have been concatenated and pushed into concatenated format of A and B. So they have been assigned. So these are acceptable variation, and don't go for the exact meaning, because this is, again I am saying, this is not a proper digital module. This is for an example. Next we have assign, I think this is the same and repetition, sorry for the typo. And here we end module. So we have seen here we have different kind of assign statements throughout this. What type of assignments can happen in a real case? Here we have done the variations. We have taken a dummy module and we have taken dummy input and dummy output. And here these are also dummies. So these are not real case or real module. However, we have just tried to define inside the Verilog structure how these variations can happen here and here. So all the variation you have seen. So these are acceptable variations. Now let me also add another thing here. This one down to 0A, and this is explicit assignment we have already discussed. However, I mentioned here again, and here we write the same thing as a implicit assignment. This kind of assignment plus this kind of assignment, the explicit assignment. All these kind of variation you can expect inside Verilog coding. Here we have generally used the assign statement inside as a continuous. However, in a procedural, this kind of variation can happen provided there is a procedural block inside which we are putting these assignments, these or these or these. So these are going in a procedural block. In that case, this will become a procedural assignment. Otherwise, we don't have a procedural block anywhere in the code and the assign statement is outside of that, then this is a continuous assignment. Let us summarize whatever we have discussed so far. The assign statement to be used both outside and inside a procedure can create confusion to an end user. Outside or inside the assign statement. So this is the two positions where we can expect. That means outside or inside of a procedure, a assign statement can stay and it can create a confusion to the end user. That means you as a learner or as a proficient Verilog coder in the VLSI industry. To get out of this confusion, please remember that Verilog has two forms of the assignment. Continuous assignment placed outside any procedures in the data flow modeling, and procedural continuous assignments placed within a procedure in the behavioral procedural modeling. So these are two types of modeling, behavioral and data flow, right? And in one we have continuous assignments, another one we have procedural continuous assignment. That means the assignments are put inside a procedural block. Continuous assignment statements are separate processes that are active throughout the simulation. These continuous assignments are unconditional and they are active throughout the entire time stretch or the simulation is going on. Procedural continuous assignment statements become active when the assign statement is executed in the respective procedure. So once we reach the procedural block of a code, right, inside that there is a assign statement written and that becomes executed only the block of code is called upon. So this is the two difference. So it's a conditional reach. The simulator will reach here to the assign statement conditionally, and here in continuous it is reached this assignment unconditionally and for the entire time stretch. So this is the difference, and I think we have summarized our discussion here. Hey guys, welcome back. In today's episode, we are going to discuss the below points. Introduction to blocking and non-blocking assignments. We'll use infographics to differentiate between the blocking and non-blocking assignments. Next, we will talk about blocking assignments and the mechanism by which it blocks. Next, we will talk about non-blocking assignments and its mechanism. We will go to thorough examples of blocking versus non-blocking examples apart from the small examples which we have given in the above points. Next, we will give a quick and to the point rules that you can follow while you are designing in the Verilog so that you properly choose blocking and non-blocking assignments in a proper fashion. Next, we will summarize our discussion, and finally, we will go through some hands-on code which are not shown in the theoretical slides and do their simulation using Verilog and Vivado. That's the menu for today. So without any further delay, let's begin. Introduction. HDL such as Verilog have a striking difference in defining a value of a variable as compared to its programming language counterpart such as C language or Perl. In C language or Perl, two consecutive value assignments are as per the line-by-line execution of code. To focus on this thing, line-by-line execution of code. So this is the fashion in which the C language or the Perl works. Hence, in the C language or Perl, the playhead is the line counter. So what is called a playhead? So when you are playing this video, right, over time, a marker goes on from left hand side to the right hand side. So that is called the playhead. In C language, this playhead is vertically down, or in Perl, it is the same. So that playhead plays the code line by line from top to the bottom. Also, the playhead can hover around the code by calling a function, subroutine, or named code blocks. These are some exceptions where the playhead can start here and go up to this point, and then it jumps over to another point where there is a subroutine, and then it goes back again to the main code execution. So this is the concept of the playhead in the execution of the code for C or Perl. Now we will go for the striking difference which we have mentioned in the first line for the Verilog. In Verilog, the playhead is the time step during the transient simulation and not the line number. So this is the very much fundamental difference. So in Verilog, the simulation can happen over time and your wave is going through like that, any wave. So I have not drawn a digital wave. If I am writing a digital wave, then it will go like this. And in this case, your playhead goes from left to right, from this direction to this direction. So this playhead is the time wise. That is, this is a transient simulation which we are talking about. This is a transient simulation and not the line number. So in C, the playhead is as per your code line by line. However, in Verilog, it is as per the timeline marker of the simulation. In Verilog, we do have the named code blocks. We will cover it in some other episode. However, in that case, the jumping will happen inside the code and jumping back to the original point of execution will also happen. Hence, two separate code blocks, like two initial blocks, which you can easily write, staying far apart in the entire Verilog code can get executed parallelly. So this is the line of code. Here there is an initial block and here there is an initial block, right? So this and this can happen parallelly because your code execution is timeline wise, and in timeline wise at this timeline, this and this initial block will happen because the initial block is executed at the beginning. So rather at this point. So here this will start executing. So this is the fundamental difference between the C language or Perl and Verilog. So the playhead in the two, one is line by line code execution, and here in Verilog the playhead is the transient simulation. For this temporal nature of Verilog simulation, there are two types of assignment operators. One is a blocking assignment, another one is a non-blocking assignment. You can remember in C or Perl, we only have this kind of operator and we do not have this kind of operator. This is called, in C or Perl, it is called less than equal to. Here it is a non-blocking assignment. Now the temporal behavior is nothing but the timeline wise response of Verilog. So this is called the temporal nature. To accommodate all that temporal feature or the transient nature of Verilog, we have the blocking and non-blocking assignment. Generally, the blocking assignment is suitable for combinational circuit logic of digital design. Combinational circuits, you know from the Carnot mapping and POS and SOP, you can design a combinational circuit. In earlier episodes, I have shown you how you can code a combinational circuit to various types of Verilog modeling. Whereas the non-blocking statement is used for sequential circuit logic of digital design. So you can see that the non-blocking is meant for sequential logic and blocking for combinational circuit. So this is a very straightforward thing to remember. Also, the non-blocking assignment allows designer to describe the state machine which update without needing to declare and use the temporary storage variables. So at some later episode, we will cover the state machine, and you can find familiarity with your already known circuits where the state machine is applicable. This is used for designing complex digital circuits and their states. There the non-blocking assignment is very useful. So for advanced VLSI design, the non-blocking assignment is a must. So here we are done with this particular slide. So let's move on to the next slide. Blocking versus non-blocking assignments. Here in this slide, we will use infographics. We will use infographics to draw a split difference inside your mind about the blocking and the non-blocking assignment. So here is our separator. At left hand side, we will have the blocking example, and in the right hand side, we will have the non-blocking example. So here you have a picture of a switch you are turning on, and you have connected a wire to a light. In this picture, how this signifies the blocking assignment. Here you can see this small cartoon character is plugging in or directly connecting the two wires of a light, which is a output, and here the switch as the input. So when both are connected in a direct fashion, that means if you turn this switch on, that will go, the instruction will go through this wire and turn the light on. So this is a very simple way to understand the blocking statement. That means the blocking statement directly assigns a value to a variable and make it fixed, make it like a constant. Now let us move on to the next infographics for the non-blocking assignment. Here you can see there is a conveyor belt, and in the conveyor belt is changing with time, because here you have different boxes with different articles that are coming in and they are going in a direction. Once this is inside a company, you have a counter where some processes are going on, and here the boxes are staying for a while, maybe for a labeling, maybe going for a destination. So it has to wait here for some kind of functionality, and it has to register here that this parcel will go out. And next, this whole thing comes to the final delivery point where our mailman is picking up the package for the delivery truck. So this is an explanation of how this picture is working in a real life. Now let me draw the similarity with the non-blocking assignment. Now here you can see the connection is very much direct. However, here whatever you are getting here as the delivery box, which is here, that is not directly what you are getting from here to here. So there are a lot of time steps, 1, 2, 3, everything will go through this checking. Here this acts as a playhead. Through this playhead goes, it passes on, it puts on the labels and everything, destination and etc., and then it comes to you. So here this thing cannot cross, this particular box cannot cross all these boxes and directly come to here before this thing. So this is a kind of concept of the state machine where different state will be executed in a particular sequence, and in known sequential logic, right, where we are using a shift register or a register, there you can see the data traverses inside the sequential circuit in a particular manner. So this is the time-wise simulation, the time axis for the non-blocking, whereas this one acts as a playhead, right, this box, the counter where everything is labeled and sealed and checked and verified, so that acts as a playhead. And no matter you try, you cannot get this box here directly at the output counter. So this way the non-blocking assignment works. That means it has to follow a sequence. That means whatever is here, it has to be labeled, whatever here it has to be labeled, whatever here it has to be labeled, and this one is labeled, right? This operation, this labeling operation or checking operation, whatever you are seeing here, you will see in next coming slides. So that is done in the non-blocking mechanism when I explain with equations. That time this picture and the left side picture will be very clear to you. You have this picture in the video, so you can go back and use chapter to come back to this particular slide once you already traverse in the explanation in the later slide. We are done here, and you have a glimpse right now. As we progress through the entire discussion today, you will understand why there is a difference between the blocking versus non-blocking assignments. Blocking assignment. Here we will talk about the blocking assignments. Blocking assignment or statements are continuous in nature, that is the same fixed hardware circuit connection. Here I have used a word hardwired circuit connection. Now you can correlate with the picture that I have just shown in the previous slide. This blocking assignment is a continuous in nature. Whatever we called continuous is analogous to the hardwired connection in the circuit. So continuous in the Verilog code means it is hardwired in the actual circuit. If you made the circuit on breadboard, blocking assignments literally block the execution of the next statement until the current statement is executed. So the blocking assignment will not allow for any parallel execution which happens in the non-blocking. You will see later. So you have to wait for some time for the entire explanation to come in front of you. Consequently, blocking assignments result in ordered statement execution. So whatever the blocking statements, they will execute one by one, obviously with the same as the playhead. Remember that. Here this ordered execution is not same as the ordered execution of C or Perl. This is in ordered execution of the timeline playhead. Example, we go for a short and sweet example here. We assign A equal to B equal to 0 separately initially. Then we assign A equal to 1. This is a blocking assignment. Here the B still holds 0. Next we assign B equal to A. Now A got assigned to B, and finally we have A1 and B1. Finally after the ordered execution. So the executions happen here first, then this, and then this. So it has a sequence of happening from this to this as per the playhead in time. Why I say the playhead in time? If we include here a hashtag delay, right? So the time playhead will wait for the delay to pass on and then it will assign. Here by the delay you can see that is by the playhead in time. Otherwise all the statements will be in a same timeline point and the playhead will play all together them in once. Digital circuits which have a race around condition in its truth or state table. State table is a term which you will find in the .lib VLSI world, the .lib or the timing.lib or the timing lib or the liberty file, and whereas you will find the truth table name from your class book. That means your textbook which you have read in your college days. I have given the both terms so that you can correlate. In case your digital circuit has a race around condition in its truth or state table, it cannot be modeled by the blocking statement. These are some rules where you cannot use. So later you will find what if we do blocking in the race around, what will happen. The race around will happen and that will make the circuit unstable. Next, any kind of feedback path from output to the input cannot be modeled by the blocking statement. So you have a block where you have some inputs and you have some outputs, and you do have a feedback path that is working in some fashion, whether it is a positive feedback or it is a negative feedback. I'm not talking about that, but it has a connection from the output to the input as a feedback path. So that cannot be modeled by the blocking statement. Not the feedback path only, but the entire circuit cannot be done by the blocking statement. The results will be erroneous. Any single output pin getting values from mutually exclusive set of input combinations over changing conditions cannot be modeled by blocking statements. So you have a circuit. It's a block. Here your output is the same. Here you have two inputs and here you have two inputs. So there are some combination circuitry and you have some selection switch. The first one, if you change its value 0 or 1, the first two input combination will be connected through this, and these two if you connect, right, if you change it to 1, these two will be connected. So you can realize this is a kind of muxing operation, right? However, in words we have generalized it and it is not limited to the mux, but however if there is some mutually exclusive set of input combinations, right, in any digital circuit, in any design, in complex design you come up which is much more complex than a mux, cannot be modeled by the blocking statement, because in such conditions where you have a combination which is connected with the output conditionally, so it acts as a switch here. So either it connects to this or this, so it is not fixed. That means it is not hardwired to any of the input. The output is not hardwired to this combination or hardwired to this combination. So this way it is very much different, and you can easily understand the blocking statement means that you have a hardwired connection. The hardwiring that you cannot change with the time. This is a blocking statement in a nutshell. We are done with this slide. Let's move on to the next slide. blocking mechanism. Now let me go through the example to make you understand how the blocking mechanism works. Here we have a always block, and in the sensitivity list we have A, B or C. Any of them changes, the always block will become active and it will execute the code inside this. Here we begin our codes with the begin keyword. Here the first statement is X equal to A and B. Evaluate A and B and assign it to X. So this is an immediate execution. So this happens very immediately from this side to this side. Next, Y is equal to A or B or C. Evaluate this logic equation and assign it to the Y immediately. Z equal to B or C. Evaluate B or C and assign the result to Z. So these are happening instantaneously. That means once the playhead reaches this point, this assignment takes place from RHS to the LHS. Next the playhead reaches here, it happens from here to here. Next the playhead reaches here, the assignment happens from here to here. So this way the blocking assignments, that means these equations are hardwiring the inputs to the respective outputs. So here you can see there are common inputs and they are getting hardwired with the output, and we end the always block with the end keyword. So here is how the blocking mechanism works. We are done with this particular slide and let's move on to the next slide. Non-blocking assignments. Non-blocking assignments allows the instant state transfer and state change operation. Non-blocking assignments literally do not block the execution of the next statements. So the non-blocking assignments allows the instant state transfer. So later we will explain how this instant state transfer happens and state change operation happens. There are two steps, state transfer and state change. I'll later in the mechanism slide, in next slide I will explain this. And here it do not block the execution of the next statement. So here until one statement is executed, it's not like that the next one will hold on for the execution. So it's a different, you will understand in the mechanism slide coming up next. The right side of all statements are determined first and then the left side are assigned together. So this is the theme. That's why it do not block the execution. That means the RHS and the LHS. RHS happens parallelly, all the calculations and blah blah blah, and they are assigned in a one go to the left hand side equations. Consequently, non-blocking assignment result in simultaneous or parallel statement execution. So here it is much more realistic because in real time, when you are having a real time data going on, the many things, many assignments or state changes will happen concurrently. So the concurrent thing has to be addressed inside the Verilog, and that is addressed by the non-blocking statement. For example, A equal to B equal to 0 initially, PO2 are executed simultaneously together, that means in parallel. So first, this one, this is 0 first, right? And 0 to 1, this state change is happening here, the state change, and B, here it's a non-blocking operator. You can see we are using non-blocking. Let me clear it, and you can see here we are using non-blocking operator here. And here you can see the state transfer. So here I have just kept the state change from 0 to 1 by this non-blocking, and this 0 goes to B as a 0 as a state by this one. These two happens parallelly, the RHS, and then in one go they are assigned to the left hand side. And after execution, what happens? This goes to A, one goes to A, so A is 1, and this goes to B, so B is 0 after the parallel execution. So it is very much striking difference from the blocking assignment, or you can have a literal difference from any programming language that you have in pen or paper you are solving, right? From there it is very different. The digital circuit that are modeled by non-blocking assignment. Now we will have a list. Any sequential logic circuits. Next, a race around condition which exists in the truth table or the state table of any digital design. Those are expressed by non-blocking assignment. Sequential logic and race around conditions which are in the state table. Any kind of feedback path from the output to input if exists, right? In that condition, what will happen? The state transfer from the output to the input. So here to here will happen and here to here will happen, but this will be calculated first and then assigned, and this will be calculated first and then assigned. So this way this is handled, the feedback path is handled. Any single output pin getting values from mutually exclusive set of input combinations, where we have a mixed situation, right, where we have separate inputs and single outputs, and over time the selection can happen from this to this, or this to this is perfectly taken care by the non-blocking assignments. So the limitations of the blocking assignments are overcome in the non-blocking assignment. Here we are done with this particular slide. Now let's move on to the next slide. Non-blocking mechanism. Here we'll go through the mechanism. Here we have the same always block which we have used earlier. A, B or C in the sensitivity list. So any of them gets changed, the always block code will execute it. We begin the code with the begin and then we have the first assignment here. So X has a non-blocking assignment from A and B. Now how this works? Evaluate A and B first. So this evaluation happens at first, but defer the assignment of X. That means it halts here after the evaluation of A and B. It halts and defers the assignment and wait until some point. We'll come at later. Next, evaluate A or B or C, but defer the assignment of Y. That means halt here at this boundary. That means up to these two, this has executed and evaluated, this has executed, evaluated, but halting here. Next, we have B or C, which is assigned to Z by the non-blocking. So the B or C is evaluated, but it is deferred for the assignment to Z. That means these three are evaluated but halting at this boundary. Now we have exhausted of all the equation and the non-blocking assignment. At this point, what will happen? All of these will be assigned in one go with the left hand side. So the LHS will be assigned in one go with the new values from the RHS. So here you can see that the LHS assignments will happen in one shot from the right hand side, where all the evaluation was happening and they were halting at the boundary, this boundary. So they will get assigned in one go once all these non-blocking assignments are evaluated. And one more thing here, all these evaluation will happen parallelly. That means this will happen parallel to this and parallel to this. So they are not sequentially happening. But for sake of explanation in the slide, I have to show you in sequence. However, in actual circuit, they are happening parallelly. And here we end our code. That's all. We have explained the non-blocking mechanism. Let's move on to the next slide. More blocking versus non-blocking examples. Blocking examples, x equal to 0. Here it means that x changes at t equal to 0 and the next one a equal to 1, a changes at t equal to 0. And here we have the delay added, hashtag delay with 10. So 10 time units delay will be here. So delay until t equal to 10 and then c changes. So t means the marker, the playhead will wait for 10 time units and then c will change. Here the 15 delay units are spaced in front of D and it is assigned to 4. So delay until 25 time units and then D changes. So just to make you understand, so after this doesn't mean this is at t equal to 15, 10 and this is 15. So if you see, right, 10 and 10 plus 15 is 25. So it is added. So once you move from here, it is added. So these are adding timing spacers. Equal to 5, E changes at time t equal to 25. So we'll go to the next non-blocking example. So you have seen how it is happening with time. The playhead is time. So since we do not have a delay, they are happening at 0. Here we have a timing separator of 10 units. So at t equal to 10. 15, so 10 plus 15, 25. This is happening at 25 and here is no time delay here. So this is happening at t equal to 25. This way, the timing playhead moves on and the instantaneous assignments are happening through the blocking example. So now see similar examples in non-blocking assignment. This schedule to change at t equal to 0. That means here we have nothing to evaluate. So it is scheduling to change at t equal to 0 once all the non-blocking assignments be exhausted. So here evaluate at t equal to 0, schedule to change at t equal to 15. So that means once t goes up to 15, this value transfer will happen. Now here it is the same, evaluate at t equal to 0, schedule to change at t equal to 10. It is not sequential, so you can see the difference here, right? This is sequential, so these two are getting added. So 10 plus 15 is 25 here. However, this is very much individual. So this one is 15 and this is 10. So they are very much individual and they are happening parallelly and all are scheduled to change. Next here, this C or 1 evaluate at t equal to 0 and scheduled to change at t equal to 0. So you can see all these right hand side things are scheduled for change at some particular time. So somewhere it is t equal to 0, somewhere t equal to 15. Okay. And when this will happen, this evaluation will happen parallelly and they will be assigned in one shot from left hand side to the right hand side. However, if delay is added, then that assignment will be done after some delay. So these are the examples of the blocking and the non-blocking examples. Let us see some more blocking and non-blocking examples. Blocking. A and B end up with the same value, the race around condition. Here we will show a race around condition by the blocking statement. This is we are talked in the initial slides in this episode and here we are giving the example. Here always at the pause edge of clock, that means we have a clock and in this positive edge we are sensitizing the clock. So once this positive clock edge comes, do these operations. A equal to B, change now. And we have another always block. You remember this and this will happen parallel. These are fashioned to work in this way. I have explained in previous episode. And B equal to A changes B to a new value. So they will happen parallelly, these two always block and they will be assigned. So you can see here B is assigned to A and here A is assigned to B. So this creates a race around condition because we do not have a control what is happening first and what is happening second. So we cannot decide what value will go where. Next, we have the non-blocking example of the same kind of operations. Here we use the same kind of always block and sensitized with the positive edge of the clock. And here we write non-blocking assignment of B to A. So read B at t equal to 0 and schedule to change for A. In the same fashion, we have the another always block where A is read at the t equal to 0 and schedule B to change when there is a sensitivity of the clock. Here these two happens parallelly, that means these are scheduled to change. So that means these are evaluated and whatever value was in B will wait to go to A and whatever value is at A will wait to go to B. Since they are not hardwired and these assignments will happen at the coming of any positive clock edge, the value which are staying in a kind of temporary register, they will be transferred to the respective variables in a ordered manner and the race around condition is avoided. So here we are done with the examples of the blocking versus non-blocking. For a race around condition, you can simulate it by your own code and you can see the results. Some rules to follow. So here in this slide, we will make some rules for you to follow so that you do not get confused in actual Verilog design. And remember all the points that we have discussed so far. And with this set of thumb rules, you are well equipped to use the blocking and the non-blocking assignments. Blocking is used in always and without the clock. So we have a always block and hence here the sensitivity list is tell that is selection A or B. So any of them become active or become their values changes, right? That will trigger the always block to execute the code inside. Case cell, so this is the first case, P goes to A. This is the second case, P goes to C. Sorry, this will happen. So A goes to C and B goes to C. So this will happen. And here we end the case. We will come up to these all procedural blocks like case, if, else, all these things later on. Before that, we have clear our minds about the Verilog coding because these are very, very similar to the Perl or C language wherever we have used the case or if or else. So you will be very much in ease to accept them. However, the hard nut which is we are cracking here before we are going to our usual easy doing things so that you are very much equipped in your mind. And here we end the always. So here you can see here do not have a clock. However, we have a muxed input right here. You can see different cases are there. It is not a mux in digital circuit nature. However, it's a muxed input. So different variable conditions here and it will go there. So here there is some typo here. O has come instead. It will be 0, B00. It's a typo. Sorry guys. And in such muxed condition, we use the blocking inside the always block. And remember, we do not have a clock here, but we have a muxed input from where the selection go to the output for multiple input condition. One comment here you can use it. The blocking can be used. However, it is better to choose the non-blocking assignments. Blocking is used in continuous assignments. Like here, you can see we have used the continuous assignment here. This is a case where you can use a block where you do not have a clock. However, you have a masked input. Better you can use the non-blocking. However, this you can use. So you have some relaxation here. Non-blocking is used in only inside the always with clock or masked input. Here we have the always block and we have the clock, passage of clock or negate of reset, and we begin our code. And here is the if condition inside which we have the counter, right? And here we have the else, and here we have the another value of the counter +1, and this is 0. And here we end our code. Here is also there are two conditions. That means here is a masked input. So if there is one condition here, right, we go for this, and here another condition is here. In such condition, we are using the non-blocking operator. This, however, you can use, but it is preferable to use this one. And this is the case where it is hardwired is the continuous assignments. So there you must use the blocking operator. This slide is good for your Q&A for the interview. Remember these things. So this could puzzle you. So if you given side by side this example and this example, right, it confuses you. This is okay, you can do that, but preference is on this one. This should be done. Now the question is why? The question because here two cases do not overlap here, right? So either this will happen or this will happen. So here this will happen or this will happen. So anyone will happen. However, the hardware thing is not good for such selection. Better that you use the non-blocking assignment. And for continuous one, which are continuous in nature, that means hardwired, input and outputs are connected together, you use this thing, the continuous assignment. Now you are well able to correlate the infographic slide up to this. When we have given all the examples, you can understand why the continuous one is a hardwired in nature, whereas the non-blocking assignment very different, which was explained by the right hand side infographics. These are now, I think, you are clear to you. You can go back and forth in the particular image of the infographics. There you can go and come back to this slide and correlate these things. If you are a beginner, right, this thing will puzzle you for some time, but after you do the coding in hand, you will get everything clear. So here we are done with this particular slide. So let's move on to the next slide. Summary. Blocking statements X equal to Y, executed in ordered manner as listed, including any delay specified. Here the evaluation and assignments are immediate from RHS to LHS. So this happens in a very immediate manner. One statement realized before the next statement is executed. So it is very sequential in nature. One is realized, then another at time t equal to some value. All the statements will execute sequentially. That means this to this, this to this, and this to this sequence at some particular time. So time will not change. However, inside the time, all this equation will execute sequentially. We will not block execution of the statements in parallel blocks. So parallel blocks will happen in a parallel fashion, like multiple always block or multiple initial block. Useful for modeling digital combinational circuit. For combinational circuit, we use the blocking assignments, also called the blocking statements. Non-blocking statements, that is, here we can read out this as a non-blocking. So less than equal to sign, although it means we are non-blocking assignment, it is here. Schedule assignments without blocking other statements. Execute next statement without waiting for the first statement to execute. So that means if we have all the statements, and here is the separator, here is the LHS, and here is the RHS, all of them will happen, evaluation will happen, and the transfer from RHS to LHS will be done in one go. Assignment is postponed until all separate RHS evaluations are done, then assigned in one go from the respective RHS. So this is we have explained, which is a very much striking difference between the blocking and the non-blocking assignment. Useful for modeling sequential logic circuits. So this is very useful for modeling sequential logic circuit. So we are done with the summary here, and we have the striking differences. The blocking is one for combinational circuit, the non-blocking is for sequential circuit, and how this thing happens we have also explained throughout the episode, and we have summarized in the summary slide. So let's move on to our next section where we will do the code simulation. Hey guys, now we'll do the hands-on testing of the code of a 4-bit shift register. So here you can see the circuit diagram here. Here this is our input bit, and here we will measure the outputs, and we have a clock input and a reset input, and that goes to all the clock inputs of the D flip-flop, 4 D flip-flops here. So this is a structure of a 4-bit shift register, and this is we are going to implement through the behavioral modeling in our Verilog code. So let me open the codes. I am using Geany here. So here is our terminal. So here you can see, as I have shown in the picture, here are the input and outputs listed. So here is clock, reset, and A, B, C, D, E. We mentioned output here and input here. Don't worry, you will get the download link of this code in the video description. From there you can download the code and do your experiments. Here we have a always block, and here we are specifying the reset condition. If it is reset, then all this will be 0, and this is happening in the positive edge of a reset, and else if it is not, we will go for the assignment. So this is the blocking assignment. You can see here all blocking. So we will use the same circuit, and we will change the assignment here only as the blocking to non-blocking. Rest of the code will remain same. And here you can see the test bench, right? And here is our clock. It is our clock definition. Here the clock is start with 1, and after every 5 time unit it's toggling. And here you can see we have created a dump file, although this will not much be needed in today's example. However, as per convention, I have kept it. Here you can see this will print the data table, and this monitor will monitor all the changes in the mentioned input outputs. And here we give our test vectors. So you can see in time 0 we have given E, which is our input, as 0 and reset as 1, and then at 7 time units we have used the 1 and 0 for the E and reset. In first case the reset was done, and in the second case reset is removed and value is assigned together. And here we have instantiated the module which we have defined in the beginning of the code. That was blocking assignment. Here everything remains same except we have non-blocking assignments here, and rest of the things remain same here. Let me give this in between the two. I am using tkdiff here to this between the two Verilog code, and here you can see the difference points have been highlighted. First, here all are blocking, and same are non-blocking assignment here. This is also blocking, and this is non-blocking. If we come down right, here we see the difference in the dump file name, the VCD file name. Obviously it will be different for the two, and we can see the instance of the module here. You can see the Shift Reg BK, which is the blocking, and Shift Reg NBK, which is Shift Reg and the non-blocking, so instance NBK. So here you can see this and this are different. So it's very clear that in this, among these two files, we have only few difference points as the blocking assignments and the non-blocking assignments, and the instance name or the module name and the VCD file name. So rest of the things are, you can see here, all these and these are same. Also that is true for part here, these are same. So with that note, let me simulate these codes. I am using Icarus Verilog. The command is iVerilog, and then we give this, and we give the output dump file name DK. It is a blocking one, right? Let me generate the two object files first. Now I do a ls. You can see here that two object files with BK and NBK has generated. Now let me execute this object file one by one. First, second, since it's a shift register, what will happen? The value is assigned at E and that will propagate in this direction. The value will shift with the clock pulse. So you can see here at 7 we have set the value right, and see this is we have used blocking assignments, and here you can see the value has changed. E is 1 while we have done reset for all, and since we have used blocking assignment, all have become 1 here. We exclude the clock. We are not talking about the clock. We are talking about the data inputs and data outputs. We are not talking about the clock. You can see that all have become 1, which is not expected, right? Because we are expecting the bit to shift left. Now we see the result of the non-blocking. So here you can see the non-blocking, the NBK we have, and here we are not talking about the clock. Clock is properly toggling here, and here you can see at 7 we have set the value E to 1, and because of the reset instruction given previously, all are 0. So you can see if we follow this line, the bit 1 has been shifted down with the clock pulse from E to D, then D to C, then C to B, then B to A. So this way the bit has shifted from here to here. So with the non-blocking assignment we have achieved the shift register design. If we use the blocking assignments, we are not able to get the desired outputs. We have done the simulations with Icarus Verilog and we have used the Geany IDE here. Let us move on to the Vivado. Let me close the Geany. So Vivado is starting here. You can see here it is starting the GUI. The splash screen has appeared and our Vivado interface is ready. So we will click on the create project here. We click on next, name it 5, and you can see here it is opening in the right, correct. And here we choose the RTL project and do not specify the sources at this time, these two options. Here everything is okay, let it be. In the boards we will pick this one. Although we are not using a board, we click on finish. So it is opened. Now we will click add sources. Add or create design sources. So we go for this option. Go to add files and we add the shift register with the blocking assignment, and here you can see the preview in the right hand side. So you can see what code you are opening, and here we click on finish. So here on right hand side our code has opened. And now we'll go for the run simulation option. So here you can see the output has came for the printing statements, and the first one is clock. If we see it aside, we can see the clock is toggling properly, and there is a bit shift in the A, B, C, D, E. You can see at 7, E is set to 1, and because of the reset instructions, everything else is 0. We are not talking about the clock here, we are excluding the clock, right? You can see that because of the blocking, here all are 1. So we don't see a bit shift here. It is not shown here, which we have seen with the Icarus Verilog simulation also. Let me now go and add sources. Here we will pick again this option, and here we will use the non-blocking Verilog code. And here we go for add files, and here we add Shift Reg in VK. And in the right hand side, you can see the code preview. Click on OK, and we say finish. So we are removing the blocking one here. So here you can see the non-blocking code has came here. We will do the run simulation. So here you can see the output has came for time and clock. We can see the clock is properly toggling, right? We can see at 7, E is set to 1. And if we carefully look, right, this bit is getting shifted towards the left following this line. So it is going from E to D, D to C, C to B, and B to A in this fashion. So with the clock edge, the bit is moving left. So with the non-blocking assignments, here we have the non-blocking Verilog file and the corresponding simulation. We can see that with the non-blocking assignment, we have achieved the shift register, the operation of the shift register here with the Verilog code. So we are done here with the example. Hey guys, welcome back. In today's episode, we are going to discuss the below points. If-else basic structure. We will look into different variants. Next, the writing style we will compare from a beginner to a pro. Next, we will talk about using multiple conditions in the checking counter of if-else blocks. Next, we will see some example of if and else. In the next section, we will enter into the operators that can be associated with the if-else blocks. First, we will talk about the relational operators. Next, we will talk about the logical operators. Next, we will talk about mathematical operators. Next, we will talk about the equality or non-equality operators. That's the menu for today. So without any further delay, let's begin. If-else basic structure. First, if we have a condition here, you can see, then we have a single statement for true condition. Else, we have a single statement for false condition. This is a very basic structure. Here we have not used any other keywords, only if and else is there because only one statement after the if or else. If multiple statements are used, we will come to that point. Here comes a multiple statement structure. First the if, then its condition is there, and then we use the begin keyword. This is similar to the programming language opening and closing braces. In various programming language, open and closing braces are used, whereas in Verilog begin and end keyword are used. Next comes the multiple statement for true condition. Then we use end of this if. Now we have the else, and again we have a begin for the else. And here we have multiple statement for the false condition, and then we end the else. This way you can see side by side compare between the two, where you can have a single statement or multiple statement inside the if-else blocks. Next we have condition 1. For that we have a single statement. Condition 2. For that we have single statement. Condition 3. We have single statement. Here you can see we have not used the else, only if we have used. So all are true condition. Here we do not have a false condition, only we have the true condition, but separate condition which are mutually exclusive from each other. So condition 1 is mutually exclusive from condition 2 and condition 3. Condition 2 is mutually exclusive from 1 and 3, and in the same way 3 is mutually exclusive from 1 and 2. So this way the basic if-else structure can be written in a Verilog block of code. In last couple of episodes where I have emulated different codes, you might have already came across the if and else conditions. So there I have not explained the structure because in Verilog we have to learn something first and then we have to go in depth. So now we are going in depth. We are done with this particular slide, so let's move on to the next slide. So if else, we will start with the beginner and then we will move towards the pro style of coding. So here the same code we will use in the left hand side as well as in the right hand side pane, and only the change of coding style will be from beginner to a pro. So when you start coding, you will use the beginner so that you don't make a mistake, and once you grow up in the Verilog coding, so there you will use the pro style. If condition 1 begin, then we have multiple statements followed by end the begin one. Else begin, then we have inside that we have a nested if condition 2 begin, and then we have the multiple statements end, then else we have again the begin and multiple statements and end, and finally end the initial begin. This is a very beginner like coding which I suggest you should use at the first so that you don't make a mess with the code. Now over the time when you grow up, you code in a different style. If remember, the left hand side and the right hand side codes are same, begin, then multiple statements, end, then else if begin. When we have the condition 2 in the nested if, then we have multiple statements, we have the end, we have the else begin, and we have the multiple statements again, and we have the end. Here if you see, right, this and this line is same, or rather this block is same as this. We do not have a change here. Next, where do we have the change? Where we are using the nested condition. So here you can see else begin is there, and then we have the if begin. Two sort of begin and end are used. However, in the pro style coding, what happens that else, then we put if, then condition 2, then begin. So one begin gets subtracted from the writings, and here you can see this begin end thing is not there. Here itself the trimming down happened. So once you grow up in Verilog coding, you make this kind of changes by yourself, and here you can see that this particular block versus this particular block do not have any changes. So we are done here. I think you have grasped what I want to say in this particular slide. So let's move on to the next slide. Using multiple conditions. Now by condition, what I mean, we have a parenthesis, pair of parenthesis. There we write some conditions. So here how we can put condition 1, condition 2, etc. How? So we will give a example just for your understanding. Here let me bring up the code. First we have write 1 and this is logical and, not the bitwise and, write 2, and with this whole set of condition, this particular condition, we are ending this. We have read reg equal to read reg 2. This condition and this condition has to be satisfied for this particular if block to get executed. Next, we have the statement for the true condition when this condition and this condition are satisfied. Next, we have else if. Here you can see the condition 1 remains same in the next nested if, and here it changes not equal to. This was equal to, and this is not equal to. In later this particular slide, I will explain all these operators. So here you can see for this if block to execute, this condition, that means here to here and here to here, simultaneously have to be satisfied. Next we have the statement for this particular true condition. We have the next statement and we end it. Next we have the another condition if write 1, and there we write another statement and else. Finally we have one particular line. So folks, here the focus of this slide was on this particular if condition and this particular if condition. Rest of the things are fair easy enough, like this one or this one. You can understand them very easily. However, how to write multiple condition, you can look at here and you can have a grasp how you are going to write multiple conditions inside the if conditional counter or conditional checking. We are done by explaining through example here how to use multiple conditions. Let's move on to the next slide. Here we will go through some if-else example. Although we are going through example, we go to another example here. Here we have always, and the sensitive variable is RST, and we have begin. Then if RST set q equal to 0, else we will remove the assignment. This means this. So we will do the deassign q and we end. So this is a new keyword. You can see I have mentioned earlier that deassign can be used to do the reverse of the assignment that is done here. So this is one example. If else can be used inside a always block. We go for the next example here in the same slide. Always at the rate the sensitive variables are write, read or status. Either of these three becomes sensitive, the always block will execute. So we begin the always block and there we have if not write. So here you can see there is a bang sign and we begin. So this is a if else if out equal to old value and end. Else if not status, that is we have a bang sign here. You can see not status q equal to new status and status equal to old, and we end this particular if. Next else if not read, that is bang read. So we have a bang here. Then we do out equal to new value and end, and we end the entire always block here. This begin and this end are paired. So although right now these examples do not hold any meaning to you because we are not inside a design, however by looking into these things you will be easily reach your hands to code for the Verilog codes for the if and else. So these are the few styles in which the if and else coding can be done. I have walked through you a couple of examples so that the things get very clear inside the mind. Only theory doesn't clear, rather the examples will clear inside your mind how you have to write the if and else. In actual case when you are writing for a design you will automatically use these things, but however some example has to be shown in front of your eyes so that your mind has deciphered how you will use the if and else inside the Verilog blocks. We're done with this particular slide, so let's move on to the next slide. So if else coding is done so far, and now we'll have come to the next section where we will cover the operators, and here in this slide we will talk about the relational operators. And here we will go through a table. This one is a less than operator. So this is a less than b, is less than b, then return 1 bit true false. What is the return value? So this is a 1 bit true false value. Now similarly this one is a greater than b, is a greater than b, that will also return 1 bit true false as a and b values are there. So this is greater than equal to a greater than equal to b, is a greater than equal to sign, and this is less than equal to. So remember all these operators here shown has to be used inside the if conditional checking counter, that is within the parenthesis. We're done with this particular slide, so let's move on to the next slide. Logical operators. Here you can see this is AND operator, and how we use that? Suppose A is a variable and B is a variable, A and B means is A and B true? Both are true, returns 1 bit true false. This is OR. So A double pipe, that means ORing. Is A or B true? So is A or B true? This means, and this is not, OR and NOT. The three logical operations are performed here. So last one is the NOT. If not A, so if A is not true, we can also call it a negation operator, so that it negates the true condition. That means the false condition will be picked up. So these are logical operators. They can be used inside the checking conditional counter of the if, that is within the parenthesis. Let us get familiar with some of the mathematical operators here. This you may use for variable calculations. Some point. These are not used generally, but however they can come through some expressions. So I am not stressing here, but for yourself getting familiar is the first thing. Star is A star B, means multiply A with B. Slash A slash B, integer divide A by B. Plus A plus B, add A and B. Minus A minus B, subtract B from A. Percentage A percentage B, A modulus of B. So in case you have learned the C language or the Perl language, you might have already came across all these operators. They are also available there for mathematical calculation. So similar set of mathematical operators available here inside the Verilog, and you can use them for your mathematical calculation. We are done with this particular slide. Let's move on to the next slide. Equality, non-equality operators. Now, if we write one equal sign, This means assign A to C. So that means A will be, it's a continuous assignment. So A will be assigned to C. If we use double equal to, that means C equal to A. What does this mean in Verilog? C is equal to A returns 1 bit true false condition. Applies for 1 or 0. That means this one or this one, either there is 1 or 0. So for both of them, either in 1 or 0, this particular equal to will work. This logic equality using Z or X operands returns always a false. So we cannot use Z, we cannot use X. So we know in digital electronics these two states exist, that is Z and X. However, this cannot handle the Z and X and returns always false. So remember this thing. This can be used for 1 or 0 and not for Z or X. This will not work with this particular operator. Not equal to. Here you can see C not equal to A. Is C not equal to A? Returns 1 bit true false logic equality. This is for that you can understand very easily by comparing with the equal to and the not equal to. We're done here. In the next slide, we will talk about the special equality non-equality operators. So let's go there. Special equality non-equality operators. Now in the last slide, we have seen that the double equal to sign cannot handle Z or X. Now this triple equal to sign, here we write like this, A triple equal to B. This includes 0, 1, X, Z. So it's appropriate for the Verilog coding, and this is not equal to and it is a not. So it also handles the 0, 1, X, Z. So this 0, 1, X, Z is also taken care here. Identical to be 1 bit true false it returns. However, the main focus is 0, 1, X, Z. Now let us compare something here. Equal to test logical equality test for 1 and 0. All other will result in X. Triple equal to test 4 states logical equality, that is 1, 0, Z, X. Equal to for comparing bits 0 or 1. Triple equal to comparing for 4 states, that is 0, 1, X, Z. So this is very strictly you have to remember, because in Verilog, if you are comparing between two logical values, then I think this operator or this operator is the right one to choose. Although the other ones shown in previous slide exist, but these are the right ones to choose for your comparison. In case you are comparing an integer to an integer, then I think previous one is okay. Equal to can be synthesized into a hardware, X not gate, but triple equal to can't be synthesized as X is not a valid logic level in digital. It is in fact having voltages in between 0 and 1, and Z is not itself any logic, so it shows disconnection of the circuit. There is one demerit, this is mentioned here. You have to choose the operators wisely. We are done here with the particular slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. Introduction. First, we'll do an introduction to the case statement in a very generic manner. Next, we will talk about the case structure itself, and we will see how we can use a single, multiple commands and combination of the two in writing an entire list of case statements for various case values inside a single case block. Next, we will go through 5 different examples using the case statements. And as you know, as a student, when you are learning the language, the structure is okay. But however, if you do not go through the examples, it is very, very difficult for you to write a code by yourself. Next, we will emphasize on the points that should be noted while dealing with a particular case statement in Verilog. Next, we will talk about how to detect the X and Z using a regular case statement. And remember, this is a very good question for any interview in Verilog, because we also have case X and case Z in Verilog. However, we can use a general case statement to detect X and Z. So in this point, we are going to talk about that only. Next, we will talk about the case Z and case X examples. Next, we will talk about the CaseX and CaseZ with examples. These are advanced case statements in Verilog, and you will see this is a basic fundamental difference from any programming language, because in any other programming language you will find case or switch case, but you will not find this kind of specific CaseZ or CaseX. These are very much specific to Verilog, so you must have a good knowledge about them and using them. That's why we are giving examples so that you can understand it and write the code with CaseZ and CaseX. Next, we talk about the constant expression in case. So in the case statement, we generally use an expression. However, we can use constants. Constant is something that is constant over the time and it don't have any expression. So it's a constant. So that we can use in case. And please remember, this is a very important question for the interview. Finally, we will summarize our entire discussion in the final slide. So this is the menu for today. So without any further delay, let's begin. Introduction. The case statement is a multi-way decision statement. Multi-way means there are multiple cases for which the digital control can go to different expression or values. So this is a multi-way. Or rather you can say it's a lookup table. So case 1 value 1, case 2 value 2, case 3 value 3. So this way it can have a lookup table. So this is a decision statement and it's a multi-way. It tests whether a digital expression matches among a list of predefined other expression or branches. As I have said, it have a predefined list starting from 1, 2 and up to n. So among those lists, it will search for the matching case, and we also have a default statement. If it doesn't match with any one of the expression here, it will go to the default at the last. I will show you. The case statement allows a multi-path branch based on comparing the expression with a list of case choices. It's very easy to understand and we will exemplify it so that you better understand it. Case choices may be simple constant or expression or a comma separated list of the same. So when you are writing case within parentheses, what can come? A constant can come, a expression can come, and a comma separated list can come. These three. Definitely we will go through the example. There you will see this. Upon exhaustion or exclusion of the list, control enters into the default block. That means when all the cases from the lookup table are finished, it finally enters into the last block, that is the default one. That means the checking counter has not matched with the values or the expressions those have been specified before the default one. And once it enters the default block, it executes the default action specified using the default statement. It is a good practice to make habit of putting a default whether you need it or not. So this is very, very important because in Verilog, you might have to debug your code based on different case scenarios. And in some particular case scenario, say your expression is not matching with the values that you have defined through the case. So it will enter into the default case and you will find, okay, all these have not been matched. In case you need to insert some more case or you have to modify some of the existing cases, that call you can take at that time. But remember, the default block will help you to go there. Otherwise, if you do not specify the default block, then you will be in a wild goose chase. So you will not understand what is happening. If the defaults are don't cares, define them as X. As we know that in digital we have X, right? So if it is don't care, define them as X. Case excels when many tests are performed on the same expression. So if the same expression is there and the case operates on the same expression but however for different values to the lookup table that we define inside the case. Case works well with which digital circuit? Ex.s, decoder and next state logic. And the next state logic is also termed as the FSM in digital design. In some later episode we will cover Ex.s and decoders, you already know. So those things go well with the case statement. So we're done with the introduction part here and with this slide. So let's move on to the next slide. Case structure, single statement. So here we will give an structural example. It's not a code example, it's a structural example of the case with using the single statement in each value. So here case variable or concatenated variable, or we can have a comma separated values also. So it start, and here the lookup table starts here. For value 1 we use colon as a separator, and on the right hand side there will be single action statement. Here it is a comment. However, in your case this will be actual Verilog statement. Next we have value 2. For that we have action statement 2. value 3, we have single action statement 3. So this is single statement. That means one statement, not more than one statement is here. And this way we continue and we reach value n and action statement n. And finally, we have the default statement and we have the default action statement. Generally, this is a int command like $display or something where you actually give a echo on your screen so that you know that all the things are not matched and your control has entered into the default one. So this way you actually do the debug. This is the structure and we end our case with the end case keyword. And this is the basic structural example, not the coding example. The structural example using single action statement. So you have one particular statement for a particular value and this way you build up the lookup table. A structure with multiple statements. In last slide we have talked about the single statement. Now your question is, okay, how we will be writing about the multiple statements in the case structure. So this is the whole kind of case where we will be going through the structural example, not the code example. Here we have the case and we have the variable or the concatenated variable, or we can have a comma separated values also. Here we have the value 1 and then since we are containing multiple statements, we start with the begin keyword. This is for value 1. This is not of the case. This is for this begin is for value 1. Now we have multiple action statements and then we conclude it with the end. This begin and this end belongs to this value 1. And here we have multiple action, although I have written one single particular comment, but however you can push multiple statements inside this begin and end for value 1. Next we have value 2 and we again have begin. And we have multiple action statement and we have the end to end it. This begin and end for value 2. This way continue and we reach to the value n. And here we again have begin, we have multiple action statements and then we close it with the end. So and this end is for value n. And next we reach at the default statement. Here we can have also multiple statement and we have the begin here. And we have the multiple statements and we have the end. This end is for default one. And to end the case, then we write the end case. So this end case is for the case statement. This way you can write multiple action statements for the case structure. So this is a structural example. It's not a code example. It's a structural example. You understand better how to write the case statement as a beginner. Now we are done with this slide. The next question comes that, okay, now we know that we can write single statement and we write multiple statement. In actual case, it may happen that both are combined. How we write that? So in next slide, we are going to talk about that. We are discussing here about the combined one for the two things, that is a single and the multiple that we have just seen in last two slides. So here we start with our case statement and we have variable, concatenated variable, and we can have a comma separated values. Next we have value 1 and we have single action statement 1. We have value 2 and begin. You can see begin means we are having multiple statements. So here I explicitly write single action statement to A, to B, to C. So these are three different single statement contained within value 2 and we end this block with end and it is for value 2. Next, we have value 3, which have action statement as a single action statement here, and we continue further. We reach up to value n and where we have action statement n, and we have the default one and we have default action state. We end the case with the end case keyword, and we are done with the structural example here. And the point is here, this particular structure can be anywhere, there, here, anywhere, or multiple, means don't have to be in one place, it can be in multiple places. So this is a structural example. Now we are done with this particular slide, so let's move on to the next slide. We have case example 1. So here we will go through the code example. So far we have seen the structural example, means how the structure can be altered and all, and they can be combined. Now we have the case example. So these are realistic example. However, we are not writing the entire code with the test bench, just for the case block so that you get efficient in writing the case statement. First we have the range A, which is 15 down to 0. We have result, which is a range and it is 9 down to 0. So both are buses. And then we start our case and we have range A as the case expression, and the values which can be possible for range A is 16 tick D0, and the action statement here is the result will be this one. So result and range both are buses, so this way we are writing the values of the buses, and here we have 16 tick D1 and we have the values. So this way we continue the lookup table till we exhaust all the values, and in the default block we have written here result equal to pick Bx. This is some X condition we are putting. You can also give here a $display command for your debug purpose, right? And we end our case example with end case. You can see that here we have used the single action statement format for the case, and here we have dealt with two buses, reg A and result, as for the conditional value of the reg A and the result as an outcome. However, you can see these are the width of the buses are not same, so you can understand that this is a very actual example where the buses will be different. They will not be same. However, you are using them inside the case statement. So this is a very good realistic example of the case using single action statement. So we are done with this example. Let's move on to the next slide. Here we will have two examples in a single slide. So let us start with the first one. Case ALU counter. You can see this is an expression ALU counter, and here we have 2 tick B00, and then what will be the action, that is ALU out will be A plus B, and similarly if it is 2 tick B01, ALU out will be A minus B. 2 tick B10, ALU out will be A and B, and default is ALU out is 1 tick BX. And these are treated as don't cares for minimum logic generation. We have done with the case example here, and here we end case. Here you can see that it is not a constant here, rather than this is an expression which is a difference from the previous example here. So we are done with this. Let's see the next example. We are staying in the same slide, so let's start here. We have case X, Y or Z. So this is a kind of comma separated values, which means that this case happens if X or Y or Z, right, any one of them is 2 tick B00. So here if 2 tick B00, ALU out is A plus. That means case if X or Y or Z is 2 tick B00, this expression must be executed. Similarly, if 2 tick B01, it will be A minus B, and for 2 tick B10, it will be A and B, and for default statement we have ALU out equal to A pipe B. And we end the case with the end case statement. This is another kind of example where we have exemplified, which is the main thing here. This is a comma separated values, and this or this or this can have the value this. So this is a different type of case example that you have just came across. So previously there was only one single. So later we will have some example with the concatenated one also. So we are done with this particular slide. So let's move on to the next slide. Case example 4. Here we have a single example, but I have broken the code into two parts for the sake of the space in this particular slide. We start our code here, and we have a module D2X8, and we have select and out. This is a priority encoder, and we have input 0 to select, output 0 to 7 out, and this is out is a reg. You can see these and these are buses, and this out is type reg, and here we start our always block, and the sensitive variable is select, that means this one, and here we begin our code, and here we write out equal to 0, and we continue our next part of the code here. And here we have the case, and here we have the select. Again, here the expression is select. So select is staying here in always. So whenever the select changes, this goes from here to here in the case. So the sensitivity is tied up with select, and that goes to the case directly. And here we have our first lookup table statement that select if it is 0, then out is a bus, right? So the 0th bit will be 1. Next for 1th bit will be 1. And this way we continue further, and we reach up to the default one. Here the default one is display, nothing is set for default. So this is acting as some debug command. So this notifies that none of these has happened and nothing is set for the default. That means the above ones have not executed. And we end our case with the end case statement. Now we put a end. Now this end, it belongs to always, right? And finally we have a end module, and this one belongs to the module statement. So here our code is completed. You have grasped the meaning, how we can use the case, and this is another type of example, and we have used the debug statement here with the $display, and we are done with this example. So let's move on to the next example. So here let us start our example, and here we start. It is a 4-to-1 multiplexer, and we have module, and we named it as a case 1, and we are writing input 7 down to 0, A in, B in, A in and D in. 4 inputs, input 1 down to 0 select, and output, his name is 7 down to 0 D out. So these are the input and outputs of this module. And here we have always block with the sensitive variable is select, so this one. and here we begin our always, and here we start our case, and you can see once the sensitivity comes to always, it get transferred to the case, and there it is checked for the values that we are listing here. The values, if the select is tick B00, this action will execute. The D out will be A in. For 01, D out will be B in. For 10, D out will be C in. And for 11, D out will be D in. And here we end our case. So you can see our case has ended with end case, and we end it. So this end belongs to the always, and we end our module. Here, this belongs to the module. The entire code is completed here. So this is another example which I think you can grasp the meaning, how to write the case statement. And let's move on to the next slide. Case points to be noted. So here we are talking about different points that we should note properly while we are coding for the case statement in Verilog. Now here it starts. In the case statement expression comparison, the comparison only succeeds when each bit matches exactly with respect to the values of 0, 1, X and Z. So these 4 values does exist in digital, and the case expression has to be evaluated, either each of them or the combination of them. This is our thing we should remember. So that means 0, 1, X and Z can come in a realistic scenario. Next, as a consequence, care is needed in specifying expressions in the case statement. So when you are using the statement, right, you must be very careful. The bit length of all the expressions shall be equal so that exact bitwise matching can be performed. So you must be very careful about the bit length. That is, when we have an expression, we have a variable, the bit length, that is the LSB to the MSB, how many bits are there. So that thing is very important there, and matching, it should be matching throughout the code. Next, the length of all the case item expression as well as the case expression in the parentheses shall be made equal in length of the longest case expression and case item expression. You have to be very careful about the length. That is what we are focusing here. So whatever in the case, that should be the superset of all the expression for the same thing. If you have some other versions, that should be there and it should be the superset. If any of these expression is unsigned, all of them shall be treated as unsigned. If any of the expression are signed, then all of them should be treated as signed. So you have to be very careful. Again, apart from the width, you must be very careful whether it is unsigned or signed. So you have to stay in the same convention. That means either you stay in the signed one or the unsigned one, whatever is applicable there. It's not your choice, whatever is applicable there. You are done here with the points that you should note while you are writing a case statement in Verilog. These things do not exist there in other programming languages. These cautionary points, these things you have to remember only in Verilog. That means in the hardware description language. So we are done with this particular slide. Let's move on to the next slide. Case detecting X and Z. So as I have mentioned in the menu, right, there I have mentioned that this particular slide will be very important for your interview purpose. You can be asked that we have already CaseX and CaseZ is there. So how you can detect the X and Z using a regular case statement? You focus on this slide with great importance, and let us begin here. So here we'll give example code here. Our case starts with case and we have a variable sig, that means signal, and signal is 1 tick BZ, display signal is floating. If it matches with 1 tick BX, display signal is unknown. And we have default that the signal is printed explicitly. So this way the case can detect the Z and X. Now this is 1 bit, right? If it is more than 1 bit, then you can have more than 1 bits here itself. We clear the markings. If this is more than 1 bit, it has some width. So here you can modify accordingly. Here we have the end case, and this ends the case statement. Just simple, yet it is very important for the interview. So we are done with this example. So let's move on to the next slide. Advanced statements, that is case Z and case X. In a case expression, each bit matches exactly with respect to the values 0, 1, X and Z. So this you are very much familiar. I have re-emphasized it here because we are talking about now the case Z and case X special case statements that exist only in Verilog. You have not seen, or you will not seen such kind of special cases or switch case in programming language. It is existing only in the hardware description language. Next, two other type of case statements are provided to allow handling of do not care condition in the case comparison. So you know Z and X does exist, you cannot ignore them. So to include them and handle them properly, we have special cases, that is case Z and case X in Verilog. One of these treats high impedance value Z as do not care, that means this is case Z, and other treats the high impedance and unknown, that means Z and X as do not care, that means this is for the case X. Next, these case statements can be used in the same way as the usual case statement. That means the writing fashion is same, but they begin with keywords case Z and case X. So these are reserved keywords in the Verilog library. So you have to use these judiciously where you have such cases inside your Verilog design. Do not care values, Z values for case Z and X values for case X in any bit in either of the case expression or the case item shall be treated as do not care condition. Basically, the Z and X, either Z or X or Z and X combined, are treated as don't care conditions in the expression, and that bit position shall not be considered. If particular bit position is assigned for Z or X or Z or X or Z and X, that should be treated in a very judicious way. So we are done with this particular slide. So let's move on to the next slide. We continue our discussion here for the case Z and case X description and definitions. The do not care conditions in the case expression can be used to control dynamically which bit should be compared at any time. So this is another thing, the dynamicity, that is another very important factor of this, because in the lookup table in the regular case statement, the left hand value from the colon right here, it should be something which is fixed. It's not dynamic. However, here in the case Z or case X, you will see the examples, how they can be dynamic, how we can write them as a dynamic. You will see this is a stark difference with the regular case statement. The syntax of literal numbers allows the use of question mark, that means this question mark, in the place of Z in the case statements. This provides a convenient format for specification of do not care bits. To denote the do not care bits, we use a question mark for Z cases. Case Z. Basically, we are now summarizing for case X and case Z. So start with case Z here. Treat Z as the don't care in the expression, and the position that can contain Z are represented by a question mark instead of a fixed bit. In regular case statement, we use either 1 or 0 as a constant number there. Instead, for Z, we can use a question mark, and this gives the dynamicity. Here we have talked about the dynamicity, right? And this particular expression gives the dynamicity of that expression. You will see when we give the example. Case X, treat both X and Z as don't cares together. Now this is a superset of case Z. However, Verilog has a provision to use either Z or case X. Both you can use or either one you can use. It depends on case by case basis. That means not the case of the Verilog, but the real case where you are coding. And for this, the case X, the position that can contain Z or X are represented by question mark or X. In the example, you will see that here these are used to denote the do not care. That means the don't care position. That means it gives the dynamicity of the case X and case Z. So for case Z has the question mark, and for case X it has the question mark or X. We are done with this, all the definitions and theoretical discussions here. Let's move on to the next slide. Case Z example. We have a bus here, IR, which is 7 down to 0. And we have case Z, this is for case Z example, IR. And here we have a left hand expression, and here you can see here the marking. All these bits are dynamic to be Z, and it could be any expression. This is fixed and these are dynamic. So this can be Z, anyone can be Z, anyone can be S. In that case, the instruction 1 should happen. That means that should execute. In the similar fashion, we have this expression, this and this. So here you can see here 1 bit is constant, here 2 bits are constant, here 5 bits are constant. Here we have 6, I think 3, 3, 6, yes, 6. And here 2 are dynamic, here 3 are dynamic, here these ones are dynamic, and here most of the things are dynamic as to give place for Z. And we end the case with end case. Now let us give some explanation of this. So the above example of the case Z statement, as we have just talked, right? We demonstrate the instruction decode whether the values of the most significant bit select which task should be called. So here these are tasks or instruction set, what should be there. And the most significant bit IR is A is 1. Then the task instruction 1 is called regardless the value of the other bits in IR. So this is very clear from this state of values and corresponding actions. That means this lookup table. So we are done here with the case Z example. Let's move on to case X example. Here we are in the slide of the case X example. Here we start our code with the reg, and this is 7 down to 0 R, and there is a mask, and we define a mask as this one, and we have case R XOR mask. So this is an expression R XOR mask, and we have this kind of lookup table here. So here. So you can see here these bits are constant and these bits are constant. And these 2 bits, right, these 2 bits are don't cares, and they are specified with X, because here we are dealing with case X. We end the case with the end case statement, and you can see how we can write a don't care condition in the case X. So you have seen the case Z example and you have seen the case X example. Now let me give the X description. So here this is an example of case X, and it demonstrates the extreme case of how do not care conditions can be dynamically controlled during the simulation. So these are dynamic. So that means this one both can be X, or one could be X, someone could be other thing. So this way this becomes very dynamic. So this is not a constant expression. This is a dynamic expression. This dynamicity is given by the CaseX. And this dynamicity, one thing I would like to mention, actually reduces the number of cases that we are writing as a lookup table. Next, in this case, if R is equal to this, then the task stat2 is, this is a typical example, right? You understand this particular case example or using the CaseX statement. So here we are done with the slide. Let's move on to the next slide. Constant expression in case. Before beginning, I would like to talk here that this is a very good slide that question can come in the interview. That means we know that in case we use the expression, and tell me or show me an example where we can use a constant in the case. So here we start with range 2 down to 0 in code, and here we have case 1 and we have encode 2 display select line 2, and we have encode 1 and display select line 2. And for encode 0, we have select line 0. And we default, here we have missed out the colon and it has the error message. Now, let me explain how this constant is working. A constant expression can be used for the case expression. The value of the constant expression shall be compared against the case item expression. That means this value is compared with this value, right? So encode can have multiple values. However, this one has to be compared with each bit. So this is a single bit, this is a single bit, and this is a single bit. This way the constant expression is compared with here. Similar way, we can have a constant value and we can have a concatenated value here also, that we can also have. In this example, the case expression has a constant expression 1. The case items expression, that means bit selects, are compared against the constant expression of a match. So here these bit selects are compared with the constant expression. So here we are done with the constant expression, and as I have given you a tip that you can use a concatenated version here also. Here you can have a concatenated version also. However, this will change somehow according to that. Those can be asked in an interview. So here we are done with the constant expression in case. Let's move on to the next slide. Summary. The case expression given in the parenthesis shall be evaluated exactly once and before any of the case item expressions. So whatever inside the parenthesis is there, that should be evaluated first, and then that should be compared with all the values mentioned in the lookup table below. Next, the case item expressions shall be evaluated and compared in exact order. So this is another good point to be emphasized, which they are given, because in digital design we sometimes have a kind of methodology of design where this order does have a significance. So in that case, you have to focus on the exact order. During the linear search, if one of the case item expression matches the case expression given in the parenthesis, then the statement associated with that case shall be executed and the linear search should terminate. So this is the most important point. Once you have a match, it goes out of the case statement. By executing the lookup table expression, it goes out of the case expression. If do not search any further. If all the comparison fail, that means all the lookup tables that we have written, they are failed. The default item is given. Hence, I am emphasizing this point again and again in this particular episode, that the default one is good for your debugging purpose. That means you have written the case conditions correctly, or you have not missed out, or in case you have missed out, you will have the default one to notify you that you have missed out. Somehow you have to go back and check, debug by yourself, which particular case I have missed out. Default is given, the default item statement shall be executed, and this is a good opportunity of the debug. The case statement differs from the multi-way if-else-if construct in two different ways. First one is the conditional expressions in if-else-if construct, that means the nested one, are more general than the comparing expression with several others, as in the case statement. So case statement, you have a specific lookup table or a lookup chart which you do not have in if-else-if construct. So it's more systematically listed in case statement, which is not there in the nested if-else-if or if-else-if construct. The case statement provides a definitive result when there are X and Z values in the expression. So this is another striking difference, because we can detect the X and Z. Also, we have the case X and case Z, which we do not have in the if-else-if construct. This is very important from the digital design perspective. You can be asked in the interview. So give the difference of if-else-if construct versus the case. The case, once they say, right, you can mention about the case X and case Z, because they are specific to Verilog. So you don't have to go for the case, you can answer this. We are done here with the summary slide. Hey guys, welcome back. In today's episode, we will cover the below points. First, we will talk about the for loop in Verilog. Next, we will go through two different examples of it. Next, we will talk about a different kind of loop which you will find in Verilog only, that is forever loop, and we also give its example. Next, we will go through the while loop syntax, and we also cover 4 different examples of the while loop. Next, we will talk about the repeat loop, which is very much exclusive to Verilog, and we will also give 3 different examples of the repeat loop. Next, we will talk about the disable command, which is the C-style break statement in Verilog. So that's the menu for today. So without any further delay, let's begin. For loop. Similar to for loops in C or C++, they are used to repeatedly execute a statement or block of statements. So, for loop is very much familiar to you from your learning in C or C++. I think that is the first programming language nowadays anybody learns at the school. If the loop contains only one statement, the begin and end statements may be omitted. So, this is a single statement for loop. Next, it controls execution of the associated statements by a 3-step process, which is as follows. First, executes an assignment normally used to initialize a variable that controls the number of loops executed. This is the counter variable that we are very much familiar with the C. Here the syntax is very same. Next, evaluates an expression. If it is 0, the loop shall exit. If it is not, for the loop shall execute its associated statements and then perform step C. If the expression evaluates to an unknown or high impedance value, it shall be treated as 0. Now, execute an assignment normally used to modify the value of the loop control variable. Then it repeats step B. So this is a plain and simple explanation how the for loop operates, and it is very much similar to the conventional for loop that you have learned in C or C++. However, there is a little bit of difference because it's digital and it has some logic which we can see here, the high impedance value, which is kind of very much native to the Verilog only. We are done with this particular slide. Let's move on to the next slide for examples. For loop example 1. So here we will go through the example. First, the for loop implements the logic while only 2 lines as shown in the pseudocode below. So this is kind of structural example, not the code example. So this is this 2 lines. So that means for, and then it call this also the syntax, right? Initial assignment here, then the condition, and then the step assignment, whether this step is increasing, it is going up, or it is going down. this kind of increment counter is here. So this is step assignment. A condition is the checking condition. It keeps on checking and validates that the condition is valid or true. Only then the for loop proceeds for the next iteration. Otherwise it exits. And initial is the initialization. Okay, here goes our statement. This is a single statement. Multiple statement should be contained with a begin here and a end here. So this is for the for syntax, or you can say this is the pseudocode. So here starts our example. You can see we have a counter variable I equal to 0, which is initialized, and then this is the checking counter. So this has to be validated. As soon as I becomes 7, the loop breaks out. And here we start I equal to I plus 1. This is a increment counter. So the value will increase over time. Next, we initialize. This is a bit assignment. So here we initialize the bit of the memory ith bit to the 0. And it is another example. Here the counter variable is I again, and here I is less than equal to bit width. And here we also have the incremental counter I equal to I plus 1, and for that we have another statement inside, which is a kind of different from this one. Here we have a if this condition is true, then we have out equal to out plus. Our expression is here, and this is used for multiplier using shift and left and then end. We are not going to the design details here. Our purpose here is to get familiarized how the for loop is written in Verilog. So I think the syntax and the two examples you are very much familiar now. We are done with this particular slide. Let's move on to the next slide. For loop example 2. Now here we start a 32-bit full adder. I'm not going in the design detail. This is for your learning purpose of the how the for loop works, because in case you are not seeing the example, it is very difficult for you to write any code, whether it is Verilog or whether it is any other language. It is a must for you that you go ahead and see the different examples, get familiarized with their coding style or the writing style, and then you become fluent in writing the code. Here we start our always. Then we have begin, and for n equal to 0, in less than 32, n plus plus, we have the begin. So you can see here we have the begin because it's a multiple statements are coming here. And then we have sum expression. This is the sum expression. And then we have the carry expression here. So here we end our for loop. So for loop starts here and it ends here. And here we end our always block with the corresponding begin and end. So here we are done with the second example. We are done with this particular slide. So let's move on to the next slide. Forever loop. This continuously executes a statement. This forever loop is a different concept from the for loop which you have seen in other programming language. So for loop you have seen in C, Java or something in other language. However, the forever is a kind of print loop which is native to the Verilog. Now in detail, the forever statement executes an infinite loop of a statement or block of statements. To avoid combinational feedback during synthesis, a forever loop must be broken with an @ or negate of clock statement. For simulation, a delay inside the loop will suffice. If the loop contains only one statement, the begin and end statements may be omitted. So this is a style where we have only a single statement inside a loop. You can find this common over the all loops here in this particular video. So this is an important thing. We will exemplify it. Don't worry. Here the syntax of the forever loop is forever, begin, then we have statements and we have end. So this way the forever loop works. Now we are done with the definition and the syntax here. So let's move on to the next slide for example. Forever loop example. We have forever begin. We have begin since we have multiple statements coming here. And then we have @ of clock. So this happens only at the passage of clock. And then we have the statements a equal to a plus 1. And we have end. So this end corresponds this begin. Here it is very plain and simple. Next, we have another example, forever. Then we have @ negate of clock and we have the statement here. Now this should be used with disable or timing control. So here we are done with the forever examples. So here we are done with the particular slide. So let's move on to the next slide. While loop. So here we go for our details for the definition, etc. The while loop repeatedly executes a statement or block of statements until the expression in the while statement evaluates to false. So this is a kind of statement that we understand in any programming language, and we are very plain and simple about that. Next, to avoid combinational feedback during synthesis, a while loop must be broken with an pausage or negage of clock statement. So this is very specific to the Verilog while you are coding in Verilog. Next, for simulation, a delay inside the loop will suffice. If the loop contains only one statement, the begin and end statements may be omitted. So this is, you will see in every loop we are talking here in this particular video. So this is a common statement. Now we are proceeding for the next point. So here we will see the syntax. Syntax is while we have an expression, this has to be true. And then we have begin and the statements here which will be executed inside the while loop, and we end it. This begin and this end ensures there are multiple statements here. We are done with the definition and syntax of while loop, and let us proceed for its example. So here in this single slide we will cover 3 examples of the while loop. First one, this is example 1, and we start with define a register with 7 down to 0 and the name is temp reg. And we have a count 0. So we are not going in the design details or talking about that. We are just exemplifying the syntax by the Verilog code so that your hand is very much free to write the Verilog code. Now we have temp reg, we give it to reg A, and then we have the while loop, and here we have the checking counter. So this has to be true, temp reg, and we have begin here. So here start is temp reg 0 is equal to 1, then we have this expression, this has to execute count equal to count plus 1, and then we have temp reg equal to temp reg. We have a bit shift operation here, and we end the while loop. So this is the end corresponding to this begin. Here we have seen the while loop, and inside we have a if and all these operations that you can write. So this is a simple example of the while loop code example. It is not a design example. It's a code example here so that you are familiar with the writing the Verilog code. We go for the second example. So this is example 2, and where we have the while delay has to be true, and we have begin, and we have a @ pausage of clock. So this we have talked about in the earlier slides. This for the pausage of clock, so that has to go. And then we have this statement that we have, this executes once we enter this while loop. And the next statement is this, because this is, we are not giving a design example. In your case this will be a proper design statement. Here it is just an example of the while loop. This is the style how you write the Verilog code so that you can apply them. Here we end our while loop, and this end correspond to this begin. In earlier slides we have talked about this pausage of clock can be included here, right? And we have exemplified it here. Now we are going for the third one. Example 3. Here we have while not overflow. So this is a inverted logic. So overflow 0, and then we have a bang in front of it to make it a true. So we begin it, and then we have @ negage of clock. So here we have seen the pausage of clock, and here we have the negage of clock, and then we have a equal to a plus 1, and we have end. So here this is a kind of another direct assignment here. So here you can see that we have exemplified both the negage and the pausage of clock along with the while. So here we are done with the slide. Let's move on to the next slide. The fourth example of the while loop. Here we have the example 4, and here we have a range which is 15 down to 0 for buffer, and we have integer k, and always pausage of clock. Here we have begin, we have k8, and while k is true, we keep the while loop running. So here store data at pausage of next 8 clocks. So here we have begin, and we have k equal to k minus 1, and then we have pausage of clock, buffer k equal to data. Now here we end. So this is the start and end of the while loop. So here the buffer is 7 down to 0s, and here we end it. So this is a very plain and simple while loop example, so you can understand it. And here you can see both the always block is sensitized with the pausage of clock, and the while loop is sensitized with the pausage of clock. So here we are done with the example. So here we are done with this particular slide. Let's move on to the next slide. Repeat loop. Now here in the single slide we will talk about the repeat loop, and we will give its example. The repeat loop, this name is very new to you. as the forever loop you have find only in the Verilog. Similarly, you find the repeat loop in Verilog only. So it's native to the Verilog only. So I think in earlier any language like C or something, you have not seen the repeat loop. So this is very native concept to the Verilog. So here it executes a statement for a fixed number of times. So this means it repeats a fixed number of times. We don't have conditions. So we have only a 10 times repetition or 5 times repetition. This way fixed the constant number of repetition. If the expression evaluates to unknown or high impedance, it shall be treated as 0 and no statement shall be executed. This is a native conditional checking for the repeat loop. Next, this is non-synthesizable. So this is the most important part while you are using. So keep in mind, this is non-synthesizable. That means you cannot use it for a synthesized process, and you cannot use a commercial synthesize tool here to get something from the repeat loop. So you will not get anything. So here we have the parameter size 8 and long size 16. So these are two parameters we are defining. These are just constant. So parameter is nothing but a constant. We will talk about all these data types and all in some other episodes where we will talk about all these data types and all in detail. For now, you see this example, and here we have the range defined with the, here also you can see that we have OPA, OPB and result. So here you also have another thing defined. So letting here the marking. So you have seen all these things have been defined. So I'm not going in the design details. It's just a code example so that you get familiar with the coding style. And here we have initialized this thing, and similarly we have initialized these things here. And here we start the repeat loop. Here is the how many times you have to repeat. Size is 8. So this repeat loop will repeat 8 times. So here we begin loop with the begin command, and here we have the if condition and corresponding action is taken here, and we have the another expression. Similarly here the third, and finally we end our repeat loop here. This end corresponds to this begin. So you can see that we have a fixed number of times, that is 8 times we will repeat, and we give that number here. If we change here, right, the number will change here. So this will repeat 8 times. This way you can have a controlled execution of a loop. Repeat loop is a kind of controlled execution. We are done here with the first example. We have the second example now. So here repeat it, and we have the begin, and then we have the if condition. It's a single line if or the inline if. If this is true, then this will be executed. So here p equal to, we have a bit shift operation, and here this one, and here we end it. So we have here the second example of the repeat. So since all these statements are contained, so we use begin and end. If there is only one statement coming here, we would have not used the begin and end here. So since this is not a design example, it is just the coding style, you can see. So here we have a inline if. The entire if thing is ended here, and rest of the statements are part of the repeat only. We are done with the two examples of the repeat loop here in this particular slide. So let's move on to the next slide. Repeat loop example. So here we are going to see the third example. We have parameters defined, cycles equal to 8, and we have counter, right? So this is the repeat loop counter, and we have defined the buffer, right? We have integer, right? And we have always passage of clock, and then we have the begin and k equal to 0, and we have repeat, then cycles. So here we have defined cycles, and here we have used it, and here store data at the passage of next 8 clocks, and here we begin. So here we have our at the rate passage of clock. We have the statement where we are storing the data, right? We have k equal to k plus 1 and end, and then we have the end. So this end ends the repeat, right? And this end ends the always. You can see we have used both passage here and passage here, that is of the clock, and we have multiple statement inside the repeat, as well as we have multiple statement inside the always. So we have, in both case, we have used the begin and end, and here also begin and end. So here we are done with the particular slide. Let's move on to the next slide. Disable the break statement. Now we have came across multiple loops here. However, we have not seen any of the break statements used in Verilog. However, in Verilog, the breaking style or the break statement is a different, and that is called the disable statement. Here we will see how to use it. Now, execution of a disable statement terminates a block and passes the control to the next statement after that block. and it is like the C-like break statement, except it can terminate any loop, not just one in which it appears. So it is much more powerful than the C break statement, and you will see in the example how it is powerful. I'll explain then. Disable statement can only be used with named blocks. So this is another good point. The named blocks are terminated using the disable statement. Otherwise, if you don't have a named block, cannot terminate. So far, we have not gone in very detail of naming block. However, this is very easy in this particular slide only with an example how to name a block. And here the statement and here the syntax is the disable, then the block name. Here we begin a block. So this begin could be a begin of any of the loop, and here we have the accumulate word, and then we have the forever, and then we begin, and then we have at the rate passage of clock, and a equal to a1, a equal to a plus 1, and here we have a if condition. If this is true, then disable the accumulate. We have not ended the accumulate blocks, we have started the accumulate block, and everything inside it is under this accumulate block. And here we end means here we end the forever one, and here we end means we end the accumulate block. Now let me clear the markings. Now in this particular statement, you will see that if this condition happens, then this particular block, not only this forever one, this particular block, the entire block stops operate, and the execution goes to the next line of code or something like that, or however the code is organized. Just you use the disable statement, right? You have to use begin, then you give a name to it, the block on which you have to operate, and then you end the block with the end keyword. So begin and end here used for naming a block, and that block can be terminated using the break statement, and this is used like the C break statement in Verilog in any of the loops so far we have discussed. Here we have exemplified with the forever. However, you can go ahead, use it with any other block. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we'll do an introduction and we'll talk about what is a generate block. Next, we will show an structural example how the generate block looks like. Next, we will talk about the local param and the Genva reference, which are very much specific to the generate block. Next, we will talk about the Defparam and its use in generate loop. Next, we will talk about implicit array in generate blocks. Next, we will talk about generate blocks, hierarchy and error. Next, we'll start our section for different examples like legal or illegal coding and parameterized continuous assignments in generate block. Also, we'll see the example of generated ripple adder and multi-level generate loop example. This way, we'll cover all the points in our today's episode. Without any further delay, let's begin. Introduction. Generate constructs are used either conditionally or multiply instance generate blocks. So these are the two ways that a generate block constructs are used. Next, a generate block is a collection of one or more module items. A generate block may not contain code declaration, parameter declaration, specify blocks, or Specparam declarations. I think the specify and the Specparam, these two have not discussed yet in this series. We will later discuss in some other episode. But for now, you know that all these things may not be contained in a generate block. Next, all other module items are allowed in a generate block. So apart from these modules, right, these things, we can use any other module or related stuffs that we have came across so far. Next, the elaboration of generate construct results in 0 or more instances in a generate block. So the elaboration step happens when the simulation tool is run. So it is one of the sub-steps. So during that particular sub-step, a generate construct results in the expansion in either 0 or more instances in the generate block. So this is somehow similar to the concept of flattening. That means we have a description which get flattened during the elaboration, and the generate blocks get flattened during the elaboration. The keyword pair generate and engenerate may be used in a module to define generate region. So these two keywords may encapsulate the things that should be contained in a generate block. So that's our introduction for the generate block. We're done here with the slide. Let's move on to the next slide. How the generate block looks like. Here we'll have a structural example. Here goes the structural example. The generate block looks like we have a generate keyword, then followed by for loops, if-else statements, case statements, and instantiation statements. Instantiation means we have different predefined modules or the existing modules which came in the library, right? All the instantiation statements. And then finally, we use the end generate keyword to encapsulate the entire generate block. So the generate block starts here and ends here, and in between it may contain all of these things. This is a structural example of the generate block. We are done with this particular slide. Now let's deep dive inside the generate block concept. What is generate block? Now we will have a much more in-depth view of the generate block apart from the introduction we have just came across. So let's start. A loop generate construct permits a generate block to be instantiated multiple times using the syntax nearly similar to a for loop statement. So once after a couple of slides of a description, once we go for the examples, you will see and you will able to relate this comment. The looping variable shall be declared in a genvar declaration. So this genvar is a special variable and this is a specific keyword as to be used for the generate block, and that particular looping variable means like a for loop we have a looping counter and generally we use I equal to something like. So that I here has to be defined by the genvar declaration prior to its use. So remember, we have to declare the genvar prior to its use. The genvar is used as an integer during the elaboration stage. So it gets flattened during the elaboration stage of the simulator. It evaluates the generate loop and create instances of the generate block. It vanishes way before the transient digital simulation start. A genvar is limited to use in nowhere other than the loop generate construct only. Both the initialization and iteration must be done using the same genvar. So here we are done with the in-depth question of what is generate block. Now we will have some additional information about this generate block in the next slide. So let's move on to the next slide. Localparam and genvar reference. Let us see what these things are and why they are important. An implicit localparam declaration automatically happen within the generate block of a loop generate construct. So this happens automatically, a localparam declaration. This is an integer parameter that has the same name and type of the loop index variable. So loop index variable which is defined by the genvar. We have just talked last slide. Its scope remains up to the generate block decided at the time of the elaboration process step. So this scope remains within the generate block. So it do not go out of the generate block. That means this integer parameter. In the examples you will come across all these things. Now we are going through the theories. This parameter can be used anywhere within the entire generate block as a regular integer parameter. Remember, this is an integer, right? And in digital electronics, it is not a voltage or something, it is an integer. So this is the identity of this parameter. It can be referenced with a hierarchical name. So we will see in the examples how the hierarchical name will come out. Because this implicit localparam has the same name as the genvar, any reference to this name inside the loop generate block will be reference to the localparam. This is another kind of mapping we have, and it will not be reference to the genvar. Hence, it is not possible to have two nested loop generate constructs that use the same genvar. So this is very, very important. So we cannot have two nested loops with the same genvar. So this is the reason, because it will create reference and that will refer to the localparam. Now we are done talking about the localparam and the genvar reference in this slide. So let's move on to the next slide. Defparam and generate loop. Now we will talk about what a defparam is and how it is significant to a generate loop. First here, we talk about some points. First, using the defparam statement, parameter values can be changed in any module instance throughout the design using the hierarchical name of the parameter. So this is the basic definition of a defparam. However, a defparam statement in a hierarchy in or under a generate block instance or an array of instances shall not change a parameter value outside the hierarchy. So this is very much specific to the generate block. How a defparam should behave in a generate block. Next, each instantiation of the generate block is considered to be a separate hierarchy scope. These all things will come out in the elaboration step and it has to be remembered. Now let us see a short and sweet example here. We have genvar I, we have generate, and here we have I equal to 0, I less than 8 and I equal to I plus plus. So this is the counter, for loop counter, and we have a begin, and here we have given a name, that is some name. This is just a name for this particular for loop. Now we have our plop instantiation here. Next we have the Defparam statement, and this way we have written the Defparam, and we end our for loop here. And finally we end our end generate. So this is generate and end generate block. So this way the Defparam, that means this Defparam can be used inside the generate block. So this is just an example. When we are going through thorough example, you will be able to see its use. So here we are done with this particular slide. So let's move on to the next slide. Implicit array in generate blocks. This is another significant concept that you must know before you use the generate block in hand. Generate block in loop generate constructs can be named or unnamed. Generate block that consists only one item don't need the begin or end keyword. So this is another freedom. If it contains only one item, the begin and end keywords can be omitted. If generate block is named, an implicit array created consisting of the generate block instances. So for a named generate block, right, implicit array is created. The index values of this array are the genvar values during the elaboration. So everything happens during the elaboration. This can be a sparse array because the genvar values do not have to be in the form of a contiguous range of integers. You understand the contiguous means, right? One after another. Here, this can be a sparse array where things are not contiguous. The array is considered even when there are no instances of the generate block. So this is another good and important point to be remembered. Now we have talked about the implicit array and generate blocks. Now let's move on to the next slide. Generate blocks, hierarchy and error. We will see about the hierarchy and errors that we may face. If the generate block is not named, the declaration within it cannot be referenced using the hierarchical names other than form within hierarchy instantiated by the generate block itself. It shall be an error if the name of a generate block instance array conflicts with any other declaration, including the other generate block instance array. Next. It shall be an error if the loop generate scheme does not terminate. It shall be an error if a genvar value is repeated during the evaluation of the loop generate scheme. It shall be an error if any bit of the genvar is set to X or Z during the evaluation of the loop generate scheme. So these are good points. You have to be very careful and remember them. We're done with this particular slide. So let's move on to the next slide. Examples. Here in this slide and the next slide, we will give some examples which are legal and illegal. That means you may face error or you are okay. So let us see the example and case by case we will talk about. First one, here we have a module, mod A, and we have genvar declaration. This is I, and then we are omitting these things, right? Or generate and end generate keywords are not required here. In this example, we have not used it. We have a for loop with the genvar, and here the counter runs with the genvar, and we have the name A. We have the same genvar here in the counter of the next for loop, and the name is B. So you can see this is kind of a nested, right? And we have the statements and etc. here. And here you will face an error because we are using I as a loop index for two nested generate loops, and here we are using the same genvar here, and this I used in both of the counters of the nested, and this gives an error in the Verilog code, and we complete our code here. So this you cannot do, right? So you have to keep in mind. That means this is a illegal one. Let's go to the next example. We have a next module mod B, and here we have genvar I, and we have reg A. We have a for loop begin, and we have given the name A. We have the statements, and then we face an error, right? Why? The error is for the A conflicts with the name of the reg A. So here it is A and here it is A. So that's why it will face the errors. And here we end it, and the module is ended. So here in this slide, we have seen two different errors, which are the illegal use of the genvar. So you know what not to do right now. Let's move on to the next slide, where we will see the similar category of an example. we have module C, and we have again genvar, and we have a for loop, right, where we have the counter here with the genvar and its name is A. Or we have all the statements and we have the end for this particular for loop. Next we have another for loop where we have another counter where you can see this is different and the checking counter is also different, and here we give a name A, and we have the internal statements of the for loop. Then we here face an error because here A conflicts with the name of the previous loop even though the indices are unique. So here you can see here this have a clash with these because these two for loops are different, and here we put the end and end module. So now you know that the two different for loops which are not in a nested format but have the same name, it may have a clash. This is illegal. You know what not to code with the genvar. Here we are done with this particular slide, so let's move on to the next slide. Parameterized continuous assignment example. So here we start our example. We have the module gray to binary 1, and this is binary and gray. We have parameter size, its size is 8. This module is parameterizable. Output is size -1 down to 0, and this is pin, right? This one is the output, and input is size -1 down to 0 is gray. This is the input. We also have the genvar here, and we start our generate block with the generate keyword. Next we have the for loop, and here the counters are there and its name is bit. We have assign statement here, and we are using this equation for the assign, and here I refers to the implicitly defined local param whose value in each instance of the generate block is the value of the genvar when it is elaborated. So this is the way here we are using the I, and also we are using the local param here. So let me read out again in a continuous mode. I refers to the implicitly defined local param whose value is in each instance of the generate block is the value of the genvar when it is elaborated. And here we close our generate block with the end generate command, and we end our module. So here in this example you have seen how a parameterized module can be fitted with the generate block. We are done here with the example. Let's move on to the next slide. Generated ripple adder example. Here we go with our code. Here we have the module adder gen, and we have the all PO, sum, A, B, C, I. So this is carry out, this is carry in, and this is A, B, this is sum. So here we have the parameter size 4. We have the output size -1 down to 0 sum, and we have output CO. We have input size -1 down to 0 A, B, and we have input CI, and also we have where size down to 0 C. Here our definition has ended and our genvar is declared here. Genvar is I, and we assign PO equal to CI, and here is our for loop using the genvar. That means here our generate action is started and the name is bit. Here we have the statements going inside. First we have the where statement, then we have the XOR instance, and we have the another XOR instance, and we have the AND instance. So these are primitive gates, right? And we have the AND instance here, and we have the OR instance here. So this is a kind of structural modeling happening here. You can see the entire block here is the structural modeling, and here we end our for loop. So in the episode of structural modeling, I have talked in detail how the structural modeling happens with the explicit diagrams. In case you have not watched that episode, please go ahead and watch it from the playlist. Here we have the assign CO C size, and here we have the end module. Here the code is done. Now let me give the things that come in the elaboration, right? Here the hierarchical gates instance names will come in the elaboration, like XOR gates will be like this, and this is another XOR gate. Also we will have AND gates with this kind of hierarchical name, and this is another AND gate. We have also the OR gates, and this kind of hierarchical names will come. And the gate instances are connected with the net named. This is the net name, right? And this is another hierarchical name, So here we are done with the code example, and we have seen how the elaboration helps to get the hierarchical instances of the gates as well as the nets. So this way, the generate block gives birth to the hierarchies during the elaboration. We are done with this particular slide. Let's move on to the next slide. Multi-level generate loop example. Here we start our code, and here the parameter size is 2. Here we have multiple genvars I, J, K, M, and we start our generate block with the generate keyword, and we have first for loop, and its name is B1, and next we have its statements, right? Next we have the next for loop which has B2, and here we have the instantiates this one, right? First on instantiate this one, and here is the third for loop, and so these are nested, right? So you can see the things are proceeding down and down, right? Here first I, J, and then K. Here it was I only, here it is I and J. So this way you can see the hierarchies go down. Now we have here instantiates this one, right? I, J, K, and then N3. Next we have an end, and then we have the if, right? This is B4. If block has the name B4. This is scope is that P1.B4. Here we have another for loop whose name is B5, and it gives birth to the scope of this, right? B1I, B4, then B5, and then M. Then we have the instances here with this hierarchy, and then we have end generate. You can see in the code this multi-level. That means we have a multiple nested loops are there, and here we have used different genvars for the different hierarchies. The first hierarchy is with I, second one with J, third one with K, right? And here the fourth one is with M. So here you can see that we have used the proper legit code for the hierarchies using the genvars and how the things go inside and how these things are expanded. So here we are done with our particular example in this particular slide. Hey guys, welcome back to the computer screen. In today's episode, we are going to discuss the below points. First, we will do an introduction. Then we will directly jump on to the two example of if else, and in example 1 you will also find the use of case where the if else is the prime one and case will be within, and in example 2 you will see pure if else example inside the generate block. And in the next example, that is example 3, we will exemplify the generate block with the case. So the case statement. So this is pure case, this is pure if else, and this is a mix of if else and case. That's the menu for today. So without any further delay, let's begin. Introduction. The conditional generate construct select at most one generate block from a set of alternative generate blocks based on constant expressions evaluated during elaboration. So the conditional generate statement at least gives birth to one expression during the elaboration. There are two types of conditional blocks, that is if generate, that means if else and generate, and case generate. These are the two types of conditional blocks that can be used within the generate block, and generally people use them because either they have to use a straightforward code in the generate block, which is a very straight and simple use, which we have already talked in last episode, or in a complex case. Generally there are different state of a machine, right, for a state machine. In that case, either we will use case or we will use the combination of if and case. That depends upon how complex the machine operates. The selected generate block, if any, is instantiated into the model. Generate blocks in conditional generate constructs can be named or unnamed. So this is very important. So the blocks which we are using, right, either they can be named or unnamed. So in today's example, we will see both the named and the unnamed as an example for the block's name. Generally, each of them may consist of only one item and hence devoid of begin and end keywords. So this is a general practice, because if you make the code too much complex, right, then it is difficult for you to instantiate the things. Hence, generally in one particular if or one particular case, generally we have a single statement, that is an instantiation of any particular maybe gate or maybe user generated or user defined or any digital circuit. So this thing is very much important here. Since generate blocks are flattened during the elaboration, it is permissible to have more than one block with the same name in the alternative scope within a single conditional generate construct. So now here are a couple of important points to anchor upon. First one is more than one block can have the same name. So we are using a construct, right, where multiple conditions are there. So there it could be the blocks could be have the same name. So the names could be same. However, they should be in the alternative scope. So this is first scope and this is second scope and this is third scope. So you can see here the name is same, here the name is same, but the scopes are very much different. So scopes are not the same, but you cannot have the two different blocks with the same name within the same scope. This is not permitted. These are the things you should know before we proceed with the examples, and hence we are done with this particular slide. Let's move on to the next slide. Code example. So here it is if, else and case. So it is a combined example. First we will see a combined example. Later we will see individual examples of the if and else and case, obviously. First, this is the code to generate e1.g1 instance or no instance. So either this will be generated or no instance will be generated using the generate block methodology. So in this way, we will code the constructs, that means the if, else and case, so that this condition is satisfied. First, we did the module test. Then we have the parameters p and q defined with the initial values. Then we have defined where as ABC. Then our condition starts here with if p equal to 1, and then we have a nested if q equal to 0. So that means this is the condition for if p equal to 1 and q equal to 0. Then instantiate what? Then instantiate AND-GET with the hierarchical name test.e1.g1. Since we are writing here, so you can see test.e1.g1. So here only at this condition p equal to 1 and q equal to 0 is instantiation will happen inside the generate block. Next we have the else if then q equal to 2 and p equal to 1 q equal to 2. So here you can see q equal to 0 and this is q equal to 2. So this condition reaches only if p equal to 1 and q equal to 2. So here you can see that OR is here, hierarchical name here. So this is instantiated. So for p equal to 1 q equal to 0 and is instantiated. For p equal to 1 and q equal to 2 or is instantiated. This way the instantiation is happening. Else is added to end if q equal to 2. Q equal to 2, this is ended by this else. And if p equal to 1 and q not equal to 0 or q equal to 2, then there is no instantiation. So this is a blank, right? So there is nothing here. Else if p equal to 2, we introduce our case inside it, and case is controlled by q. So for case 1 or 2 or 0, so you can see 0, 1 or 2. That means if p equal to 2, so this is satisfied, and q equal to 0, 1 or 2, then instantiate X or get. So you can see the first set of if were for the p equal to 1, and here the second set of things will be for p equal to 2. Whatever happened inside is in if else format, and whatever happening inside is in case format. So both examples are shown in the same example, in the same code. Now here we introduce our default condition, that is for that comes along with the case, right? If p equal to 2 and q not equal to 0, 1 or 2, then instantiate X not get. Here we also satisfy that if these things are not there for q, what to do? Just instantiate X not. And here we end case, and here we end module. Here although you cannot see any generate keyword, but you can understand that this code can be easily packed inside a generate statement, and you can use these if first and then the case in the second to generate different get instantiations. You have to have the example of the coding style, how you can use the if and else. Here this is combined. Now let's move on to the next slide where we give the detail of this example. Code 1 explanation. This generate construct will select at most one generate blocks module named U1. So you can see for two different conditions. For P there are two values, right? First value and second value. And Q also there are P values, P different values, or otherwise there would another case. So that means all cases are covered. At most one of the generate blocks will be created using the generate statement and the case and if combined code. the hierarchical name of the gate instantiation that in that block would be s.u1.g1. So you can see the hierarchy, right? So hierarchy is easily understood here. Previous page code I have just explained. u1.g1 instance is one of the following gates. And or XOR XNOR is generated if P and Q combination is 10, 12, 20, 21, 22 and 2 and default. So this way we have covered all the possibilities. That means all the permutation and combination of P and Q, which we have defined as a parameter in the last example. And you can see that we have covered all the cases. So at least using this particular code, you are sure that you will instantiate at least one gate using the generate block. So we are done with the explanation. Let's move on to the next slide. Code example. This is code example 2 and this is about if-else. So here we are using pure if-else and not any if-else and case combined as we have seen in the last example. So this is the parameterized multiplier module, and here you can see module multiplier A, B and product. We have A width, so we have defined two parameters to define bus width. Here A width and B width, and local param we have defined product width A width plus B width. Next can be modified either with the Defparam statement or module instance statement. Input A width -1 down to 0 A. Input B width 1 down to 0 B. So these things are here. Output product width -1 down to 0 product. So here we have defined all the buses, right, for the input and outputs using the parameters here which we have defined, and here we have also the derived parameter, right, the product width. Next we use the generate statement here and we start our first if condition here. If A width less than 8 and B width less than 8, begin mult. So this is the block name which we have just talked about in the first introduction slide. So this is the name of the block. So you can see this is the instantiation CLA multiplier. A width, B width is nothing but carry look ahead. Here it is instantiated as a CLA multiplier. And here we end. So begin and end. Else begin mult. So you can see mult is again used here. However, this is a different scope. So this is the scope of if and this is the scope of else. So we have two different scope and we can have the same name here. And here it is Wallace multiplier and we have the instantiation statement. In the if condition we have CLA and in the else we have Wallace multiplier. Next we end it. The end corresponds to the else here. And here we end our generate statement, so it corresponds to the generate. And here we end our module, so end module corresponds to the module statement here. So we are done with the exam. I hope you have understood it very easily, because rather than understanding every bit of the thing, the style or in the fashion how we are writing the thing is important to you. I think you have understood that what we can do and what we cannot do using the codes inside the generate block. So you can see here another thing I would like to suggest here. You can see the generate statement can be just placed ahead of the if-else block and it can be ended in the end generate. In the previous example, that means in the code 1 we have just discussed, you can similarly insert the generate just beginning before the if, and you can insert end generate when the both if and case has been covered, right? After that you can end generate. So this is the way you can code. So here we are done with this particular example. Let's move on to the next example. Code example 3, and this is a pure example with the case statement. Here we start our code with the generate keyword and we have the case statement at the beginning, and the case controlling variable is width. So we have just skipped the things that we write before and we have just jumped to the generate statement, because in the previous example you have seen what we write in the initial, right? All those things you were done here. So you can just understand the generate statement here is width, and for width equal to 1. So if width is 1, what will happen? We'll begin adder. So this is the name of the block. And here we have this code, and this is 1-bit adder implementation, right? We end this one. Let me clear the markers. Next we have the adder, and it is a 2-bit adder, right? And here the width, if it is 2, it goes to here. And here we have the 2-bit adder. We end this block. So you can see the name is same, but the scope is different. So we can have the same name in the different scope. Next, we use the default. If width is not 1 or 2, our control comes to the default one. Again, we are using the name adder here, and here in this default, we will have the carry look ahead, abbreviated as CLA sometimes, that adder. So here we have the adder CLA instantiated, and here we end it. The default will generate the CLA adder, and here we end our case. So this corresponds to this case statement, and here we use the keyword in generate, which corresponds to our generate keyword. So we are done with this particular example, and it is very short and simple example to understand the case statement that can be used within the generate and in generate. That means the generate block. We are done here. Hey guys, welcome back. In today's episode, we are going to discuss the below points. What is where, that is net, in Verilog. Next, we will give some more specific detail on wheres. Next, we will talk about what is a register data type in Verilog. Next, we will give more specific details on the register data type, that is reg in Verilog. So there comes a inevitable question, are the where and the reg are interchangeable? We will intercept this question and its answer. Next, we will compare the circuit implementation of where versus net through infographics. Next, we will discuss the use of where versus reg for a particular module and when it is used in the test bench. Next, we will go through some legal and illegal definition and use of the where or the reg through examples. Here we are done with this particular slide. Let's move on to the next slide. What is where, which is a net in terms of the VLSI perspective in Verilog. Where, physical where in the circuit. So you understand the physical where which you use in breadboard to connect different components to make a analog circuit or a digital circuit. So where serves that purpose in Verilog. A where does not store its value. So this is the most important thing. Where cannot store a value, and it must be driven by connecting the where to the output of a gate or a module and assigning a value to the where in continuous assignment. So in earlier episode, we have discussed about the continuous assignment. Please go ahead and watch that episode in case you have not watched. A where net type variable can be used to connect signals together using continuous assignment. Here, we must emphasize that we cannot use where in the left-hand side assignment of any procedural block. So this is a very important thing. We cannot use in the left-hand side of a procedural assignment. There are different types of nets are available in Verilog. These are where, want, var, try 0, supply 0. You can see all these things are available in Verilog. Next, we have try reg, try and, try or, try 1 and supply 1. In case you want to go to the detail of each of them, I will suggest you to go through the language reference manual, that is LRM, for Verilog. Alternatively, now since the Verilog is a subset of the system Verilog, you can also find the definitions of these type of nets in the system Verilog LRM. Now let me give a small example of the where. Here we have the input definition of A and B, and we have the output definition of sum and carry. We can use the where as is in the input or output definition, like here we have used. Next, we are using the assign statement. It's a continuous assignment as we have mentioned here. Then sum is equal to A XOR B. And we are also assigning the carry, which is a where carry is equal to A and B. This way, the where can be used for defining the data type of the interconnects, and for where you have to use the assign statement like this for a continuous assignment mode. So here we are done with this particular slide. Let's move on to the next slide. More specific on wheres. We have gone through the definition of the where. Now we will give some vivid detail of the wheres that you can use in an interview purpose when questions are asked. Now let me go to the detail. Where elements in Verilog are simple wheres or buses of arbitrary width in Verilog designs. Stateless way of connecting two pieces of Verilog based design. Can only be used in the model combinational logic. Connect input and output ports of a module instantiation together with some other element in your design. Used as inputs and outputs within an actual module declaration. This must be driven by something, cannot store a value without being driven. So this is a limitation. The only legal type on the left hand side of an assign statement, that is the continuous assignment. cannot be used as the left hand side of an equal to or less than equal to sign in an always block. This cannot be used. The where related terms cannot be used with these signs inside the always block. So here we have listed out a lot more detail about the where, which you can use, you cannot use, which is the limitation and the advantage, whatever we have captured here in this slide. So we are done here. Let's move on to the next slide. What is register? Register, not the register of a CPU, that is a central processing unit. We have some memory units which are called register. So this is not that register. You have to be very specific in your mind. This is the register of the Verilog language. No guarantee to be a DFF, that is D flip-flop, may be a physical where. The register can be a physical where, holding its value until a new value is assigned to it. The speciality of the register or the reg type is that it can hold a value until that value is replaced by some other value. It is event driven. You understand the events in terms of the Verilog, right? A register that is reg type variable can only be driven using a procedural block that is primarily the always and initial. So this is a very direct contrast with the where it cannot be used in this kind of blocks. On the contrary, the reg type has to be used inside the always or initial block. We have to remember that we cannot use the reg in the left hand side of the continuous assignment. So this thing we have to remember. So this is a word of caution and hence we have colored it with the red color. Let me give a small example here of the reg type. Reg CLK, and then we have the always block beginning here, and we have after every 5 time unit the clock is inverted. So this is valid and this is end. So you can see we have defined the reg type variable clock here, and we have used inside the always block, and here after every 5 time delay unit we are inverting it. That means we are changing it until a value is changed. The reg is holding the value. After certain time, here it is the 5 time unit, the value is inverted, and once it is inverted it keeps on the inverted value until that is changed by the next inversion. So this is the short and sweet example of reg, and here we are done with this particular slide. So let's move on to the next slide. More specific on reg. Reg elements are similar to wheres but can store the information which is called state like physical registers. So this is a similarity with the physical registers in digital electronics. The only legal type on the left hand side of an always block is equal to or less than equal to sign. The only legal type on the left hand side of an initial block is the equal to sign used in the test benches. So these are the 2 points you should remember in the always and the initial block terminologies for the reg. Can be connected to the input port of a module instantiation. Any input port of a module can be connected with a reg which is not the part of that module. Can be used to create registers when used in conjunction with the always at pausage of the clock. That means you can use with the pausage or negage, all this type. That means the age sensitive operations can therefore be used to create both combinational and sequential logic. So this particular register elements can be used in combinational or sequential circuit design. Can be used as the output within an actual module declaration. The reg type of variable can be an output port. Cannot be used in the inputs within an actual module declaration. So when we are writing a module itself, we cannot use the reg as the inputs. Cannot be used on the left hand side of an assign statement. So if we have a continuous assignment using the assign statement, we cannot use a reg type variable in the left hand side, that is the LHS. Cannot be connected to the output port of a module instantiation. So these are the things you should remember about the reg, that is register type variable in specific when asked in an interview. We are done with this particular slide. Let's move on to the next slide. Here you can see the question is, are where and reg interchangeable? Here in this slide we'll discuss about this question and its answer. The where and reg elements can be used interchangeably in certain situations. In certain situations, they are interchangeable. Except them, they are not. Both can appear on the right hand side of an assign statement and in an always block. For the equal to or less than equal to signs. So on the RHS, not on the LHS, remember this. On the RHS, whatever is coming, there the where and the range are interchangeable. Next, both can be connected to the input ports of a module instantiation. As an input port, when we are giving some input, maybe in a test bench or maybe in a broader module, as an input we can connect the range to the input as well as the where to the input. So these are the part where you can interchange the where and the range. Where versus range. Infographics. Here in this slide we will understand the difference of a practical use, that means the circuit implementation of range versus where through an infographics. Here is our digital circuit. You can see these are the AND gates, OR gate and NOT gate. So these are very familiar. This is a simple circuit here we have drawn, and here this box represent our module, and here you can see that we have connected from, these are the port, right, of the module. If you compare it with a physical chip, here we have connected them with some interconnects, this interconnect, this interconnect, this and this type of interconnect. So these are different interconnects we have used in this module. We are not naming it because it is irrelevant for the understanding perspective. However, you can understand that these things how are important for the where and range. So this is a Verilog module or instance. You can think this is of an instance in terms of the Verilog circuit, right? And here we have the where or the net. Which are the where and the net of the interconnects that I have just highlighted a few minutes back are this. That means wherever we are connecting these things, right? These are wheres, right? And next we point out the registers. Registers are what? This one is a register. This one is a register. And this one is a register, because let me explain why these are registers. So here we have to use a value, and that value must not be flickering. That means whenever we are using the value should be stable. Whatever we are connecting to the input of a module, if this is a test bench and inside you instantiating this, then this is a must. So this must be registered, this must be registered, and this must be registered. And when this is a test bench, right, or maybe in a bigger module, right, there whenever we are using this output to go to somewhere, in that case what happens, this value has to be stable over time. That means this value might not flicker over time. That's why this has to be the range type. So here you can understand the where or net and register. These are the things that you must take care. So in this slide you have just pictorially, that is through the infographics, you have understood what is a where type net, where to use it, and what is a range type net and where to use it. So here. So you have understood from the circuit connection perspective the usage of where and register. We are done with this particular slide, so let's move on to the next slide. Where versus range, test bench perspective. Here in this slide we will discuss the where and range when we write a module and when we write its test bench, how the where and range should be applied, where and why. So here is a simple module of a Not-Gete that we have shown in, I think, in the first couple of episodes. And here it's input, here it is output, and here is the assignment where output is the inverted input. And here we end our module. So this is our module. You can see next we write its test bench. So this is a test bench. We write the module test bench name and we write with CLK, not the gate input, the Not-Gete input, and where out shift, that is the Not-Gete output. So this module has a input and output. When we have to use it, right, we are defining input as range and the output as where in the test bench, not in the module. In the module we have used it like where. Next we write our initial block, and there we write our dump commands for dumping the VCD and the display command, that is the print command on the screen. And we continue with our variables, and then we initialize the clock with 1. So this is the initial block, and then we initialize the clock with 1. Next, at 50 time units passed, we hit the finish with the $finish directive. Next, we end our initial block, and then we write our always block, start with the always begin. And after 5 time unit we invert the clock. That means after 5 time unit the clock will be inverted. Now see, this has to hold the value. So this is the type range. You can see this range is inverted, and the inverted value is hold for 5 time units, and after that it is inverted again. And here we end our always block. Next we instantiate our Not-Gete. So this Not-Gete is instantiated here, and what happens, we give our range to the input and where to the output. So this way we connect the input with the range and output with the where. And here we end our test bench with the end module command. So with this simple example, you can understand when a module is written and it is used in the test bench, how to define the input and output with range and where. Hope you have understood the difference of usage of where and range in terms of a module versus its test bench in Verilog. We're done here with this slide and the example. Let's move on to the next slide. Legal versus illegal examples. Module my and YAB. Their out is Y, input is A and B, where we write for the Y. And here we have a always block, that is an inline always block for @ A or B. That means whether these are sensitive, that means when these are changing, Y is A and B. And here we end our module. So illegal left hand side assignment. So you can see this is the mistake we are doing here, and replace the declaration where Y with the range Y. You can see here we have done the mistake. Since these examples of legal versus illegal, some of the examples will be legal, some of them will be illegal. So here what is illegal? We have written Y which is in the left hand side, right? And we have written it as a where it should be as range because it has to hold the value for a time being, and here it should be replaced with range. The next example, we have the module my and YAB. Output Y, input AB, and we write range Y. Assign Y equal to A and B. So here it is the illegal assignment because this is a continuous assignment, and here we have used the range in the left hand side. Either we remove the range Y declaration or we change it to where Y. You can see the legal versus illegal. That means for the same module, when we are writing it with the always block, that means a procedural code, or a continuous code, that is with the assignment, right? Whatever we use here in this continuous one, range in the left hand side is illegal. Here in the procedural, where in the left hand side is illegal. So if we change here it to where to range, this will be legal. And if we remove range Y or write the where Y here, this becomes legal. Legal and illegal you can understand with this example, and whatever theories we have explained so far and the examples and the infographics we have used so far in this particular video, I think now you are able to understand and differentiate what is illegal in the code and why this is illegal. So here we are done with this particular slide. Let's move on to the next slide. We continue our legal versus illegal examples here. Here module my driver. So this is some driver. You don't have to focus what type of driver. Here Y, A1, EN1, A2, EN2, all these ports are there. Output is Y. Input, all these four are input. And assign, we have a ternary operator here, and again we have a assign ternary operator here. We end our module here. Here multiple drivers on a common net using the continuous assignment. Module my other driver. We have the same kind of ports here, and we have output Y. Input, all these fours are inputs. Range Y, always block, right? We have the sensitive A1 or EN1, and we have the if block, else block, right? And we have the code proceeding, and we have the always, again another always where A2 or EN2 is there. And here we have the if block again, and we have the else. Now here we have Y equal to 1 tick BZ. Multiple assignments to a behavioral variable. You can see there are multiple assignments to a behavioral variable using always block assignment. You can decide whether which one is legal or illegal on your own, because here we have not used the always block, that means a procedural code. Here output Y, either we can write here the where or we leave as is, and whatever assignments you are doing is okay. And here when we are using the range, right, in the always block, right, whatever we are writing here is okay. Hey guys, welcome back. In today's episode, we are going to discuss the below points. Basic data dealing in Verilog. So here we'll talk about how many types of data are there and how you can deal with them. Next, we will go in detail of data and literals. Next, we'll talk about the different data types handling. Next, we will go explicit detail of time, registers and variable usage. Next, we will provide example for literals and their interpretation. Next, we will talk about how we can use the format specifiers to print the different data formats and variables during a simulation. Next, we will talk about very important directive, that is the backtick timescale in simulation with examples, and it has to do with the time data type, whatever data type we are talking about here, and we will also talk about that. Next, we will go through a code example of the backtick timescale with different variation, and we will compare the outputs. This part will be very important for you in case of both simulation as well as for the interview preparation. And this part will be important for your understanding as well as interview purpose. So the entire episode is very important. Pay attention properly, and we're done here with the menu. So let's move on to the next slide. Basic data dealing in Verilog. Here you can see the table. What are the basic data that we deal in Verilog? That is 0, which is a logic 0 or false condition. Logic 0 when we are exchanging data among the logic gates connected by nets. And it is a false condition when we are using it in the if condition. Next is 1, it's a logic 1 for circuit connection, and it's a true condition for the if condition. Z is the high impedance state, and this is strictly for the circuit connection and circuit data exchange among the gates. It is used for tri-state buffer, and X is the do not care or unknown value. These are the 4 basic data that we deal in Verilog. We can have different representation of them in terms of octal or hex or decimal. However, when we are dealing in the circuit level, we will deal with these 4 basic data values, or since it's a logic circuit, you can say we will deal with all these logic values. So we are done here with this particular slide. Let's move on to the next slide. Data and literals. In Verilog, we have different way of representation, use and display methods for various number system inside a single Verilog program. The value Z and capital Z stand for high impedance, and X and capital X stand for uninitialized variables or nets with conflicting drivers. So this is a perspective for the digital circuits for Z and X. Now, what are the literals? We have binary literals, and how we write? First, we write 2. That means what is the width of the data, right? Then we have a tick here, and then we have B. B means binary, and then we have 1 and 0. So 1 goes here and 0 goes here. This is the binary literal. 2 is the width here. B is the type of the data, and the content of the data is 1, 0. You can see the graphical representation here on the right hand side. Now let us see what are the other literals are there and how we write them. Octal literal. Here you can see 2 is the width, O stands for octal, and the content is 17 in octal. Next we have decimal. So decimal do not need such kind of format specifier like B or O. What type of data? You can write directly the decimal number, or in case you want to write, you can write D. D represents decimal and the content is 9, or you can write in this way. We'll talk about this separator in upcoming slides, so you will come to know. Next is the hexadecimal literal. So here the width is 3, type hexadecimal is defined by H, and the content of the variable is 189. 189 is not in decimal, it's in hexadecimal. So be careful and pay attention. This 17 is in octal, this 189 is hexadecimal, and here it is in decimal. All these type of data we can represent through the literals. Literal is a term for Verilog where we use it to represent the different number systems here, and we write them with the help of the syntax that is available inside the Verilog. We are done here with this particular slide, so let's move on to the next slide. Data types handling. Here, let me give some examples. First one is the real, then ABC. So ABC to be real. Real is a data type. You know, in case you are familiar with the C language, you might know that there are real numbers, integers, etc. We can also define the integer with the keyword integer, and then JK are the integer variable. So here, if we type real keyword here, it will mean that all these variables are real. That means some decimal format 3 or 2.3 is a real number, right? Our integer is 2 here. JK can be this type and ABC can be of this type. So integer can be of this, the array of integer variables, right? I 1 up to 32. So this is the bus representation in Verilog. However, this can be used for integers to represent the array. Reg is a type Reg, that means a register. We have already talked about this kind of registers and compared with them the nets. It is where in last episode. So here the Reg is there and array 3 down to 0 is there and it's a Reg. Again we can have integer I initialized here in the declaration itself. I equal to 0 I have written here. And we have real R2 equal to 4.5, R3 equal to 8. They are initialized at the declaration. Then the unique data type that is exclusive to Verilog as compared to its programming language counterpart like C, Perl, etc. is the time variable. So here we have the data type time and we have a time variable. Start time is 40. 40 is the value of the prefix and it has to be multiplied with the time unit, and the time unit has to be defined by backtick timescale. Next we have integer a equal to 1. It's a string number 1. Size is 32-bit. Next we have integer a equal to -1. We have the initialize. It is signed number, that is -1. Size is 32-bit in 2's complement format. These are a couple of examples of data types that you can write in Verilog. So here we have talked about integer, real, time, all these type of data type handling in Verilog. We are done with this particular slide. Let's move on to the next slide. Here time, registers and variable usage. Time, we have time declaration and we have a time variable new time, and time and integer are similar in functionality. Time is an unsigned 64-bit used for time variables, and here we end our comment. So this was a comment. If you remember the comment, multi-line comment starts with a slash, then asterisk, and then a asterisk and a slash. It ends. Next, we have range representation 8 star 15 down to 1, and it's a string. How we can deal with a string in Verilog? This way we can do it. This is a question for your interview. This defines a vector with a range. So the range is MSB of the expression down to the LSB of the this way. Let us look into some examples here. We have an initial block and begin keyword here. And then we have a equal to 0.5. It is same as 5.0 e minus 1, the real variable. Then B, we have 1.2 e12. So 1.2 into 10 to the power 12. Then we have C as 26.19 underscore 60 underscore e to the power minus 11. Dash R used for readability. We have reached to the next line. String is, we have a string example under the double quotes. This is a string. Remember, we have defined the string here. Then we have the new time, right, equal to $time. Whatever $time contains, it goes to the new time because we have defined the new time variable here. We end here the initial block. This is a kind of example how to deal with the different data types which are new to you, like the time one in Verilog, apart from whatever concept that you borrowed from your programming language. So here we are done with the example. Let's move on to the next slide. Literals and interpretation examples. Here goes our table. So here we have range 1 down to 0 A, and we have 2 tick B. These are two binary numbers. The first one is this and the second one is this. So the value is actually is this. Underscore is ignored because it is used for the readability. We have range 3 down to 0 A, that is 4 tick D1, and this is 1. D is for decimal, right? And we have range 5 down to 0 A. It has 6 is the width and octal, and that is 1, 2 is the octal content. So here it is the octal value and O is used for octal. We have range 5 down to 0B and we have 6 tick H1F, and the content is this one in hexadecimal, or rather we expressed it in binary. Here we have expressed it in hexadecimal. Here you can see all the data are represented in binary. H is for hexadecimal, and then we have 4 down to 0A, which is a range type variable, and the content is represented by the literal 5 tick BX. This has a width of 5 and the content is X, so it is 5X. X is the don't care condition. Range 4 down to 0A, 5 tick BZ. So here similarly the width is 5 and the content is filled up with all Z. Z is high impedance. And here we have port down to 0A, which is a reg type, and we have the content value is 5 tick BX01. What does it means? 5 is the width, so the entire width is 5. X occupies apart from whatever 01. So 01 is written from the right hand side, and in the left hand side the rest of the places are filled up by X. The width is defined by 5, so it is XX X, then 01. That is high impedance. So here we have given the little examples and how we interpret them. I hope this is a good page for you or a good slide for you for your understanding how we can write in different literals in Verilog. We're done here with the examples. Let's move on to the next slide. Printing and format specifiers. Here goes our table. So folks, you have came across the $monitor, $display, etc. I have used in the first couple of episodes where simulation has been directly run through the Vivado or the Icarus Verilog. Here you have come across couple of format specifier for printing. I have used in the test bench, and here I have the exhaustive list. So to print the hexadecimal numbers, right, you have to use the format specifier %h or %H. For decimal format, you have to use the %D or %D. For binary format, you have to use the %B or %B. For hierarchical name means generally net has a hierarchical name. Okay, so for that you have to use %M or %M. To display something as string, you have to use the %S or %S. You want to display the time value, you have to use the format specifier %T or %T. Display the real in a decimal format, you have to use the %F or %F. Now, to display the real in an exponential format, that is 1E, this kind of format, you have to use %E or %E. And decimal means is 1.2, and here this is 1E10. So this kind of values you can print with %E. So folks, this slide contains the exhaustive list of all the format specifier that you can use for your print statement inside the test bench, and these are good for your debug. We're done here with this particular slide. Let's move on to the next slide. Backtick timescale in simulation. This is a very important slide. Please pay attention. The backtick timescale has two components. First one is time unit, then comes a slash, and then the time precision. The unit is whatever unit has it, right? And the precision is the fractional value up to which it can count under this unit. Time unit is the unit of present time unit, the unit of present simulation time or delay insertion. So it is the unit, one single unit. And time precision, the fraction of the time which is measured with accuracy. That means how far we can go in the molar direction to measure some time. Backtick timescale is used for base unit of measurement and precision of time. Print timescale system task is used for display time and precision. In case you want to see this format, right, you have to use the print timescale. Time and real time system functions return the current time and the default reporting format that can be changed with another system task, that is time format. You have came across all these different tasks which are predefined in the Verilog library. In case you want to go to the details, please check the LRM, that is the language reference manual. And for Verilog, since now Verilog is the subset of the system Verilog, you have to look for the system Verilog LRM. Here we are done with this particular slide. Let's move on to the next slide. Backtick timescale case example. We will talk about different case examples of the backtick timescale. So here again, the timescale, the backtick timescale directive has two parts. One is the time unit, another one is the time precision. That means how far you can go downwards in the precision wise. Let us see some examples. First one, backtick timescale 1 nanosecond and 1 picosecond. So this is the unit is the 1 nanosecond. So this is a unit for your time simulation. And this is the precision or the fraction up to which it is measured. So you can see nanosecond to picosecond. It's 10 to the power minus 3 difference, right? Next, we have timescale, backtick timescale with 10 microsecond by 100 nanosecond. That means this is a time unit that should be there for the unit step for your simulation. And this is a fraction up to which accurately time should be measured. And here the backtick timescale again comes with 10 nanosecond by 1 nanosecond. So 10 nanosecond is the unit in which your simulation progresses as per the unit time, and when some difficult calculation or accurate calculation is needed, it goes down up to 1 nanosecond accuracy. That means your simulator will calculate up to 1 nanosecond. So these are couple of examples of the backtick timescale that is used in Verilog simulation. This is very important. This is asked in interviews, to get prepared, and also you can think of any tricky thing, a tricky question that can come up to your mind, and be prepared for your interview. Here we are done with the particular slide. Let's move on to the next slide. Backtick timescale code example. Here we'll go through a code and later we will see its output itself in this particular slide, not in the simulator. And there we can see how the backtick timescale impacts the calculation accuracy. So first we have the 1 nanosecond by 1 nanosecond timescale unit and the precision. Alternatively, in the second set of simulation, we are going to use 1 nanosecond by 1 picosecond. Then we have our module test bench is abbreviated as TB, and we write reg val. We write our initial block, and here we print our timescale. Initialize the signal to be 0 at time 0 unit. Val less than equal to 0 is the kind of assignment, dynamic assignment that you do, right? It's not a continuous assignment. Then we advance by 1 time unit. Displays the message and toggle the value. Here we have #1, that means we are proceeding with a 1 time unit delay, and we use the display that is equal to %e at time #1 with real time. You can see real time we are using here. Whatever time we are using, that can be printed through the real time. Next we assign 1 and advance by 0.49 time unit and toggle the value. Again, in the similar way, we are putting it here and we are putting a display command %t here and real time here. And next we change the value to 0. That means you can see 0 to 1 here and then 1 to 0 here. So we proceed with the time unit which is defined by this, and then we toggle the value. So this way our code proceeds. So the code is not finished yet. Let me show you the remaining part. We advance by 0.50 time unit and toggle the value. Here it is #0.50 and display %0t at time is 1 with the real time. And then we again toggle the value. The earlier value was 0. From there we have toggled it to 1. Again with advance by 0.51 time unit and toggle the value. So here is the #time delay and here is our display command. So here we toggle from 1 to 0. Let simulation run for another 5 time unit and then exit. So here we have #5, display this, and then we end our block, and here end our test bench model. What happens when we simulate this code with 2 different backtick timescale options, which we have shown already? Let us see in the next slide. Simulation output comparison. So what happens for backtick timescale with 1 nanosecond by 1 nanosecond? Here is the out. You can see at time #1 is 1, time t equal to 1 at time 4.49. Time 0.5 is also this, right? This. So this is kind of proceeding, right? So here you can see it is not changing here in these 2 values, and here it is also some kind of difficult to interpret how much accurately we have changed. Let me explain here. Since the precision is 1 nanosecond, the time scale can proceed with multiple of 1 nanosecond unit only. Hence, the fraction of nanosecond cannot be measured. You can see here we have proceeded to fractional, but here we can see no fraction here. Now let us see what happens with the time scale 1 nanosecond by 1 picosecond. That means we have increased our precision up to 10 to the power minus 3 here. Here comes our output. Here you can see everything in the code remains same, and here you can see this with the time scale we have printed that whatever time scale, the print time scale command, we have printed 1 nanosecond by 1 nanosecond, and here you can see with the print time scale we have 1 nanosecond by 1 picosecond. So here you can see equal to 1000 at 1, 1490 at this, 1990 at this, and 2500 at this. These keep on adding, right? Because we are adding delay, so these are getting added to the initial time, right? And that's why whatever is changed, you can see the reflections here. That t equal to 7500, we end our simulation. So here, let me summarize it. Since the precision is 1 picosecond, the time scale can proceed with multiple of 1 picosecond unit, and what the difference here versus here you can see, because only change in the test bench is this versus this. So you can see how accurately you are able to print or measure the time. Here there is no accuracy, 1 to 1, 2 to 3, so you do not know exactly how much precision it has moved forward. But here you can see 1000, 1490, 1990, 2500 and 7500. Hence, fraction of nanoseconds can be measured. This is very crucial for it. Why? Because in Verilog simulation, when you see a waveform through the VCD file or maybe your inbuilt simulator like Vivado, if you do not choose the time scale properly, you will not be able to debug in case of different changes. Say you want to measure something like pole value or setup value or difference between the two changes in two different input changes or output changes. That becomes very difficult for you. So the time scale, this time scale and its precision, the unit and its precision is very, very important. Generally, this is very good to know for your simulation and debug, and this question is asked in the interview, that whether you know the importance, significance, the usage and how they become different when you have the different unit and precision. So this is a very small example. You can write down or memorize the example and give the output so that your interviewer is satisfied with this thing. Obviously, I will ask you to try out the code, write down the test bench in either Vivado or Icarus Verilog and simulate it. So I think in the first or second episode, we have shown how to simulate using the Vivado or Icarus Verilog. I think up to this episode, you are well able to write a code and simulate. So hence I am not showing anything here. I'll suggest you to try it out at your end, write the code and see these out and do your changes and see what happens, and try to explain whatever changes you have made and accordingly whatever the difference you see in between this and this. So that will help you out to prepare for your interview. Here we are done. Hey guys, welcome back. In today's episode, we are going to discuss the below points. Introduction. Next, we will talk about function, its syntax, rules and restrictions, and then we will go through the defining process and calling of a function. Next, we will move on to task and we will go through the process of declaration of a task and its syntax. Next, we will be doing the defining and calling of a task. Also, we will learn what is a global task. Next, we will look into the different examples by which we can do a task declaration. After that, we are completed and we will move on to the comparison of task versus function, and we will talk about similarities and differences. Finally, we will list up the library functions and tasks that are ready to use with the Verilog language. So that's the menu for today. Without any further delay, let's begin. Introduction. The $sign introduces a language construct that enables development of user-defined tasks and functions. So whenever you encounter any task and function in Verilog, you will have the name preceded by a $sign. The name following the dollar is interpreted as a system task or system function. You are reading a Verilog code which is not written by you. There, if you find any phrase which start with dollar, then it is either a system task or a system function. How you will know which one is the system task and which one is the system function? For that, we have two slides at the end of this video. There you will get familiar with the system task and functions already available in Verilog. System task and function are used for simulator functionality and not for Verilog design. So this is a very important point. So whatever system task and functions are, these are not for Verilog design. These are for the simulator functionality or any kind of simulator capability enhancement. The $sign is a system function identifier or system task identifier and shall not followed by the space. So that means whatever we are writing after this dollar, there should not be a blank space here. So it should be continuous. So the name will start immediately at the next character position after dollar. This is the few things that you need to know in the beginning. We are done with this particular introductory slide. Let's move on to the next slide. Function syntax. A function definition begins with the keyword function. So the keyword is function itself that you need to write. Then it follows by an optional keyword automatic. It is an optional, so it could be there, it may not be there. Followed by an optional function range or type of the return values. So generally any function in any language has return values. So those return values will be coming after the automatic. Followed by the name of the function. So after all these things are done, finally we have the name written afterwards of that particular function which we are writing as per our own purpose. And this is not a system function, whatever we are talking about here. Even if you find in the library, they might have all these formats, but whatever we are saying here, it is for your consumption. That means you have to write a function and how you start and what sequence you have to write the function syntax. Followed either by a semicolon or by a function port list. That means after we are done with the name, immediately after comes a semicolon or by a function port list. So that means ports. We generally in Verilog we define a block, right? So that will have input ports and output ports. So all these port data will come as the port list. Function will end with the end function keyword. We started with the begin and here we have to end the function with the end function keyword. So this is the syntactical requirements that you have to fulfill. Here we are done with this particular slide. Let's move on to the next slide. Function, rules and restrictions. So here in this slide, we will talk about the restrictions or rules that you must follow while you are writing a function, that is a user-defined function in Verilog for your design purpose. A function cannot contain any time control statements like hash, @, posage, negate. You have come across all these things already in all multiple previous episodes with example, definition, etc. All these time control things should not exist inside a function. A function is a pure function. It's like any programming language function and it do not have any time component. A function cannot start or enable a task because it may consume simulation time but can call other functions. Inside a function, you can call another function. You have a function and you are calling a function, but you cannot call a task. Task is not allowed to call from a function. The fundamental difference between a task and function is the involvement of time, and hence to keep this fundamental thing intact, you cannot call a task from inside a function. A function should have at least one input. This is very important. A function cannot have non-blocking assignments or force release or assign deassign. All these are syntactical things. A non-blocking assignment you are already aware. Force and release we have not talked about, and assign and deassign we have talked in some of the episodes. So you must remember that non-blocking assignment, force release or assign deassign, these cannot exist inside a function. A function cannot have any event triggers. Event also related with the time, so it cannot have any event triggers inside the function definition. A function cannot have output or in-out. You know already the types of the ports are input, output or in-out. These cannot exist. So these two cannot exist. Output or in-out cannot exist inside a function. So here we are done with this particular slide. Let's move on to the next slide. Defining and calling of a function. First type of definition of a function. Function 7 down to 0 sum, input 7 down to 0 AB, begin, sum is equal to A plus B, next we have end, and we have the end function. So these are the syntactical ones. If you look carefully in the structure, we have the port declaration here or input variable declaration since we cannot have the ports. If we look carefully into the code, you can see here is the input declaration and here is the body of the function. So the body is enclosed with begin and end, and inside that we have the mathematical function here. So this is the first type of defining a function. Second type of defining a function. We have function, then 7 down to 0 sum, then we have input 7 down to 0 A and B. So here you can see the difference. Here we have this, here in addition we have this. So which we have written here can be written also here. Next, we have our body begin, then sum equal to A plus B, and then we have the end and we have the end function. The body remains same for the two, here this and here this, both are equal. However, the only difference is here it is written here. In these two ways, you can write a function structure. Next, calling of a function. How we call a function. So we have defined range 7 down to 0 result. Then we have range 7 down to 0 AB, and we have our initial block. We have initialized A equal to 4, equal to 5, and we are assigning the result, that means this one, with sum of A plus B after 10 time units. So here you can see we do have time involvement, but it is not inside the function. It is outside the function. So here it is called and the value is returned here in the result. And here we end our initial, and here you can see this is a test bench, and hence we are declaring the variables as range for all these things. Here we have not defined range or type because it is not needed. However, we need to hold the results here, so we are writing range here. So here we are done with the defining and calling of a function. Let's move on to the next slide. Task. A task can contain time controlling statements. This is the beauty of task, that it can have time involvement inside its code. A task can enable other tasks and functions. Earlier, functions were not allowed to call any task, remember. But the task has a capability to call both task and function. A task can have 0 or more arguments of any type. A task shall not return a value. So if you look into the name, right, it is task. That means it has to do something, and that's all. That's the purpose. So why should it return a value when a function is already returning a value? That's why by the definition, the task do not return a value. It just executes a task and finishes its operation. A task can support multiple goals and can calculate multiple result values. Because this is a task, it has to finish the task, and if we break down the bigger task into smaller steps, so all the steps have to be executed, and hence it can calculate multiple result values because these are the baby step of a large step. A task shall be enabled from a statement that defines the argument values to be passed to the task and variables that receive the results. A task shall be enabled from a statement that defines argument values to be passed to the task and variables that receive the results. Control shall be passed back to enable process after the task has completed. Thus, if a task has timing control inside it, then time enabling a task can be different from a time at which the control is returned. So that means by all these points, right, all these points we have discussed, this is a task, right, and we do something here at say time equal to t1, and it takes some definite time to finish, and then the control returns back here, and this is not t1, so this will be t2. So this is a kind of philosophical explanation that the point at the time when the task begins and when the task returns to its own code, those two times may not be the same one. A task can enable other tasks, which in return can enable still other tasks with no limit of number of tasks enabled. So one task calls another task, that task again call another task. So this way hierarchy can go. So this task can again call another task. So this way the hierarchy can go, and it can have multiple branches like this we are talking about. It can have multiple branches like this. So one task is calling another task, it calling another task. So this way hierarchically the tasks are calling each other in the down the hierarchy. That is okay, and that is possible in the task definition or allowed in the task definition. Regardless how many tasks have been enabled, control shall not return until the enabled tasks have completed. When the task do something, right, until or unless this is done, right, the control do not goes back. So that means it has to finish the task here defined, not the task here by syntax. The things, the to-do list that has to be completed here, and then only the control will go back. So here we have thoroughly understood what is task. So here we are done with this particular slide. Let's move on to the next slide. Task declaration and syntax. There are two alternate task declaration syntax. The first type of syntax shall begin with the keyword task, followed by the optional keyword automatic, followed by the task name and a semicolon, and ending with the keyword end task. The keyword automatic declares an automatic task. Task item declarations can specify the following: input, output or in-out arguments. You can see the difference. Here is the difference from the function. If you have noticed already, in case you have not noticed, rewind the video and watch the functions. There is one clue that this point is different from the functions. All data types that can be declared in a procedural block. The second type of syntax shall begin with the keyword task, followed by the name for the task and a parenthesis enclose the task port list. That means the port list should be there. The port list may consist of 0 or more comma separated ports. There shall be a semicolon after the close parenthesis. the task body will follow, and then the keyword in task comes into the picture. All these things will be clear once we go through the example. Defining and calling of a task. First type of defining a task. Task, we have sum, then we have input AB, output C. You can see both input and output ports are there. Then we have the begin, we have the C equal to A plus B, and we have the end keyword, and we have the end task. So here is the body of the task which the to-do list have to be performed, and here we have our port list. The first type of defining a task. Now let's move on to the second type of defining a task. Task sum, input 7 down to 0, AB, we have output 7 down to 0, C, and we have begin, then we have C equal to A plus B, end keyword that closes the begin, and we have end task. Here, if you look and compare into the two codes, this one is the common part and which is same. So this is the body of the task, and the difference lies here. This syntax and this syntax both are equally okay. So the difference lies here only, and the rest of the part of the task is same. So in this two way, you can write a task. Calling of a task. Initial, begin, we have, and we have reg 7 down to 0 xyz, and then we have xyz. So this way we are calling a task, and here our initial block ends. This calling has to be there in the initial block, and this way the task is called, and then the control goes to whatever you have defined. So if you have defined this, it will go to the body, execute and come back, or in case you have in the second way, it will go to here and come back. This way you can define a task and call the user defined task inside a Verilog code. We are done here with the particular slide. Let's move on to the next slide. Global tasks. Global task is a task outside all of the modules. Task, we have a display task, and we use the $display, which is our system defined, and here we put hello world, and we here end with the end task. Now how this becomes global, you will come to know by the rest of the code to be shown here. We are showing an example here. Then we have module des, then we have initial begin, and then we have display called inside this module, and we have the end, and we have the end module. So the module des is calling the display task, which goes to here, execute the print statement and comes back here. This one is a global task because it is defined outside this module, and if there are further modules defined, then all those modules can call the task. This is a global task. But in case this was defined inside this one, right, in this module, it cannot be a global task, and then this is not allowed to call the task, or this is not allowed to call that task. So they have to have their own task inside, or have a global task like this, call it. This way you can make a task global and use the code reuse method to repeatedly call a task, which is a global task. Types of task declaration. We'll see one example here. Task, my task, it is just a name. Then we have input AB, we have inout C, we have output DE, we just begin the body, and the statements that perform the work of the task will be written here by you. And here we have few just dummy examples. C equal to 4.1, equal to 4.2, and equal to 4.3. So the assignments initialize the result sets, and we end our body of the task here, and we end the task itself here. This is one type of the task that you can write. This is one type of example, and we are done. It's just an example. Now let's move on to the next slide. So to see another type of task declaration. Now here you have my task. Again the same. We have input, inout and output here, and we have the begin, the body, and here goes the statement that perform the work of the task. And here you define all the statements that initialize the results. And here we end our body of the task, and here we end our task. So you can see that the difference of this type of example is only here. We're done here with this example and comparison. Let's move on to the slide. Task with test bench. So here we will use a test bench, and this code you can run in the simulator, Icarus, Verilog or Vivado, and also will display the result here itself in this slide. So let's begin. We have module, test bench for task, and we have reg 1 down to 0 bus. We have task write bus, input reg 1 down to 0 bits. We begin our task with the begin keyword, and here are the statements and we end our body of the task with the end keyword, and here you can see only one statement is inside, and we end our task. So we are done with the defining of the task here. Let's use it. Initial begin, and then we use the $downfile task1.vcd and $down. So these are for your value dumps inside the VCD file. I have explained earlier in, I think, first or second episode or third episode, where I have done the thorough simulation through Icarus, Verilog and Vivado. There I have shown you that how the VCD file is there and how we can open it to the waveform viewer, GTK-Wave, or we use the inbuilt waveform viewer in Vivado. Next, we use the write bus is the task here in tclatter. Next comes our write bus, and you can see here the values are changing. The bus values, whichever we are writing as an argument, changing. And at this we finish. And here we end our body of the task. And here we are done with the test module. So basically here we use a delay to write down the bits. So we insert a 5 time unit delay, and then we insert the bits which we receive through our argument. That is the purpose of the write bus function. And here what we have done, we have added delay manually, and after that we have inserted the different bits as argument. Or as you go ahead and simulate it in any of the simulator, Vivado or Icarus Verilog, will get a waveform like this. So that is a task for you. Please complete it. It's not a very big code. You can write it down by just pausing the video and typing it. Here we are done with this particular slide. So let's move on to the next slide. Task versus function, similarities and differences. Task and functions permit grouping of common procedures and then executing these procedures from different places. Arguments are passed in form of in-out or input values, and all calls to the function and task their variables. So these are the similarities of the task and function. Now let us look into some differences. In left hand side we have task, right hand side we have functions. So the task permit time control and the function executing in one single simulation time unit. So that means it is time independent, and this one is time dependent, and this one is time independent. Can have zero or more arguments. I think here is a typo. And the function require at least one input. Does not return a value, which is very important, and assigns the values to output. So it goes and does a to-do list and it comes back to the time control. In comparison, the function returns a single value. No special output declaration is required. It can have output arguments that permits #, the arrow, wait, task calls. There is again typo. Does not include permit outputs. That is, all of these things cannot be there. So here is the similarities of the task and function. Here is the dissimilarities of the task and function. So we have done the comparison of task and function from all of the points. So here we are done with the particular slide, and let's move on to the next slide. Here we come to our library functions, which are also called system functions, and we'll just review the definitions, and here we will just review the names, because for detailed description and all you can consult the LRM, as because the Verilog is now a subset of the system Verilog, you can go ahead and the system Verilog LRM you can have all the definitions, but at least you have some list inside your mind while completing this tutorial. You have the function names in your mind, which are available as a part of the library and called system functions. Simulation time functions, what are there? Here we have real time, time and S-time. Conversion functions. We have signed, unsigned, bit to real, I to R, real to bits, R to I. This is real to integer, and this is integer to real, and this is bits to real, and it is real to bits. So these two are paired and these two are paired. So these are opposite and these are opposite. You have signed and unsigned. These are also paired. These are conversion functions. We do have mathematical functions such as log to ln, log, exponential, square root, power, floor, ceiling, etc. And also we have trigonometrical ones as sine, cos, tan, all those things. I think sine is hyperbolic ones, and also the inverse of that. We do have all these sort of mathematical and time related functions available in the library. For all the definitions, please consult the language reference manual, that is LRM for system Verilog, as Verilog is officially the subset of system Verilog now. Here we are done with this particular slide. We will move on to the next slide. Library or system task. Display task. display, display V, display H, display O, probe B, etc. All these display related tasks are available there. And we have write B, monitor and all the monitor variants, monitor on, okay, all these things are there. We have file IO tasks. So these were display tasks, that means printing like tasks. So file input output, that means you are writing your file to your hard disk, all those things, and reading from the hard disk, all those things are there. There we have F closed, F display, this is F display B binary, hexadecimal, the octal, okay, this is strobe, this is again binary, hexadecimal and octal. So all these things are there. Also we have SWrite, SWrite B, SWrite H and O. So this is binary, hexadecimal and octal. And we also have C-like functions with the names are similar here. You can have fscanf, fread, fseek, fflash, feof, SDF annotate. So this one is different. SDF you can annotate here. Next we move on to the time scale task. We have print time scale and time format. Simulation control task. We have finish or stop. The finish you have seen already. We have used in multiple examples, and now you are all aware of the task. Those are available in the Verilog library. For the detailed description, I will suggest you to visit the LRM, that is the language reference manual. Download it as a PDF and keep it with you, and you go and into the details of each in the LRM. And as the Verilog is officially the subset of the system Verilog, so you will have to download the system Verilog LRM, the language reference manual. And one more thing I have to tell you, that please try to consult the latest LRM, because all the latest developments you will find there. Otherwise, if you are using maybe 2-3 years back, or maybe 5 years old, or maybe 10 years old LRM, then you might miss something. Many definitions or bug fixes, they may not be there. So always try to catch the latest LRM and go through it. Here we are done. Hey guys, welcome back. In today's episode, we are going to discuss the below points. Introduction. First, we will introduce you to the various parameters and give an overview on them in Verilog. Next, we will classify the different parameters in Verilog. Next, we will go in detail for the module parameters. Next, we will go for the parameter, Defparam and Localparam to thorough example. Next, we will talk about another parameter, that is specify parameters, and we will follow it up with the example of it. Next, we will compare specify versus module parameters, and hence we will conclude the episode. So that's the menu for today. Without any further delay, let's begin. Introduction. Verilog HDL parameters do not belong to either variable or net group. You know, right? There are integer, real, this kind of variables are there, and also net and wheres and range, all these things are there. We have already discussed them in previous episodes in this series. In case you have not watched, please go ahead and watch them. Next, parameters are not variables. Rather, they are considered as constants. So this is a very important concept about the constants. Parameters are constant. Why? Because in the beginning we assign them with a value, and at some point that value is used. So hence the parameters contain constants, and variables are such thing. Those are used for continuous calculation. Their values may change with different block of code or maybe with the timing operation. So hence the parameters are constant and not variable. Every Verilog parameter accepts a range specification. So we do have a range specification. That means we have a parameter that can begin from a range and end from a range, and in between there could be multiple values. So this range specification is there with the parameters from the birth. Verilog have two types of parameters. These are major classification module parameters and specify parameters. We will go in detail in the subsequent slides. A parameter cannot be redeclared as a net or as a variable. So you cannot use it as a net or use it as a variable. This is not possible. A parameter, once it is declared as a parameter, that means you are declaring a text, right, as a parameter, and that text string cannot be redeclared as net or variable. So you have to take the use of the parameter with this particular string. We are done with this particular slide, so let's move on to the next slide. Types of parameters in Verilog. In this slide, we will classify the different parameters and we will go in further detail, and we will also sub-classify them. So here are our parameters. The parameters in Verilog can be divided into two broad categories: module parameters and specify parameters. Now, module parameters can also be subdivided into two categories. First one is the Localparam and another one is the Defparam. Whereas the specify parameter has only one particular division or subdivision. It is called Specparam. In Verilog, we have at the end, that means the leaf level, we have the Localparam, Defparam and Specparam. We will go through the example of all of this, so don't worry. Here we are done with the classification and let's move on to the next slide. Module parameters. Parameters represent constant and hence it's illegal to modify their value at the runtime. However, module parameters can be modified at the compilation time to have values that are different from those specified declaration assignment. Since the parameters are constant, you know, right? So they cannot be modified anywhere in the code. This is as per the definition. However, for module parameters, when we are instantiating a module, we can access the module parameters which exist in the definition of that module, and at that time we can modify it. For different instantiation, we might have different values of the parameter, and this has to be done prior to the compilation of the. A parameter can be modified with Defparam statements or in the module instance statement. We will see the example, so don't worry. This allows customization of the module instances. And typical use of parameters are there to specify delays and width of variables. Generally in Verilog, parameters are used to specify delay or some variable. Some variable doesn't mean that you are using a Verilog variable. Some variable means which is typically constant but can vary from one instance to another. Here we are done with this particular slide. Let's move on to the next slide. Parameter example. Now we have talked about the definitions and we have seen the classification. Let's start our example so that you can better understand the parameters. First example is that we are using parameter keyword. So this you have to use when you are declaring a parameter, and this is the text string which you are reserving for parameter, and this you cannot use in any other variables, which is the strictness for the parameter thing, and you are assigning a constant value 7 to it. So the constant value. Similar fashion, we can have parameter E equal to 25 and F equal to 9. This defines two constant numbers. So if you have a comma separated definition, you can declare multiple parameters in one single line. Here you can see we are defining parameter R equal to 5.7. R is for real, right? R declares a real parameter 5.7. So the parameter values can be of different type. However, this should be constant and these values cannot be changed during the operation. That is the timing operation inside the Verilog. Next parameter, we have byte size. 8 byte mask equal to byte size minus 1. So we can have the mathematics with the already defined parameters. So here we are defining byte size equal to 8, and later we are defining another parameter which is byte mask, which is byte size minus 1. So this mathematics also is allowed because this is constant. This will be calculated during the compilation time. So here if you change this value, the next parameter will be impacted. Parameter average delay R plus F by 2. So I said the mathematical operations can be there. Here we have defined R and here we have defined F. We are doing a mathematics with R plus F by 2. So this will give the average delay. So here you can see parameter sign 3 down to 0, marks left to 0. So this is a bus type parameter. And here you can see we have signed value. So parameter can be signed or unsigned. Parameter real R1. We have 3.5 e to the power 17. That means we can have real parameter with exponential form. So these are constant merely. This is a constant, right? That goes to R1. And here we declare the type. That means real. We can have a type declaration of the parameter in this way. Here we have defined signed. Here we have defined real. And we have assigned the value. So here we are writing parameter P1 13-H7E. So this is another way of writing the parameter. Here you can see parameter 31 down to 0, yet constant is 1 tick B1. The value converted to 32 bits. So H is for hex, is a hexadecimal. B is for binary. This is a hexadecimal constant. This is a binary constant. Because in Verilog we don't only have the integer, real and etc. We do have the hexadecimal, octal and binary. So here we have the new constant 3 tick H4. So this is a hexadecimal constant, right? For the H implied for the range 2 down to 0. And here we have the new constant equal to 4 implied for at least 3 down to 0. However, the names are here same. Please try to mention two different parameters with two different names. Here is just a mere example and we have tried to explain. So in case you have some other different parameters, don't name two parameters with the same name. Rather have a different name. Here we are done with our initial example of the basic parameters in Verilog. Let's move on to the next slide. Defparam example. So here we will see the example of the Defparam. We have a module is named as secret number. Then we have parameter, then secret equal to 0. Next we have initial block that starts with begin, and we have $display here. Here my secret is this, and we end it, and here we end the module. So this is the purpose. The module has a specific module parameter. That means this is very much tied to this module. So this is very much tied to this module, and we'll see the example how we can change the module parameter to the Defparam syntax. Here we have the module. This is a test bench. Here Defparam example, we have given the name. We have Defparam, then u0.mySecret is equal to 11. u0 is the instance name, and that instance name contains the mySecret. So e1.mySecret is the internal parameter, that is mySecret. This parameter is accessed through this syntax, and we are injecting value 11 into this parameter for that u0 instance. Let me give another example here. u1.mySecret, we are injecting value 22. So this will replace the original definition 0, which is in the module definition. When we have different instances, we have corresponding values for the module parameters, and we change them with the Defparam syntax. Next, we have the instances secret number u0, and we have secret number u1. So you can see here that u0 is the instance of secret number, that is this module, and u1 is in the similar fashion. And this way, with the Defparam definition, and this way the Defparam usage, we access and change this particular variable which is defined with some initial value inside the module. And here we end our test module. Here we are done with the Defparam example, and you have seen how we can access a module parameter from outside using the Defparam. So here we are done. Let's move on to the next slide. Localparam example. First, we'll give 2 points on Localparam, and then we'll proceed for the Localparam example. Verilog HDL local parameters are identical to the parameters, except they cannot directly be modified with the Defparam statements or module instance parameter value assignment. You can see this module parameter, Localparam, cannot be changed with the Defparam. Local parameters can be assigned constant expression containing parameters. So this cannot be handled like a Defparam. Now let us start the example. Module, then we have the module name, RAM model. We have different ports, right? Address, write, chip select, data, all this. And we have parameter data weight is equal to 1. Parameter RAM dev 256. And we have local param. You can see we are using another keyword, local param, to define a local param. So ADDR width, that is the address width. And we have this one, the function here. Then we have the input, then ADDR width down to ADDR width minus 1 down to 0, and address. So this is, we are going for the input and output. So we are defining them, and here it is in out, and then we define the function which we have used here. So you can see we have local param, and we use a different keyword local param for that particular usage, and this cannot be modified like the Defparam, which the example you have just seen in the previous slide. And here we have the function definition, and here goes the function body, and we end function, and we use it like this. These are the equations of the module, right? And rest of the RAM model goes here. So we are not in an explicit mode of defining, rather we are giving the idea how the local param can be used. So if it is declared with the parameter, right, this can be changed with the Defparam, right? But if it is declared with the local param, right, it cannot be neither accessed nor changed with the Defparam statement. So that is the difference between the Defparam and local param. So here we are done with the utilization and example and definition of the local param. So let's move on to the next slide. Specify parameters. Here we will talk about specify parameters. The keyword Specparam declares a special type of parameters that is intended for providing timing and delay values. So this is intended for timing and delay values. So this is a kind of special parameter. It can appear in any expression that is not assigned to a parameter, and it is not part of the range specification of the declaration. So these are few points you have to get clarified in your mind apart from the basic parameter definition. So from the basic parameter definition, how the specify parameters are different, we are going through those points. Specify parameters are permitted both within the specify block and in the main module body. So the extent of the specify parameters are both within the specify block and in the main module. A specify parameter declared outside the specify block shall be declared before it is referenced. So you have to declare and then you have to use. This is the funda. The value assigned to a specify parameter can only be a constant expression. This is very strict. Parameters are always constant. A specify parameter can be used for a part of constant expression for subsequent specify parameter declaration. So they can be used in a expression. That means we have seen already such expression for other parameters. Those are also true for the specify parameters. Unlike a module parameter, a specify parameter cannot be modified from within the language, but it can be modified through the SDF annotation. So this is another very important part. Like we have used the Defparam, we have modified during the instance declaration, all these things. This cannot be done within the Verilog language. That means when you are writing the Verilog language, there you cannot modify the already defined specify parameter. However, where it can be accessed and changed from the SDF file, standard delay format. If those things, the delays and other timing things are declared through the SDF file, the tool will change them in the actual compilation time. So these are SDF specific parameters which can be accessed through the SDF file. Specify parameters and module parameters are not interchangeable. Specify parameters have a specific usage and module parameters are different. These are not interchangeable. You cannot exchange them, or during the use we cannot use one in place of another. Here we are done with the definition. Let's go to the example in the next slide. Specparam example. We have a module and we have the ports here. And we have input, output, where all these things we are defined for all these ports, right? Now specify block containing delay statement. This is going to start specify, and then we have the Specparam DL1 equal to 6 and DL2 is equal to 7. We can define multiple Specparam using a comma separated format. Next, we have the condition here for DL1, the delay from A to Q. Then we have B to Q is DL2, delay from B to Q. Here we have C to Q, DL2 delay from C to Q, and D to Q is DL1 delay from D to Q. So you can see we have a module where we have the input A, B, C, D and we have the output Q. There are different delays we are defining from the input ports, 4 input ports to a single output port. And there we are using the DL1 and DL2. And here you can see these are specified here using the Specparam. So these are timing values. Now you have a SDF file. There you can have a different values for the DL1 and DL2 which will override all these values that we are defining here. Next, we end the specify block. The specify block has to be started with specify and end specify will terminate the specify block. And there you have to use the timing and delay values for the Specparam, right? All these things. And all the specify parameter values can be overridden with the SDF file where the values of this specific Specparam values are different as per the delay and timing requirements. Next, we have the module definition. We have the OR instance here, and we have the OR instance, second OR instance here, and we have the XOR instance here, and we end the module. So you can see here we have different logic gates interconnected from input to the output, where we have defined the different delays through the specify block and through the specify parameters. Now these are not hard coded, so once you have these things here it goes with the module, but however during the actual usage or in the instantiation through the SDF file you can modify these parameters and hence the delays from input to the output of this particular module. This is the usage of the Specparam in a very simple fashion I have explained here. Let's move on to the next slide. Specify versus module parameters. Now we have walked along a long path for the different definitions and examples of the specify and the module parameters. Let us side by side compare the specify versus module parameter. This is very important for your interview. So in the left hand side we have specify parameters and the right hand side we have the module parameters. This type of parameters are declared by the Specparam keyword. This is a reserved keyword, and here you can see the module parameters are declared by the parameter. Can be declared inside the specify block or within the main module. Can only be declared within the main module. So the specify log cannot contain a regular parameter, but the specify parameter can go into the main module where the actual parameters or the basic primitive parameters are defined. May be assigned Specparams and parameters. Okay, may not be assigned for Specparam. This syntax can be applicable for the Specparams and parameters, but the reverse is not true. SDF can be used to override the values. The specify parameter can only be overridden. That means the constant values can be overridden to the SDF file only, and we have no other means to override them. Whereas the instance declaration parameter values and the Defparam can be used to override the regular parameters, which are called the module parameters. And one thing here I have to verbally mention that the local params cannot be modified apart from where it is defined. So here we are done with the comparison of the specify versus module parameters. Hey guys, welcome back. In today's episode, we are going to discuss the below points. Introduction. Here we will discuss the background of today's topic. Next, we will classify the types of Verilog syntax which can be used for synthesis. Next, we will go in detail for the fully supported Verilog constructs. Next, we will explicitly discuss about partially supported Verilog constructs. Now, this fully supported or partially supported is completely related with the synthesis. That means whatever code you are writing in Verilog that can be converted into a chip. Next, we talk about ignored construct. That means the constructs that are ignored by any Verilog simulator. Next, we will explicitly discuss about the unsupported constructs. So, you must have a clear idea which are ignored. Ignored means even if you write, your simulator will not do something. Rather, ignored constructs means that when you use these constructs, the synthesis tool will ignore them. However, if you write any one of the unsupported constructs, what will happen? The synthesis tool will reject your code for synthesis. So that's the menu for today in a nutshell, and we are done here. So let's move on to the next slide. Introduction. Synthesis tool have difficulty to find hardware with exact delays. So this is a inborn problem of the synthesis tools, and hence all absolute and relative time declarations are ignored. So whatever values you are giving manually, those will be ignored. All signals are assumed to be maximum strength, so signal strength 7. So this is a particular level. When you use a synthesis tool from a manual, you will come across all these strengths. Boolean operations X and Z are not permitted. So this is a very good thing you must know, that although in a test bench you can use the X and Z, however in synthesis you cannot use X and Z. Many simulable Verilog syntax used in test bench may not be synthesizable at all. So this is a very important point. Must remember, whatever you are writing in the test bench, that may not all be simulable in a synthesize or a synthesis tool. The test bench code is well simulable. It gives output, it gives a text output as well as the graphics, but may not be acceptable by the tool. This you have to remember, and hence we are making this episode for you so that you are well aware what to use and what not to use for your actual chip design. However, for testing, many syntax you can follow and many corners you can go. Hence, your knowledge must be crystal clear between learning Verilog and using Verilog in VLSI flow. You might question that why we are coming across this particular episode after so many episodes. The reason is that primarily the series is intended for the learning of the Verilog. However, when your learning is done and you enter into the VLSI industry, what you will do? You will use the Verilog in the VLSI flow. That time, you will get stuck, because if all these precautions measures that are going to be discussed in today's episode are not disclosed to you, you will get stuck here. So hence this episode is kind of a bridge between your learning and your actual work in the VLSI industry for the RTL coding. We are done here with this particular episode. Let's move on to the next slide. Types of Verilog syntax for synthesis. Let us make a classification here. First, here goes our total set of Verilog syntax. Now, this can be subdivided into 4 subsets. First one is fully supported construct. The next one is partially supported constructs. The third one is ignored constructs. And the fourth one is unsupported constructs. So when you are learning the Verilog, all those 4 types or 4 set of constructs you must know and use. However, when you are coding for the VLSI chip, you must be well aware of the last 2, that is ignored constructs and unsupported constructs. And you must know the conditions of the partially supported constructs so that your RTL code or the test bench is standing good for the VLSI chip design industry. And one most important thing that I need to say here is that when you are going to appear in an interview for a VLSI company or any of the front-end design part, some obvious interview questions will come that you can face if you complete this episode. We are done with this particular slide. Let's move on to the next slide. Now here in this slide, we will give the explicit description about the 4 categories or 4 subsets that we have just shown you in the previous slide. The Verilog constructs are classified as fully supported constructs. These are the constructs that are supported as defined in the Verilog Language Reference Manual. So, the LRM is the main document that you should consult for all these subsections and their details. Partially supported construct that are supported with restrictions on them is very important. So they are supported for synthesis, but we do have some restrictions applied on each of them, and the conditions are different for each of the particular construct. Next, ignored constructs. Constructs that are ignored by the synthesis tool. That means even if you write all these constructs in your Verilog RTL code, they will be ignored by the synthesis tool. Next, the unsupported constructs. Construct which if used may cause the synthesis tool not to accept the Verilog input code or may cause the different results between synthesis and simulation. So you must be very careful about the unsupported constructs, and at max you should avoid them. When there is no other way out, only in that case for a test bench or something, you can use them, but it be a good practice or a be good convention that you avoid all these unsupported constructs. And remember one thing, you must consult a up-to-date LRM for all of these syntaxes and their inclusion or exclusion for synthesis part. We are done here, so let's move on to the next slide. Fully supported Verilog construct. Here we are going in the explicit detail. The first one is the module instantiation with named and positional notations. Next one is the integer data types with all bases. So you know that there are different bases like decimal, binary, hexadecimal, octal, so including all the bases. We have the identifiers in particular list. We have more like subranges and slices on the right hand side of an assignment. Continuous assignments. We have all these symbols and operations. That means all these symbols and corresponding operations. We do have all these keywords like assign, procedural and declarative, begin, end, case, CaseX, CaseZ, end case, default, disable, function, in function, task, end task. Also we have if, else, else if, input, output, in, out, where, want, or try. Also in this list we have integer, reg, macro module, module, parameter, supply 0, supply 1. So this is the exhaustive list of the fully supported construct. That means if you use any of these Verilog constructs in either your test bench or in your chip level Verilog code, there is no issues either with the simulation tool or the synthesis. So here we are done. Let's move on to the next slide. Partially supported construct. First, here we have the char, flash and modulus operation. Now, what is the restriction here? When both operand constants or power of 2, only in that case it is supported for synthesis. That means when both operands, that means we have a char, right? At left hand side there will be something and right hand side there will be something. Similarly for the division or the modulo division. So in that case when we have the both operands, they should be constants or power of 2. In that case it will be supported by the synthesis. Next is always operation. Only the edge triggered events are supported for synthesis. So here this is our just to map the left hand side to the right hand side. This is our mapping notation and it is not a Verilog code syntax. Next one is for bound by static variables and only use of plus or minus for the index, that means the incrementation count. Next we have posage and negage, and they are allowed only with the always at the rate. So here we talked about always and talked about the triggered events. Now you can see these two are coupling to each other. Next we have primitive, end primitive. I think there is a typo here. There should be a E here. Table, end table. So combinational and age sensitive user defined primitives are often supported. For this you have to remember. Next, this particular symbol. What is this? It's an assignment operation. Limitation on the usage with blocking assignment. You must be careful about this. Next, AND, NAND, OR, NOR, XOR, XNOR, BUF, NOT, BUF F0, BUF 1, NOT 0, NOT 1. All these gate types are supported without X or Z construct. That means you cannot use X or Z in their input-output logic. So without them, they are supported for synthesis. Next, these all operators, you can see there is a huge list of operators are supported without X or Z count. Again, for these operators, on the operand side or the output side, you cannot have X or Z operations. Here we are done with this slide. Let's move on to the next slide. Ignored constructs. So here you will go in an explicit description of the construct. Those are completely ignored. That means even if you use, they will be ignored by the synthesis tool. First one is intra-assignment timing controls. Next one is delay specification. So this is intra-assignment timing control is the kind of hash statement and then the delay value, right, coming here. And delay specification, here we specify like this only. Pillared, vectored, small, large, medium. All these constructs are ignored. You also have specify in this list. We talked about the specify block in couple of episodes back, and we have time. Some tools treat these as integers. That means some synthesis tool treat this as integers. Next, we have week 1, week 0, IZ0 and IZ1, full 0 and full 1. So someone may pronounce them as IZ0 and IZ1. So either of the pronunciation are correct. Next, we have the $keyword. Some tool use these to set the synthesis constraints to this kind of keywords. Next, we have the wait statement. Some tools support wait with a bounded condition. That means it should be a boundary condition. Here is the exhaustive list for the ignored constructs for the synthesis tool. We are done here. Let's move on to the next slide. Finally, here in this slide, we will talk about the unsupported construct. That means the synthesis tool will throw away all these constructs if used in your coding. First is the assignment with variable used as bit select on the LHS of an assignment. Next one is the global variables. Next one are these two operators. We have already discussed about these two operators. Next one is the constructs which are completely unsupported are CMOS, NMOS, RCMOS, RNMOS, PMOS and RPMOS. These are completely unsupported. Deassign is also unsupported. Now, deassigning means that you are assigning some variable and then deassigning the value. This is okay for your code, but not for the synthesis tool. It is okay with the simulator tool, but not okay with the synthesis tool. The next one is Defparam. Next one is event, force, fork, and join. All those are also not supported for synthesis. Next, we have the forever, the while, and initial. So you know, right? The forever and the while are the infinite loop. That means these cannot be there in a real system. And the initial block is also for initializing the circuit condition. In actual case, when your circuit is there in chip, right? The initial conditions are determined during the power up or power down sequence. So that determines, and hence the initial block or the initial conditions you are writing for your simulation have absolutely no value in actual case, because the initial conditions will be determined by the power up or power down sequence, generally the power up sequence, not the power down one. Next one is the pull up or pull down construct. Next one is the release and repeat. Next we have rtran, tran if 0, tran if 1, rtran if 0, rtran if 1. So all these constructs are unsupported. We are talking about the unsupported one in this particular slide. we have table, end table, primitive, and primitive. So these are unsupported construct. So here we have discussed the exhaustive list of the unsupported construct, and here we are done. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will introduce the concept of SDF versus Verilog mapping to you. Next, we will talk about what is the SDF Back-Annotation. Next, we will directly jump to the mapping of SDF construct versus Verilog constructs for delay components. Next, we will exemplify whatever we are mapping here. Next, we will go further deep and do the mapping from SDF to the Verilog for the timing check constructs. Next, we will exemplify whatever mapping we have done here. Next, we will go in vivid detail of SDF versus Specparams correlation in Verilog to an example. Next, we will talk about the situation when we have multiple SDF file. What will happen to all the mapping that we are doing here? So if whatever we have talked in this section is dealing with a single SDF file. Now, if in picture or in real design there are multiple SDF files, then what we will do or what the tool will follow and what will be the end result. So we will talk on that. So that's the menu for today. Without any further delay, let's begin. Introduction. SDF files contain timing values or specify path delays, Specparam values, timing check, and interconnect delays. So all these things are there in the SDF file. For your information, we already have a full episode on SDF file, how it is constructed, what are the internal parts and different syntaxes we have thoroughly discussed, and the link of that particular episode is provided in the description of this video. Please go ahead and watch it in case you have zero knowledge on SDF file. Verilog back-annotation is the process by which the timing values from SDF file update specify path delays, Specparam values, timing constraint values, and interconnect delays. What is a back-annotation? Back-annotation generally is a process where we have a netlist, and in netlist we add some values to different nodes or different parts, whatever is applicable as per the tool through which we are simulating. So this is sometimes called Verilog back-annotation, and since the back-annotation is done through the SDF, we sometimes call it the SDF back-annotation. Rather, if we call it as SDF and Verilog back-annotation, then that will be much more proper. The term SDF annotator refers to any tool capable of back-annotating SDF data into a Verilog simulator. So this is an annotator tool. Not all tools are capable. Generally, some tools are there which can do it, and the part of the tool or the part of the source code of that tool that does it is called the annotator. That means it can annotate SDF values into the Verilog values, provided it is into the exhaustive list of the mapping, not outside the mapping. Mapping we will discuss in further slides, so wait for that. SDF files may also contain other information which is completely irrelevant to the Verilog simulation. So all this data will not be picked up in this mapping, or we will not talk about them here. So that's why I have told you we have a full episode on SDF. Link is in the description. Go ahead and watch so that you will have a clear idea on SDF syntaxes and details. All constructs unrelated to Verilog timing shall be ignored without any warnings. So this is very straightforward, because which are unrelated and which are irrelevant should be skipped without any warning, without any message. Otherwise, the end user will get confused. That means you who is doing the SDF Verilog back-annotation will get confused. The timing values in SDF usually come from application-specific integrated circuit, that is ASIC delay calculation tools that take advantage of connectivity, technology, and layout geometry information. The general information, easy to understand. You're moving to the next point. Any Verilog timing value for which the SDF file does not provide a value shall not be modified during the back-annotation process, and its pre-annotation value should be unchanged. So we have a mapping table, and there will be a subset of values in actual simulation. They will get back-annotated. Anything not that list in the back-annotation list should remain unchanged. Otherwise, it will create disruption. So this should be there in the annotator tool, and this method should be followed there. And as a designer, you should verify that there is nothing changed which is not intended to change. Here we are done with the introduction. Let's move on to the next. SDF back-annotation. So here we will go in detail of the back-annotation process. So let's start. SDF timing values appear within a cell declaration. So this is a syntax inside the SDF file. So those who have not watched the SDF episode, I am again emphasizing, please go ahead and watch the episode on SDF file. Link you can find in the video description of this video. This section may contain more than one delay, time check and label. So these are syntaxes that are contained within the SDF file. The delay section contains propagation delay values for specified path and interconnect delays. So these are delay which you can find and which you can back annotate. The timing check section contains timing check constraint values. The label section contains new values for Specparams. So from all this section, you have the SDF values. Those values will get back annotated. That means inserted into the Verilog file by the annotator tool, not your Verilog simulator tool. One thing to mention here, your Verilog simulator tool can be an annotator tool if it has the code to annotate. Back annotation into Verilog is done by matching SDF constructs into the corresponding Verilog declarations. So there should be a mapping and there should be a proper matching. Otherwise, thing will jumble up and the code will go for. Then the existing Verilog timing values are replaced by respective values from the SDF file. When annotating delay constructs, the SDF annotator looks for specified paths where the names and conditions match. When annotating timing check constructs, the SDF annotator tool looks for the timing checks of the same type where the names and condition match. So these are the routines that go in the annotation process where it checks, matches and maps and then picks up from the mapped values and back annotate into the Verilog file in the respective variables or respective regions of the Verilog code. Here we are done with the back annotation concept. Let's move on to the next slide. SDF to Verilog mapping for delay components. So here we'll give a table and directly talk about the mapping. So here is our table. In left hand side we have SDF construct. In right hand side we have Verilog annotation zone or construct. So it could be a zone where the values will annotated or directly a Verilog construct. So again, before proceeding, I'm again mentioning, please go ahead and watch the SDF video. The link is provided in the video description of this video. That will help you to understand the SDF construct like this and you will get the meaning. So here we have path pulse and where it will get annotated conditional and non-conditional specified path pulse limit. Again, there is a percentage version of the path pulse, that is path pulse percent, that will get annotated in the conditional and non-conditional specified path pulse limits. There is a construct called IO path. It will get annotated in the conditional and non-conditional specified path delay and pulse limits. So here this is delay and pulse limit. IO path with retain conditional and non-conditional specified path delays or pulse limits. Retain may be ignored. So here this particular construct helps to ignore. Condition with IO path. Conditional specified for path with delay and pulse limit. So here is the straightforward mapping. Let's move on to the next slide. We continue our table here. Then we have the condition, then IO path, then retain. What will happen? In the Verilog, conditional specified paths, delays, path limits, retain may be ignored. Here we also can use the retain for ignorance. Condition else IO path, if there is none. And then if we append the IO path and then retain may be ignored. These are the syntaxes that you have to tally the SDF file and your Verilog design file side by side and then you will be able to understand. Wait, we have some examples here for easy understanding. You're done here. Let's move on to the remaining part of the table. Here for delay, this is the final part and we have completed here the delay part. So here is a device where it annotates all specified paths to the module outputs. If no specified paths, all primitive driving modules out. So these are few advanced things. You have to have your SDF and Verilog side by side to understand and compare, right? Next, we have device then port instance. If port instance is a module instance, all specified paths to module outputs. If no specified paths, all primitives during the module outputs. If port instance is a module instance, output all specified paths to that module out. And if no specified path, all primitive driving that module out. This way the mapping should be there in between the SDF constructs versus the Verilog annotation zone or construct for the delay components. We're done here. Let's move on to the next slide. Here we see the example of the so far things we have talked about. So here it's a SDF construct, right? And here we have actual values. So IO path, then cell, then Z out, 1.3, 1.7. I have explained all these terms SDF file episode. So please go ahead and watch that. Description of this video contains the URL of the video. And here in Verilog, how we see, we can have this kind of relation condition where you can see that all these values will be annotated back. So these values, whatever we are getting here, will get annotated here. Next, we have a more detailed one, condition, then mode, then IO path, then cell, then Z out, then this value. How it will get, right? There are two ways, positive logic and a negative logic. So here, if condition is there, then we have this value, and if this condition is there, we have this value. In this way, we can get the values back annotated in the Verilog. Similarly, this one is there. You can see we have both the negative and positive logics here again, and these values will go into this. This way, the things will get mapped in your Verilog code. So you have to be very careful when you are seeing or mapping it back. So that requires the expert skill set, not a beginner or novice level skill set. And you can consider this episode as an expert episode, not as a novice or beginner episode. So at that level, you can do the mapping and do the back annotation. Here we are done with the example. Let's move on to the next section. SDF to Verilog mapping for timing check. Here are the things set up. So here we have SDF constructs in the left hand side, and right hand side we have the Verilog annotation zone or construct. This is much more straightforward than previous type of mapping. This for the timing check, we have the mapping setup time, that is V1. So we have already predefined system functions here or system tasks here. Here it will pick up this system function or task correspondingly. For hold, we have these functions. For setup hold, here we have all these functions. For recovery, we have all these functions, and for removal, we have all these library functions available in Verilog. Those will be used for mapping. And through these functions or system tasks, right, you will be able to, that are declared within these constructs, will be back annotated into the Verilog through this. So here we are done with the mapping. Let's move on to the next section. We continue the table here, and we have this particular constants, that is RECREM, and that is we can map it to the recovery, removal, RECREM. For skew, we have skew. For time skew, we have time skew. For full skew, we have full skew, and for width, we have width. So all these SDF construct can be easily back annotated through the Verilog predefined library function or tasks. So here we are again done. Let's move on to the next slide. Here we continue our table, and this is the final page. So here you can see this is the period and which will be mapped to the Verilog system function or task. Period for no change, have no change. So this is, you can see that for the timing checks, it's very straightforward to use the system function or task. We're done here for the mapping. So let's move on to the next slide. We have talked about the mapping. Now let us see some examples for the timing checks. In left hand side we have SDF constructs, and right hand side we have the Verilog annotation zone or construct. You can see setup, hold, etc. here, and we have the complete SDF syntax, and what it will call, the setup, hold, system function or task, and this way we can use its syntactical form to map all these values. And similarly this would go here. Again, I am saying that there are two modes, that is a positive logic and a negative logic, that is controlled here. So you can use those as per your need. Setup, hold, data, passage of clock, and we have the rest of the SDF construct. So here what it will call, the system function setup and hold, setup and hold. Again, I am saying there is a positive and negative logic here, mode and bank mode, and in this fashion it will be the syntax will be written and the SDF values will be mapped here in the Verilog. So here you can see the passage and negate is here and passage and negate is here. So here we have seen only the passage, but however in actual practice we can have both passage and negate. And here we have the third one, setup and hold, and we have some conditions here. Here you can see again there is a positive and negative logic here, and you can see passage or negate is also here, and in similar to the previous examples you can see it is taken care well in the syntax, and all these SDF construct can be mapped very well to the Verilog annotation zone or construct. This is a very advanced topic. It will take for you some time to understand and implement all these things into your Verilog code or SDF code. As a beginner you can have a touch base, so that when you are working in a company, once you see all these things, you can come back to the video and you can have the correlation quickly and do your task in the working environment. So here we are done. Let's move on to the next slide. Here in this slide we will talk about the SDF and Specparams, the correlation in Verilog. Here is our SDF code, and in right hand side we have our Verilog code, and in SDF code you can see these are the basic constructs, right? And here is our variable d high is 60 and d low is 40. In the right hand side Verilog code you can see that here we have defined the Specparam d high and d low with initial value 0, and that will be used in the code. And here you can see d high and d low are getting used in the always block. So when this annotation is done, so this value, this will go to here and this value will go to here. So this way things will get back annotated. The Verilog code simulation will start with the initial 0 values, and because of the annotator tool, these two values will be back annotated here. So this is a very simple thing to understand where the Specparams play a good role in back annotation from SDF into the Verilog. We have also have Specparam episode here itself in this Verilog series. Please go into the playlist and find that episode for detailed understanding of the Specparams. And also I am providing the direct link of the video in the description of this video so that you can understand the Specparams properly and without a glitch. So here we are done. Let's move on to the next slide. Dealing with multiple SDF files. So this is the last slide of this presentation, and here we will talk about the real-time scenario, because in ASIC design we have multiple SDF files. One may be from pre-layout version, one may be from post-layout version, or maybe some from one team and another team. One team is analyzing one part of the code, another team is analyzing another part of the code. What will happen in that real scenario when there are multiple SDF files? Before this slide, whatever we have talked about, we have a single SDF file and we have a single Verilog file where we are doing the mapping and changes. Now here what will happen? This will happen. Yes, more than one SDF file can be back annotated into the Verilog code. Each call to the SDF annotated task annotates the design with timing information from an SDF file. Now what will happen when there are multiple SDF files? Annotated values modify, increment or override, that is absolute values from the earlier SDF files. That means when we use put SDF file in sequence, some values were annotated from this file. If we have similar values here, we will get either modify, that is increment, or override, that is absolute value from the SDF file. This can happen. That means either modification will be done or override will be done. Next, different regions of a design can be back annotated from different SDF files by specifying the region's hierarchy scope in the second argument to the SDF annotation. This is what a real scenario is. This is what I was saying, that a design is done by different teams. Different part of the design is done by different teams. This is the real-time scenario, because here different design teams are dealing with different parts of the design and they are giving different SDFs. When that SDFs come to the RTL designer, what happens? That you try to back annotate all of them. And here we have our Verilog code, and here we have a region, here we have a region. From SDF file, some values will get annotated here. From another SDF file will get annotated here. So we have already talked about when we are facing the modify or the override situation. In addition, if there are multiple blocks and they have different SDF files, they will be separately annotated in sequence or maybe in a simultaneous way. However, they all those values will get incorporated in the Verilog file to the backend and with the SDF annotate construct. Now, my suggestion to you is to consult your latest Verilog LRM, and since now Verilog is a part of the system Verilog, please consult the latest system Verilog LRM, that is language reference manual, for latest and up-to-date syntaxes on the SDF annotate or anything related to the SDF back annotation. So here we are done talking what will happen with the multiple SDF files which happen in actual ASIC design. We are done here. Hey guys, welcome back. In today's episode, we are going to discuss the below topics. First, we will talk about the various display functions in Verilog. These are called display tasks. Next, we will go in the detailed and explicit description of display and write. These are two different tasks. We'll go in the explicit detail of these two. We will share what is their similarity and also what is their differences, so that you can use them as per your need, and any confusion about these two should be removed from your mind. Next, we will talk about different format specifier. These are very essential for the printing of different variables that are under the Verilog simulation. This is a very important list and you have to keep it handy. Next, we will go in the details of the strobe task, and here you will see how it is different from the display and write. Next, we will talk about the monitor task, and let me emphasize this monitor task is a very widely used display task in Verilog. So here we will talk about 4 types of display tasks, that is display and write, and strobe, and then monitor. So this all we will cover in our today's episode, and here we are done with this particular slide. Let's move on to the next slide. Types of display tasks in Verilog. So let me show a chart here. First, we have the display task category. Under that, we have 4 different type of display tasks. First one is display and write. Next one is strobe. Third one is monitor. And fourth one is the continuous monitor. So we will cover all of them, don't worry. And these are the types, right? Monitor and continuous monitor, these are the application specific categorization, whereas the inbuilt categorization comes with display, write, strobe, and monitor. So here we are done with this particular slide of categorization of different kind of display tasks that exist in Verilog. So let's move on to the next slide. Display and write tasks. Display and write are main system task routines for displaying information. These are like printf functions from C. Generally, these two you will use the most. $display automatically adds a new line character at the end of its output, whereas the write does not. These are the 2 tasks. You see the first difference here between display and write. As per Verilog convention, we use a $ to signify this is a system task or a system function, and it should be used in this way only. Now, when you use the display, when you have to enter a new line character, by default, whatever you give the string inside to print, it adds a new line character at the end, and your cursor will go into the next line in the printing part, that means in the log or maybe in the monitor. And when you use write, we are printing different text and we want to keep them in a single paragraph. So in that case, you will use the write. Until or unless you want to go to the new line, use it. And next, when you want to use a new line, you can use this is one of a kind of a use, but it is not limited. You can do the things as per your need. The $display and $write task display their arguments in the same order as they appear in the argument list. So this is the similarity. Argument means these are the tasks. So definitely there will be a pair of braces where you put all the arguments, where there will be strings and maybe variables with the format specifier and so on. These two have the same order of the argument. Above mentioned argument can be a quoted string, an expression that returns a value, or a null argument. These are the different types of argument you will face in your Verilog coding for display and write tasks. The contents of string arguments are output literally, except when their certain escape sequences are inserted to display the special characters or to specify display format for a subsequent expression. If we have a kind of format specifier, that will be replaced by the respective variable. Otherwise, it will print as is. So here we are out of the scope of the page, and we will continue our discussion on the same in the next slide. Let's move on to the next slide. Escape sequences are inserted into the string in 3 ways. So escape sequence is something that you need in every programming language like \n or so. How these are done here, let us see. The special character / indicates the character to follow is a literal or non-printable character. That means when we have a \n, it denotes a new line and hence it will not be printed. Instead, there will be a carriage return, or maybe the cursor will go to the new line. The special character % indicates that next character should be interpreted as a format specifier. So these are escape sequences. So this will give a new line character, maybe like that, or tab, right? \t. And this is the format specifier like %d, %s. All these things will be considered. So these two are special characters. You have to remember their use, and you should not exchange them, because then the meaning will be disrupted and the Verilog code will not accept. So whichever is applicable to the respective area, you should use that. For each % character in a string must have a mapping argument containing an expression. This is associated with a format specifier, so you must have an argument that should get fill up or replace the percentage something, whatever we are writing with the percentage character. Exception to this rule is %m and %%. So these are the 2 things which are exception for this rule. So I'll explain these 2 also in this slide. The special character string %% indicates the display of the percentage sign character, that is %. So if you have to print a %, maybe somewhere in your text, you have to use a %, that will give the %. So you should not use a \& and then %. That will not do. You should do a %, and that will print a %. Any null argument produces a single space character in the output display. Suppose you have written a percentage something and you forgot to mention its argument, right? Argument in the right hand side. What will happen? So nothing will be replaced and there will be a single space. That means a space character will be entered there. The display task, when invoked without arguments, simply it prints a new line character. You know from the definition, right? The display task has a new line inbuilt. So if you do not give any argument, it will just print a new line. So you can use it in that fashion only. You have to insert a new line somewhere. You are using write, different write statement, and you give just a display statement without any argument. So that will print the new. This is one of the use. You can use this thing as your own need or own coding style, whatever is applicable. A write task supplied without arguments prints nothing at all because the write task do not contain something like a new line. It do not contain anything. So it will print nothing. So there will be nothing on the screen if we write a blank write task. So here we are done with the display and the write task and we are end of this slide. So let's move on to the next slide. Format specifiers. In previous two slides, we have talked about the format specifiers through which you can print an expression, any variable, whatever is applicable. In this slide, we'll take a short tour of the format specifier that are mostly used so that you can use them as per your need. And here comes the first table. Right? So percentage small h or capital is used for hexadecimal format display. Percentage d or percentage capital D is used for display in the decimal format. If we have a percent small o or percent big O, that is a capital O, it is display in the octal format. Percentage small b or percentage capital B used to display the binary format. Percentage c or percentage capital C display ASCII character. Character means single character. Percentage small l or percentage capital L display library binding information. For details of the library binding information, you can consult the LRM, that is the Language Reference Manual of Verilog or System Verilog, since now the Verilog is a sub part of the System Verilog. Here comes our next step. Percentage V or percentage capital V used for net signal strength. It displays the signal strength of net. Percentage small m or percentage capital M display the hierarchical name. Now, this gives a hierarchical name. Means we have a hierarchy of the like top. We have something at the top, right? And then we have A, B, C, D, E like that. And then we are going to the leaf cell, right? All this entire hierarchy can be printed with percentage M. Percentage S or capital S display as a string. So this is, you know, from your C language knowledge, right? Percentage S or percentage capital S can be used for a string. Percent T or percent capital T is for current time format. It is used for time. Percentage U or percentage capital U is unformatted 2-value data. And Z and percentage capital Z are used for unformatted 4-value data. So these are not very much widely used, these two. So you have to consult the LRM for detail and actual uses. I included everything here so that if you take the snapshot of this page right now, you have something handy so that you can consult. And some which are not used in a regular fashion, maybe rarely used, sometime you may need that. So I did not exclude them, I have included. We are done with this particular slide. Let's move on to the next slide. In this slide, we continue with the format specifier and some more format specifier we are going to describe here. Here goes our table. So percentage E or percentage capital E display real in exponential format. E for the exponent. If we give the percentage A for percentage capital F, it display the real in the decimal format. The percentage G or percentage capital G display the real in exponential or decimal format, whichever format results in the shorter printed output. These two are specific and this is a generic. So here there is an auto decision what will be printed for a real number. Percentage M, it does not accept in an argument hierarchical name of a module, task, function or named block that invokes this system task containing the format. Whenever any task, any display task is called from any particular module, right? If we include it in the display or something like that, this percentage M will print the hierarchy. So which I have just said, right? From the top cell, if we go down and go down to the leaf cell, from top cell to the leaf cell, this hierarchy, whichever cell is this, if we include this in the leaf cell definition, the entire hierarchy will be printed. And wherever this cell is, this cell could be here, so that time this will be printed. Percentage S prints the ASCII codes as characters. So this percentages print the string. That means not the single character, that is a bunch of character. That means generally a line or string. So here we are done with this particular slide, and here you can take a snapshot so that you can save it for your later use. Here we are done. Let's move on to the next slide. Strobe task. So far we have discussed about the display and the write task, and in this page or in this slide we'll talk about the strobe task. The system task strobe provides ability to display simulation data at a selected time. That means we have a time selection here. The arguments for this task are specified exactly in the same manner as for the display. So arguments are in the similar order. Specialty, we have a time selection here. For example, forever @negage of clock. And we use strobe at time %d, the data is %h. So you have time data. So this task is tied up with this one. That means with the negage of clock, in that time, the strobe actually prints this in the %d and %h, that is decimal and hexadecimal. Time is in the decimal format and data is in the h. This is the time bound. That means it's not a generic. It is only triggered when we enter this forever loop. Here, although it is 2 bullets, but this is a part of the code. While formatting, I have just kept it as in the bullets. But in actual Verilog code, these 2 lines are back to back in a line of code. In this code, strobe writes time and data information to the standard output and the log file at each negative edge of the clock. So that means this is a time-bound display format. The time-bound is controlled by this. However, at that particular time, strobe will be called. So this is the use of the strobe if you want to display something at a particular time event, right? Like negage of clock or pausage of clock or something, anything. There is a time marker attached with it. Maybe it's a periodic or it's maybe a non-periodic manner. In that case, you can use the strobe, and the arguments and the printing, everything is similar to the write or display. So we are done here with the strobe task. Let's move on to the next slide. Monitor task. The monitor task provides the ability to monitor and display the values of any variables mentioned in the arg. And let me emphasize here, the monitor task is very much widely used rather than any other display task in Verilog. Most of the test benches, when you are testing your module which you have written, if you go back to maybe episode 1, 2, 3, 4 of this series, if you are watching from playlist, otherwise if you go to the playlist of Tech Simplified TV and find out the first 3-4 episodes where I have shared the code to how to run your first Verilog code. Here you can see this monitor task is used the most widely. And in fact, in general, when you are writing your code, Verilog in your actual practice, maybe in the industry, monitor task is used from any other task because of its application. It can monitor, actually, it's not a very simple task. It can monitor the changes. Let me see how. The arguments are specified exactly in the same manner as display system task. When a monitor task is invoked with one or more arguments, the simulator sets up a mechanism whereby a time variable or an expression of argument list changes, with the exception of $time, $s_time or $real_time system functions. The entire argument list is displayed at the end of the time step as if reported by the display task. So, whatever argument we are providing, whenever any of those argument is changing, the monitor keeps a watch on them. At any change of one or more argument, the entire string that is given to the monitor is printed, and maybe you are displaying with some format specifier, right? All those data and all those arguments you have provided, all those things will be printed anytime any of these arguments are changing. That is the beauty of the monitor. If 2 or more arguments change the value at the same time, only one display is produced that shows the new values. That means if 2 arguments change simultaneously, only a single line will be printed, not 2 lines. Only one monitor display list can be active at one time. Multiple monitor statements cannot be there. Only one monitor could be there because it is monitoring. You can put a single monitor statement, watch over all the things. The monitor on and the monitor off, these 2 tasks control the monitor flag that enables and disables the monitoring. That means by default this is on, and if you want to turn off, you have to use it at any point. Maybe from time T1 to T2 you want to turn off the monitor, right? At T1 you have to use the monitor off, and then at T2 you have to use the monitor on. These 2 tasks to suppress the monitoring for that particular time span from T1 to T2. By default, the monitor flag is turned on. That means yes, this is turned on, which I already mentioned. The beginning of the simulation time. So at time t equal to 0, the monitor on is flagged on by the simulator by default. It could be any simulator. For Verilog, this will be turned on. You have to turn off at T1, you have to use the monitor off, and T2 you have to use the monitor on again, so that things will be monitored after T2. T1 to T2 it should be blank, and then from T2 onwards up to the simulation end time, anything will be printed with the monitor on. So here we are done with this particular slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. Introduction to VCD file. We will talk about what is a VCD file and what does it contain. Next, we will go for the description and details of the dump file and the dumpware tasks that are available in Verilog. Next, we will go through the example of the dumpwares. Next, we will talk about the method of pausing and resuming the data dumping during a simulation. Next, we will talk about how to view the live VCD file. This is very important because for a long simulation time, this information will help you to view the VCD file while it is being created. So, that's the menu for today. Without any further delay, let's begin. Introduction. A VCD file contains information about value changes on selected variables in the design stored by the VCD system task. All these system tasks are part of Verilog and some of them we will talk about in this video. VCD files are not the part of the Verilog RTL design. Rather, this is the file. It is used inside the test bench module for verification and debug purpose. So generally, these VCD files are part of your debug and verification. It is not part of the design. However, this is an essential part because a design needs to be verified and debugged for proper function. This file is created during the Verilog test bench simulation. Post simulation, we can open the file in waveform viewer. Generally, in Linux, we have GTK-Wave, and this GTK-Wave, we have an episode. The link is given below in the description of this video. Most of the commercial IDE tool comes with their own waveform viewer capable of reading the VCD file. So this kind of waveform viewer comes as pre-bundled with the IDE simulation tool that can simulate the Verilog file, and I would like to emphasize this is for the commercial IDE tools. Free and open source tool GTK-Wave can be used to view the VCD file where you do not have any proprietary software. So the VCD file you can view with GTK-Wave. I'm again emphasizing that the link of the GTK-Wave video that we have already created in our channel is mentioned in the description of this video. There can be two types of VCD file by construction. Again, the construction means when the file, if you open it maybe in a notepad or so, you can see the construction. But for your Verilog debug and verification purpose, you must not bother about the construction. These two types are 4-state VCD to represent the variable changes, that is 0, 1, X and Z with no strength information. Another one is extended VCD to represent the variable changes in all states and strength information. So all state and strength both are included. So here in the first one, no strength information is present. That is the basic difference between a 4-stage VCD and the extended VCD. One thing I would like to mention here, you do not have to bother about the 4-state and extended because these are the file structure. When you open this VCD file in GTK-Wave, you will see the waveforms. So be rest assured that you don't have to go and code this 4-state and extended VCD. It's just an output, and this is just for your general knowledge, so I have kept this in this slide. So here we are done with the introduction slide. Let's move on to the next slide. Dump file and dumpware tasks that are available in Verilog. The dump file task shall be used to specify the name of the VCD file. So we have to give a name to the VCD file. This is, you know, right, from any programming language. When you open a file, you have to give a name using the fopen or functions like that. Here we have a similar system task called dump file that can assign the name of the output VCD file inside your Verilog code. Obviously, you can use it inside your Verilog code. That means the Verilog test bench. This is the example. So we have an initial one line, that means the inline initial block here. We have the dump file command, and here we have given the name within the double quote. So the module1.dump. This way you can name the dump file. Generally here instead of dump we write .vcd. Okay. Generally we write here VCD. However, this is the syntax that can be used to dump a VCD file. The dumpware task shall be used to list which variables to dump into the file specified by the dump file command. So here definitely we will have different ports and their variables in Verilog, right? They will change values as per our input vectors, and those changes in the ports that we are probing, they must be given to the dumpware command so that we can later view all their waveforms in the GTK-Wave. Why I mention about the GTK-Wave? Because it's free and you can readily use it. Otherwise, if you are using a commercial tool, you will have a bundled waveform viewer. You can use that also. The dumpware task can be used with or without arguments. Dump task, when invoked with no argument, it dumps all the variables. If we do not mention anything as an argument, so all the variables that are inside your Verilog module, all the input output ports, all of them, whichever is changing, right, they will be dumped in the VCD file. With arguments, the dump task, first argument indicates how many levels of the hierarchy below each specified module of instance to dump the VCD file. So the first argument mentions about the hierarchy level. That means the 1 level down, 2 level down, 3 level down or 10 level down. That particular hierarchy is given in the first argument. Subsequent arguments specify which scopes of the model to dump the VCD file. These arguments can specify entire modules or individual variables with a module. We'll come up with example, don't worry. Putting the first argument as 0 causes a dump of all variables in the specified module and in all the module instances below the specified module. If we put 0, there will be a consequence that will dump all the variables in the specified module and the module instances below the specified module. Means the level of the hierarchy that we have given and all the rest of the down hierarchy. So here we are done with the descriptions and a small example of dump file and dump bash. So let's move on to the next slide. Dump bash example. Here, dump bash, we write 1 and top. As the first argument 1 is 1, this statement dumps all the variables within the top module and does not dump variables in any of the module instantiated by or inside the module top. This means this for this module only. So that means, say, you can think of the hierarchy like a staircase and the floors associated with it. A floor has different rooms, right? So this can be the instances. So if you are standing at this level at the top and you have given 1, so all these rooms, that means all these instances will be taken into consideration for the dumping of their variables. Next, we have dump bash, then 0 and top. In this example, the statement shall dump all the variables in the top module as well as all the instances below the hierarchy. That means again I am drawing the staircase. So this is top, right? And we have mentioned 0 here. That means all the rooms here which we are around, right? In the staircase, if we are going and at each staircase we have a level, right? So all these rooms at this level will be taken into consideration. That means all those hierarchy down, we will get all the variables there, all the instances there. So all those variables will be dumped. Third one, dump bash, we have 0, again this is common, and we have top.mod1 and top.mod2.net. So these are two hierarchies. This is top, then we go one direct hierarchy down, and in another direction we have top, then mod2, and then we go another. So this is net, so this is not a hierarchy, net 1. So this statement shall dump all the variables in top.mod1 module and all the instances below mod1. So this will do under this, and along with the variables net1 in the top module. So this is the net selection, this is a module selection. All the things under this will be covered, and this particular net from where to where it runs, all the variables inside that will be covered. So this is the example of the dump bash, how you can use it. Let's move on to the next slide. Pausing and resuming the dumping of data. This could be very, very important because at some point you may not need the data from time T1 to T2. This is your simulation entire runtime, right? This is 0 and this is end. I write E. And here somewhere in this particular window, you do not need any data. So you can pause here and you can resume here your data dumping. The rest of the thing is unimportant. So how to do that? Executing the dump task causes that value change dumping to start at the end of the current simulation time. To suspend the dump off tasks, this task dump off can be used to suspend, that means pause the dumping of the data, which I mentioned, right? Long time, and we have a window where we do not want to dump. So here we call the dump off. Next, again to resume the dumping, that means again to turn it on, we can use the dump on task. The dump on task is again called here, and this entire period the data will be blank. Here data will be printed and here the data will be printed. This is your end, this is your beginning, and this way you can exclude this particular part. And there can be multiple such parts in your entire simulation where you do not need any data. That is up to you, where you want to stop and you want to resume. That is up to you. You can use these two tasks. One example here, initial begin, and we have n amount of time delay. We have dump bash. Then at 20 we have dump off. Here we stop dumping all the data. That means here to here, right? This is start in, and here this is 20 after 20 time delay. After that means this is 10 plus 20 means this is 30. This is 30, right, from the beginning, because at 10 we have dump values and this is natural simulation time. This is 30. Next we have 80, that is this marker is at time, right? 10 plus 20, 110. This is 110. At that point we are turning on the dump ons. Any data between this region is blank. Data from 0 to 30 and 110 to the end will be there. At 90 we have dump off and we end it here. So at 90 means again 90 to it means this will be 200. At 200, right, time unit, there we again switch off the dumping and rest of the thing will be blank and we end here. So this is a typical example. In actual simulation we will have reasonable numbers, and there you can use the dump on and dump off to exclude a region where you do not need any data, and this helps you in a quick debug when there is a large simulation time and you have to debug at some particular window and you have to turn on other windows. You do not need them. There you can pause and resume. This is very useful when you are debugging, and I again mentioned that the entire VCD file thing is for your testing and debug purpose. This makes your debug much more easy. We're done here. Let's move on to the next slide. How to view the live VCD file. That means when the VCD file is getting generated, how you can see that. The dump all task creates a forced checkpoint in the VCD data that shows the current value of the all selected variables. The dump limit task can be used to set the size of the VCD file. The file size argument specifies the maximum size of the VCD file in bytes. So this is another couple of good tasks that you can use in your debug. I did not get any other space or other slides for them. I have just included them. Please excuse me for that. And here we have dump all creates a force checkpoint, and the dump limit limits the size of the VCD. And this is again for quick debug, right? We need a particular size because we do not want to overflow our disk space that has been allocated by our Unix admin. So that is the reason. When the size of the VCD file reaches a specified number of bytes, the dumping stops and a comment is inserted into the VCD file indicating the dump file limit has been reached. So this message goes there. If you open it up in a notepad kind of application, then you can see it. Otherwise, you knowingly doing it, so you don't need to go and check. The dump flash task, right? Now we are coming to our point, the live VCD file. How we view that can be used to empty the VCD file buffer on the operating system to ensure all the data that in the buffer stored in the VCD file. After executing a dump flash task, dumping is resumed again and with no value changes or loss. That means when you use the dump flush command, it's like a flush command in a programming language, right? To the std out or std error, whatever you are using, right? So like that, when you flush it, right, your original data that is getting dumped into the VCD file does not change. Only your display buffer gets the value of all the variables. Example, how to view the live VCD file. Here we give an example. Initial begin, we have an initial block, and then we have dump bash, and we have dump flush here, and then we have a $path to invoke the VCD application program. So here we can invoke our program that can actually view the VCD file. And here we end. Here is the flushing of the VCD file into the std out, where you can actually view the live VCD file with your viewer and you can use them. So this is again for the debug purpose. It is not part of your VLSI design. It is for your debug. Quick debug, you need to have some handy task and all those things that you can use to make your debug efficient and quick. So here we are done with this particular slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. Introduction. Next, we will list of available compiler directives. Next, we will focus on the backtick include compiler directive. We will proceed our discussion with if def, if not def, else, else if, and end if. We will see various combinations for which all of these can be used. Next, we will talk about the backtick reset all directive that is used in conjunction with many of the available compiler directives, and this one can reset many of the available compiler directives effects. Next, we will talk about a cell define and a end cell define directive Next, we will talk about the default net type. This is a very important one because when you are writing a Verilog RTL code, by default, what type of net is selected, that is very important. So that is defined by the backtick default net. Next, we will talk about the pair of keywords, that is the begin and end keywords. Next, we will talk about the pair of compiler directives, that is begin keywords and end keywords, which are used to declare user-defined keywords. That means the keywords which are not in the Verilog library, rather with the keywords that are defined by you, that is the end user. So that's the menu for today. Without any further delay, let's begin. Introduction. The scope of compiler directive extends from the point where it is processed. That means you have multiple line of code and at some point you have defined the compiler directive. From then on, the effect of this directive is processed and across all file process. That means there are several files which may be included by a backtick include directive. All those files, when they are inflated during the compilation and simulation, that time this particular directive which is defined before it, that will be also applicable for that particular code, to the point where some other compiler directive supersedes or the processing completes. That means up to the point where any other directive nullifies its effect. Next, all Verilog compiler directives are processed by the backtick character, which has a ASCII value of 60. And this backtick is very different from the apostrophe character, which has a ASCII value of 27. So that's the basic introduction for the compiler directives. Let's move on to the next slide. List of available compiler directives. So here we will list out the available compiler directives that can be used in Verilog. Available compiler directives in Verilog are begin keywords, cell define, end cell define, default net type, define, undef, end keywords, and this is paired with the begin keywords. This is paired, and define and undef are also paired. Next we have non-connected drive, unconnected, and these two are also paired. Similarly, the begin and end keywords are paired. These are the compiler directives that are available. Let us extend to some more list here. The list continues. If else, if, endif, if undef, include, line, pragma, reset all, and timescale. Some of this today we will be discussing, and we have already made a detailed episode on the backtick timescale because it is hugely used in Verilog design. The link of the video is given in the description. We're done with this particular slide. Let's move on to the next slide. Here in this slide, we will talk about backtick include. The file inclusion, that is the backtick include directive, is used to insert the entire content of a source file into another file during compilation. This is very similar to the C language backticking, where you use the include directive to include the stdio.h. So it's very similar to the C. Advantages of it are: helps to incorporate the benefit of a configuration management system, that is CMS, for code versions. We have different codes and that helps to maintain the backtick include. Now how this happens, right? When you have your source code here, there is something that is included, and time to time these things may have different versions again. So if all these things are in repository, when you are compiling your code, right, the right version or the latest version will be pulled from the repository. So this backtick include helps you in that way. Helps the RTL designer to organize among various Verilog source code files. When you are writing the code, right, if you are using a bottom-up approach, right, in a design, so you have first defined some blocks, right, and then you are designing a bigger block using those blocks. So these are kept in separate files and these will be included in your bigger Verilog code using the backtick include. So this way you can manage your code structure. Facilitating the eye-on-term maintenance of Verilog HDL source description and code reuse. The code reuse is a very important thing here because whenever you write a code, right, piece of code, you don't intend to write it again and again and again in different cases. So you write it, you keep it in a repository or a hard disk location from where you use a include directive to include this piece of code. Examples of backtick include are as follows. Backtick include, then parts, then count.v, then include file A, include file B. The file name here can be full path or a relative path. Relative means you have a dot dot then slash and then you have dot dot then slash and then you start with the path. So that means this is a relative path. So please watch our Linux series for the relative and absolute path. There I have created episodes where live demonstration of the accessing the Linux system is there. There you can get familiar with such relative and absolute paths. Link of the Linux tutorial series is given in this video description. Here we are done with the include directive. Let's move on to the next slide. If def, here in this slide we will talk about if def, if not def, else, else if and end if. Now all these things are here and various combinations of them can be used. Here we will have a general idea in this slide. These conditional compiler directives, abbreviated as CCD, are included optionally in a Verilog HDL code. Situation where the if def, else, else if, end if and def compiler directive may be useful, including the following. Selecting different representation of a module such as behavioral, structural or switch level. Choosing among different timing or structural information. Selecting different stimulus for a given run. Nesting of if def, def, else, else if, end if compiler directive shall not be permitted. Now the cases where it can be used, like we have talked about these things, where we have multiple choice of direction. That means we have multiple roads to go ahead. So there we apply the condition using all these compiler directives. That is the conditional compiler directives called CCDs. So here we are done with our introductory slide. From next slide we will see the combinations in which all these 5 can be used. Here in this slide, we will talk about if def, else and end if usage. The if def compiler directive checks for the definition of a text macro name. So generally text macro, if you are familiar with C language, you already know about the text macro. If the text macro name is defined, then the lines following the if def directive are included. If the text macro name is not defined and else directive exists, then this source is compiled. So this way the if def, else and end if, these things can be used. Here there is a pair, you can see, right? If def and end if. So these are paired. So it starts the conditioning and this ends the block. And in between we have else. The end if compiler directive ends with the if def block, which I have just mentioned. So here we are done with this particular slide. Let's move on to the next slide. Here in this slide, we will talk about if and def, else, end if, how these are used. The if and def compiler directive checks for a definition of a text macro name. It's similar. If the text macro name is not defined, earlier for if def it was defined, that true condition was checking. Here we are checking about the false condition. If not defined, then the lines following the if and def directives are included. The text macro name is defined, then and an else directive exists, then this source is compiled. Basically, if not defined, it goes to the first block with the if and def, and if the text macro name is defined, means the opposite, the code for the else block will be compiled. So this is the way it works. Here we are done with this particular slide. Let's move on to the next slide. The end if compiler directive ends the if and def block. As I have mentioned, this is the starting and this is the ending. So these two are paired and in between the else exists. It is similar as the previous slide which I have talked about. Here we are done with this particular slide. Let's move on to the next slide. Here in this slide we will talk about if def, else if, end if, how these things are used. The else if directive exists, the compiler checks for the definition of the text macro name. If the name exists, the lines following the else if directive are included. The else if directive is equivalent to having a else block and within we have a nested if def and an end if. So this is equivalent. The entire thing is get replaced by the else if block. This directive does not need a corresponding end if directive because the if def that will have its paired. So these do not need another end if. This and these are paired. So these two will complete the block and the else if will reside in between. The first, what happens, the if def condition is checked. If it is not fulfilled, then it goes to the else if condition and there all of this thing happens and then the entire block is ended by the end if condition. This directive shall be preceded by an if def or if and def directive. So here we are done with this particular slide. Let's move on to the next slide. Define and undef. So here we will talk about two different things, that is define and undef. And just a reminder, we have come across the conditional compiler directives, that is CCDs, and previous slide was for them, and here on we are talking about very different things, and we start with the define and the undef. In the situation where a constant number is repeatedly used throughout a description, a text macro should be used in that case. If the value of the constant needed to be changed, only the source description need to be altered. The directive undef undefined previously defined text macro. That means the undef reverses the action of the define. The text macro facility is not impacted by the compiler directive reset all. The text macro names cannot be same as the compiler directive keywords. This is another very important point, because if we write a text macro as keyword, the compiler will get confused and it will throw an error. So this point has to be noted. Our text macro name cannot be same as any of the compiler directive keywords. Redefinition of text macros is allowed. That means once you define something with the define, at some later point you can again use a define to redefine it. The latest definition will be retained by the compile. That is the provision that our Verilog compilers have. Example: backtick define word size 8. Then we have range 1 down to word size data. Next we have define max, and then we have this text macro defined here. You can see it's a conditional block, right? Or you can say it's an inline function type thing, and then we use it like this. And later we can have this also. This exemplifies the define. And let me hear what happens. This text macro is mapped with 8, and hence in the compilation time this is put here and expanded. And we define max as this, right? A and B, and here when we are writing the code, right, all this, it will be expanded as. So this way the expansion takes place using a text macro. So I have exemplified with different examples. Hope you have understood. And anything you have defined using the backtick define can be undefined using the backtick undef. That means if you write undef word size 8, so this thing will be removed, or you can say this is undefined. So here we are done with this particular slide. Let's move on to the next slide. Reset all. So here in this slide we will talk about reset all. Here we start with, when a reset on compiler directive is encountered during the compilation, all the compiler directives are set to default values. That means this directive, the reset all, resets all the previously defined compiler directives. This is useful for ensuring that only directives that are desired in a compiling particular source code file are active. The best practice for a RTL designer is to use the backtick reset all at the beginning of each Verilog source code and before any other compiler directives are used. This means when you are writing a piece of code, at the very beginning, if you write the reset all, right, by mistake, if any other code has something macro or something is defined and which you are reusing here in this code, it resets any previously defined things that are there. Although generally we have the undef. I've just given an example just for your understand. However, going throughout this video, you will come to know which things are getting resetted by reset all and which compiler directives are not. It is illegal for reset all directive to be specified within a module or a user defined protocol. So you cannot use it inside a module or UDP. That you cannot do. We have talked about module and UDP in the very beginning episodes of this series. So in case you have not watched, please go ahead and watch them. Here we are done with this particular slide. Let's move on to the next. Here in this slide, we will talk about the cell define and end cell define. The directive cell define and end cell define tag modules as cell modules. That means if you written a module, in case you would have to define it as a cell, these two pairings have to be done in the beginning and the end. That will define it as a cell. It is advisable to pair each cell define with an end cell define, but it is not required. It is advisable that you keep a practice of writing the cell define with a paired end cell define. These directives may appear anywhere in the source description, but it is recommended that the directives be specified outside the module definition. More than one of these pairs may appear in a single source description. The latest occurrence of these directives in the source control whether the modules are tagged as cell module. The reset all directive includes the effects of a end cell define. So here you come to know that if we use the reset all, that does the purpose of the end cell define. Previously we have talked about the reset all, right? So as I mentioned, we will come across the instances where the reset all can act. So here is one example that reset all can act here end cell define if you are using. So here we are done with this particular slide. Let's move on to the next slide. Default net type. The directive default net type controls the type of net that are created for implicit net declarations. The possible net types are where, try, try0, try1, want, try and, WOR, for, prior, try-reg, UWhere, and none. Default net type will set your default net type in your Verilog code, and the possibilities of the list is written here. Next, it can be used only outside of the module definitions. Multiple default net type directives are allowed. The latest occurrence of this directive is the one which controls the type of implicit net. So that means you have written the different default net type statements, and the last one will be active, and before to the previous ones will be inactive by the compiler. When no default net type is specified or reset all is specified, implicit nets are of type where. So that means in case you are not using this or using this, what happens that the default net type is where. So here we are done with the default net type, and now let's move on to the next slide. Begin keywords and end keyword. Here let's start. The pair of begin keywords and end keywords are used to specify custom or user-defined keywords within a block of source. These names are very much self-explanatory. Begin keywords and end keywords. That means you are defining a keyword, and these keyword names should not be your predefined or the library keywords from the Verilog. These should be different. Otherwise, the compiler throws an error and it stops. The directives do not affect semantics, tokens, and other aspects of the Verilog language. The begin keywords and end keywords directives are allowed to operate only outside design element like module, primitive, or config. So that means these two has to be used outside any module level. The begin keyword directive impacts all included source code across main source code boundaries until matching end keyword directive is encountered. That means anything between these two will be considered as keywords. That is the user-defined keywords. Each begin keyword directive must be paired with an end keyword directive. This pairing has to be done by you, so you must keep a convention of writing the begin keyword and end keywords in pair. So here we are done with this particular slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will introduce you to the concept of the PLI. What is that in Verilog? Next, we will talk about where the PLI is used. Next, we will show you the infographics, how the PLI works in our standard VLSI design process. Next, we will talk about different types of Verilog PLI routines. Those are evolved over time. Next, we will go through a simple example that is a hello world to the PLI routine. Going further down, we will talk about the different user-defined system tasks or functions. Those are associated with the PLI routine. And also, we will talk about the conventions that are used for these user-defined system tasks or function associated with the PLI routines. And there, we will conclude our episode. Introduction. C language procedural interface standard and interface mechanisms are ported into the Verilog HDL. So whatever procedural interface standard that was existing in C language, that has been ported into the Verilog. This procedural interface, known as PLI, provides the means of Verilog HDL users to access and modify data structure in an instantiated Verilog HDL data structure dynamically. An instantiated Verilog HDL data structure is the result of compiling Verilog HDL source description and generating the hierarchy model by module instances, primitive instances, other Verilog HDL construct that represent the scope. The PLI procedural interface provides a library of C language functions that can directly access the data within the instantiated Verilog HDL data structure. So, you can understand that the PLI routine has been ported from C language. Those of you who already have been familiar with the PLIs from the C language or may have used it in the past can very easily grasp the Verilog HDL PLIs. So, here we are done. Let's move on to the next slide. Where the PLI is used. Now, this is a very good question. Where we use the PLI? Let us see. A few possible application of the PLI routines are C language relay calculators. Now why we say C language? Because our PLI routines we have to write in C language, and the target to achieve is the relay calculators for Verilog model libraries can dynamically scan the data structure of a Verilog software product and then dynamically modify relays and any and many instance of the RTL code. So that's the usage. That's the first usage of the PLI routine. Next, we have the C language applications that dynamically read test vectors. Here we focus the test vectors because this is a very important factor in Verilog or system Verilog or other data from a file and pass the data into the Verilog software product. The test vector is a very important thing because this determines the checking of the functionality based on different set of combinations of the inputs. Those are called test vectors. However, in system Verilog, there are assertions. We are not going in that direction because right now we are restricted into the Verilog PLI routines. Next, custom-made graphical waveform and debugging environment, that is GUI for Verilog codes. So this can be developed by a ASIC engineer who is working on the RTL and wants to debug the outcome of a Verilog simulation to the waveform, because multiple time the timing things have to be judged to the waveform, and that can be done using our CLI, and there we can build such GUI to debug those waveforms. Custom-made interfaces to actual hardware that dynamically interact with simulation. Here you saw the custom-made GUI, and here you can see the custom-made interface. Interface means it's a hardware interface. It's not a software something. It's a hardware interface. That means you already have a hardware which is talking to your PC where you are running the Verilog code. And those things you can interrupt and intercept to the Verilog PLI routines. Source code decompilers that can regenerate Verilog HDL source code from the compiled data structure of a Verilog RTL. Sometimes we need, from the compiled language, we need decompilers. Decompilers is a kind of reverse engineering that helps to go up to the code. Say you have got some code which is already compiled from a vendor and your design is stuck at that point, but maybe due to some reason you are not able to see the code or you cannot ask for the code. In that case, you need a reverse engineering, that is the decompilers. So those decompilers you can design here through the PLI and you can use it for the reverse engineering of a compiled Verilog code. Simulation models written in C language and dynamically linked into the Verilog HDL simulation. So this is a kind of dynamic linking, and these are the simulation models. That is a very straightforward thing to understand. And here we are done with the slide. Before moving to the next slide, I would like to say that these are the general usage. These are the general usage of the PLI routines. However, it is not restricted that the usage should be within all these points. The usage could be anything and everything. Get prepared for that. You can use it for your own goal, provided that you are using the right kind of task or function to interpret and intercept the compiled data structure. We are done here discussing. Let's move on to the next slide. How PLI works. Verilog RTL code. First, any VLSI engineer, that is the RTL engineer, writes the Verilog RTL code, and then we go for its compilation. You know very well, this is very easy thing to understand because in past couple of episodes we have shown hands-on example of the Verilog RTL code and its compilation and the waveform and text outcome. Next, we have the compiled data structure. This is what we cannot see in day-to-day work because it stays behind your eyes. But however, there is a compiled data structure. And finally, we have a simulation. The result of the compilation is the compiled data structure. This is very important. Hold on. Why it is important? I am going to explain very shortly. So how PLI at all intercepts this flow? The starting point is user-defined task. So this is your written Verilog code as a RTL engineer, and here you incorporate the user-defined task, that is the PLI routine task, and it goes for the call of the PLI interface and the PLI routines, and the data exchange happen here at this step with the compiled data structure. So this code you write already, you know how to write it. Here you are getting familiar and you will be able to write the PLI codes, right? And through the user defined task, and that will call the PLI interface, and through which you will have the data exchange between the compiled data structure and the PLI routine. So here is the infographics, how the PLI works, and here we are done talking about it. Now the idea is clear how the PLI works. Let's move on to the next slide. Types of Verilog PLI routines. Here we'll talk about the Verilog PLI routines that are evolved over time. So there will be a couple of types of PLI routines and generations that we are going to see in this slide. Task or function routines. These are called TF routines. Here, the first point, these are called TF routines, made up the first generation of the PLI. So this is the first generation PLI. That is the PLI routines and tasks, everything we are talking about. These routines, most of which starts with the character TF, because these are called TF routines. So the routines will start with TF underscore, were primarily used for operations involving user-defined system task and function and arguments along with utility functions. Next comes the second category, that is the access routine. This is called ACC routines. Here you can see these are called ACC routines formed in the second generation of the PLI. The PLI routines evolved over time and the access routine came into the picture as per the need of the time or need of the hour. These routines starts with the character ACC underscore and provide an object-oriented access directly into the Verilog HDL structure. So here you can see the striking difference, right? This is a kind of procedural-oriented code since we are not talking about any objects, right? Here, as the time passed, you can see the object-oriented things become more popular and that has to be incorporated, and that has been incorporated using the access routine. ACC routines are used to access and modify information of objects inside the Verilog HDL description. That is the compiled data structure. Now, you can see that the next one has already come. We are shortly going to that, but before that you can see there has been a striking change from the first generation to the second generation, right? The need of the hour was the objects and the object-oriented things, and those how we can access, because like Java, C++, all those language came with objects, right? And the world has seen that how the object-oriented things are much more handy to use. So those things have been in demand and that has been implemented through the access routines. The next thing, the next generation of PLI routines are called VPI routines. Let us see about this. Verilog Procedural Interface, right? VPI. These are called VPI routines, are the third generation's PLI, and this is currently being used. The VPI routines are currently being used, and in my work experience, I have already used these VPI routines. However, these are not written by me. Those were written already by the tool vendor and readily available for the usage. Most of the time, the coders of the Verilog simulation software, they provide the VPI routines. And to some extent, these are also becoming ready to use, ready to cook kind of things. That means the VPI routines for the verification IPs. Inside the verification IPs, these things, the VPI things will be there, because the verifications IPs are nothing but to test your verification and make your verification faster. So the verification IPs from any IP vendor, if you are getting, those will contain the VPI routines nowadays. So this is the latest hot and happening thing. Obviously, you will come across in case you are a RTL engineer. This routine starts with character VPI, provide an object-oriented access for both HDL structure and behavioral objects. You come to know about the things that how this is there. So it's also object-oriented. The VPI routines are the superset of functionality of the TF routines and ACC routines. That is why I said the VPI routines is the hot and happening thing in the front-end verification today, and these are packed inside the verification IPs. Whatever company you are getting verification IPs from, those will contain the VPI routines, and that's how you can use them readily. So all those things are made ready for you. You don't have to code it and you can just use it. However, until or unless you don't know the fundamentals, you will not understand and you will think these are some alien things and we do not know what we are using and what is is inside that and you will consider it as a black box. But right now, after this slide, you know that the verification IPs what are the tool sets inside that. At least one tool set you know that these are VPI routines which will be used for the digital verification purpose, the front-end verification purpose. So here we are done with our discussion of the different ages and generations of the PLI routines, and we also talked about the latest hot and happening VPI routines. So now move on to the next slide. Hello world through PLI. In this slide, we'll show you the infographics, very simple enough, and how a hello program can be incorporated through the PLI routine. So here is our hello world.v and here is the content. You can see it is the module and the name is hello world. We have an initial block starting and ending with begin and end, and here we are calling a user defined task hello world. Now where we are defining this? We will define this in our hello world.c. And the content of the hello world.c is here, and here we include this particular header file and we write a user defined function int hello world, and here we give the IO printf. So this is used for the echoing, that means the echoing of the hello world. And altogether when we execute through our already shown infographic process how PLI works, right, a couple of slides back, there we have talked the process through which we get the output. Once we go through that process, our output will come as hello world. So this is very simple enough to understand, and here we are done with our PLI routine and how the PLI routine works and how the things call each other. So here we are done discussing about the PLI routines and the hello world program through it. Let's move on to the next slide. User defined system task and function types. In this slide, we are going to talk about the user-defined system task and functions that you can write in your PLI routines. We've just shown you the example. Before that, we have shown you the infographics. And now we are going to the details of the task and function types. So let's start. The type of the user-defined system or task and functions determine how a PLI application is called from the Verilog HDL source code. The types are as follows. A user task can be used in the same place of a Verilog HDL task can be used. So this is the beauty. A user-defined system task can read and modify the arguments of the task but does not return any value. This is a very important point. Please remember this. A user function can be used in the same place of a Verilog HDL function that can be used. This is the beauty, right? Where you hack into the system and you reverse engineering the system, where you are not using the already provided function or task. You are writing your own task and functions to reverse engineer or break down the data structure that is encapsulated. And from there you are fetching the data. All these things you are doing. A user-defined system function can read and modify the arguments of the function and it returns a value. So very simple enough to understand. So let's move on to the next point. The bit width of a vector shall be determined by a user-supplied size TF application. So this is another important point that you should remember. And here we are done with talking about the user-defined system task and functions, how they behave and what are their types. We are done here talking, and let's move on to the next slide where we will talk about conventions of these tasks and functions. Conventions for user-defined system task and function. A user-defined system task or function name is the name that will be passed within a Verilog source code to invoke the PLI application. Please remember, this is not a standalone thing. It has to pass through the PLI routine or PLI wall, and that has to communicate in a proper way up to the compiled data structure. The name shall adhere to the following rules. Number 1. The first character of the name shall be a $sign. Next, the remaining character shall be letter digits underscore character, right? This is the underscore or the $sign. Uppercase and lowercase letters shall be considered to be unique. The name is case sensitive. So remember, this is case sensitive. The function or task name, the way you write the same pattern of combination of the caps, you have to maintain and use throughout. The name can be any size and all the characters are significant. So this is the convention for the user-defined task or functions that you must follow as a RTL engineer. So here we are done, and in this particular video we have talked about the PLI routines, how they work and what convention you should be using, and how in an up-to-date situation or scenario how the PLI routines any VLSI RTL engineer is using and what is the purpose. We are done here. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below. And bye for today.